Welcome in Ventspils, to whom managed to arrive in person, and welcome all online participants as well who are connected now and connecting in the next minutes. We will start our first multi-project technical workshop, and this is focused on physical modeling and blue and green transitions. And intention is to show how we can, researchers in this case, model our world in physics and bring this to some kind of products in the future. Today we have day one, and we have following agenda. So first talk will be by myself about physical modeling, some kind of introduction, why we are here. And next talk will be by Modris Dodolis from Riga Technical University, insights of SolidWorks and how it works. And later we continue with more dedicated SolidWorks for future activities and some recent innovations in this SolidWorks program software. And it will be joined talk by Martin Johansson and Alex Askidel. After that, we have lunchtime, and actually I make a wrong copy of this presentation, so I need to switch to original one. So yes, so this is last copy. Later we will have Christian Tabri, our colleague from Tallinn University of Technology, with his talk about two tools and numerical access for maritime accidents. And we have two on-place colleagues, Ronald Jakobsons and Sabine Hochner, which again focusing on modeling using OpenFOAM, and continue with Marina Konjuhova about
megawatts to our area of our engine body.
But
this
please
is Tauron 20 megawatt and Promet plus 20 megawatt facility. But in terms of production of fuel in Poland, this is quite different to your cases in Finland, because we have to calculate in our projects our renewable source.
Yes, so it works. And later this day we'll have hands-on activities. Again, so it's some kind of challenging task to try to show how SolidWorks will work in practice. And we'll have some kind of hands-on activities to run and see how physical models could be executed. And for next day, we continue with face-to-face talks. And we have, let's say, our keynote from Latvijas Flote, Laura Poga, with her vision about fleet developments and port developments from Riga side, and several talks about modeling, and I will continue tomorrow and describe it in more details. And for today, for hands-on activities, who are willing to participate and join this session at 3 o'clock, 3:30, please respond to my email in the morning, because we need to make it interactive, and we would to know how you contact you and connect you to our workstations. So I think this is all from announcements. And if you need internet, you can use Ventspils. I think it should work here, and there should be no problem. And I will continue with my talk. About physical modeling, and trying to summarize what we are doing here. And first, several words about multi-project and why we are trying to collect all people together here. So MARTE is a Maritime Technology Excellence Hub in Sustainable Blue Economy in the Baltics. So it's a project, but we would like to make it sustainable and make after the project community which works together. And our mission is connect science and innovations and support the improvements of the maritime environment, efficient use of resources, and the development of sustainable blue economy. And this includes everything related to Baltic Sea, coastal regions, ports, and industry who working on these fields, and people who live here, also local authorities and institutes and universities who are trying to do some research and innovations in this field. Project started in 2025, and we're going to organize at least 3 similar workshops for scientific dissemination and show how we can do science and how the science could be useful for our industry partners. And in this case, 1 second. So MARTE, it's unite a so-called Quantiple Innovation Helix framework, which collects academia, industry, government, civil society, and environment itself as a wide partner. And this is 2 countries, Latvia and Estonia. Together we are 13 partners, civil society like a Baltic Coast, Worldwide Fund for Nature, Estonian Iceland Cooperation Council, public authorities like Environmental Investment Center of Estonia, Saaremaa Development Center, Kūrja region, and Latvian Investment and Development Agency, and supporting with research from Tallinn University of Technology, University of Tartu, Latvian Institute of Aquatic Ecology, and Ventspils University of Applied Sciences. So we are here, and industry and business partners and stakeholders as well, the Estonian Maritime Industry Association and Ventspils Freeport Authority. And so how we can combine all together and how we can boost research groups to communicate with industry and understand what industry partners need and how research could help to make a new deep tech products in this case. And probably in this day we speak a lot about technologies, but it's good to understand what is technology itself and how it could be developed, and basic principles of technology readiness level. You can see it here. Try to make it laser pointed as well. So we need some ideas, and when we have idea, first of all we need to define it and make some first assumptions. And we could achieve basic principles observed, so some preliminary studies, feasibility studies, and we got to L1. Going next, we need to test this idea. Is this working or not, or it's maybe completely impossible to do something? And we formulate technology concepts and make some first laboratory tests and some first models, maybe on paper, maybe on computer, maybe sitting in laboratory technical benches. And when we are finished our research or make us like an experimental proof of concept, we somewhere in research level 3, and this is mostly institutes and universities do this like a research proof of concepts. Next, we need to go and collaborate with industry and think how our ideal concepts could work in real world. And we need to make some kind of prototypes and test them in laboratory. And after that, validate in real environment. And usually here, so it's mostly researchers, but here we bring also entrepreneurs and industry who would like to use this technology in later stages. Next, when we are ready to say something, okay, we have a prototype is working as we expected, we need to make it some kind of, not product itself, but a prototype which operational in demonstrated in an operational environment in real life in this case. And after that, we can make our certifications and licenses, for example, if we need to move it to market. And this part is mostly related to industry. In this case, industry need to join this research and bring this efforts to bring this at product level. And if you divide, make it a real deadline and achieve a fully operational system, so we say, okay, our, for example, hydrogen compression system working as we expected, we can sell it. And this goes to fully industry and entrepreneurs who need to disseminate it for the later public. And when we're speaking about physical modeling, we are somewhere here, TRL 2, TRL 6. In different levels, we need different kind of approaches and models. And maybe first of all, I will say a couple words about Ventspils itself. So we are in Ventspils University, and in university, science related institute is Ventspils International Radio Center, do astronomical, radio astronomical modeling and far beyond a lot of activities related to space and physics itself. And here is an example of some models and the real results. I show a telescope, 32-meter telescope, which located near Ventspils in Urbana, 30 kilometers outside. And when we start to develop some new instrumentation or new ideas, so we need, and usually we start with visualizing concepts, and it helps to do some 3D modeling tools. We can use these 3D modeling tools and print a prototype in 3D printers, and these give us like a first preliminary understanding what we would like to create. Later, in later stage, we need to add physics and analyze how physics-based simulations can be involved in our design. For example, here you see this is like a vertex loom of telescope. Here is one more, and inside is a cryogenic system which works in 20 kelvins, so it's minus 250 kelvins. So very dedicated system which have to work on moving conditions. So its telescope is rotating quite fast. And we need to analyze how this model not only smooth design and smooth result concept, but how it physically operates. And next, we need like engineers and industry support to create this in a physical in metal. And using models, we can skip several steps over like a laboratory testing, trying to understand so how our model will survive under different conditions. And here, how it looks in practice, for example. So we have nice plot, which could be done rather easily, but could be not enough to understand if these, for example, transitions and heat sinks works under cryogenic conditions. So, and first of all, we need to make it drawings. After that, we need to test it, and after that, we can do it in metal and test it in laboratory in metal. And after that, proofing our physical model. And very often this is interactive process. So we're creating a prototype, find out what our model was not precise, and we need to adjust it, like I mean physical model of our vision. We adjust model, improve it, and give new results, and we'll see new prototype in a metal. And physics itself. So how we can, what we can calculate using our models, and usually it's starting from structural mechanical, like a stress, strain, deformations and fatigue and vibrations, which give us some estimate of our constructions. Next, very often we need to include heat transfer, like a conduction, convection, radiation, and thermal management, showing how our, let's say, engine or compression system heats in time. And this is sometimes very critical if you are not able to make an equipment which cooling down in particular temperatures, you probably will be overheated and system not working. Next, we're adding some fluid flows like gases and liquids, one or two or both. And very often we need to make like airflow simulations or water currents or turbulence and pressure losses. For example, if you're trying to build a wind turbine, so we need to make a analysis how this wind turbine will survive under different wind conditions. And one option, we can use wind tunnels, like physical wind tunnels, which are good enough to test like a scaled models, but sometimes it's not completely enough to like proper understanding of 200-meter long blade, how it evaluates in different wind conditions. And we definitely need a model of this turbine in our SolidWorks or OpenFOAM, for example, and understand how models could be adjusted with real conditions. Often, and we also use electromagnetic process like magnetic fields and forces and inductions and the electrical forces, how they could be modeled. And here's an example of permanent magnet modeling again. So we need to understand how these forces influence of our strengths of our construction and works together with like movements and so on. And next step, we use multi-physics interactions. So we use several like physical things like a flow and heat, electromagnetic process and mechanics like a structure and thermal coupling. We need to model them and understand how our future best prototype will survive on different conditions. And in many cases, this is not a static process, but this is dynamic. So we need to find out transients and instabilities in our prototype in different conditions and how in real operation conditions it works. Next step, it could be when equipment is created, or let's say wind turbine is built, we would like to see how long it survives. And it could be so that we create a so-called digital twin, which lives same life as a real wind turbine, but in a digital form, and we can see how these structural changes in time, and if we see some kind of parts of this wind turbine need to be replaced in year time, we already know what we need to buy additional parts, for example. And some example of flow, that's like a compressor chamber, what we are trying to model, and in some kind of dynamical process of liquid and flow and air animation in one compression chamber, for example. And what we can see here, and some kind of different ways and different structures. So before we build a real thing, we can try different scenarios, find out best one, and like save time for prototyping and understanding of things. Yeah, so it's some kind of nice plot that could give us statistics and answers how this equipment works in real conditions. But now we're speaking about like a small scale instruments or models or prototypes, let's say laboratory testing. But very important about extend our physical modeling to Earth systems, to model a global process which occurs around us. And tomorrow you will see our colleagues from University of Latvia describing how we can also model atmospheric conditions and how this process works. And usually, so it's like a atmosphere, like a wind pressure, temperature, clouds, extreme weather predictions, ocean models which involve currents, waves, sea level, and temperature distributions. And actually, each of us use these models almost every day. So probably first in the morning, what are you doing? You're looking on phone and looking forecast for today. Is it cold? Is it raining or not? But behind this is a very complicated atmospheric and Earth models, which provides us forecasting data. And usually these models are extremely heavy for calculations, so it's not possible to just run it on single station. We need very dedicated clusters for it. And here, these models also give us like a short-term forecasting, let's say couple days, couple weeks, maybe months. We're looking also for long-term simulations, we're saying years and even hundreds of years, showing how our, for example, Baltic Sea change in temperature and saltness level, for example, and how our life changes during this period, for example. And this is, again, physical model, which not only complicated, but also could be not very precise. So, and probably you see forecasts for a couple months, and usually it's 50-50. It could be true, it could be false. And unfortunately, even our technologies at this moment not able to predict what will be after a couple months in our clean climate. So how it's, is it summer will be warm or it will be raining? Nobody tells you. This is some kind of variability, but not exactly precise. And for these models, usually we need high performance computing and parallel calculations. And going next, some examples of these models, which models of oceans and atmosphere, actually a lot of and different one. Here's maybe some of the latest one, Copernicus Interactive Climate Atlas, and just showing how temperature rises in exactly northern pole. So we are suffering from higher temperatures actually in last 10 years, and it goes 10 years in future. So it's climate changes, and you can see it, and you can model how precisely. It's a good question, but it's a tool that we can use. And the same instrument, for example, new European Wind Atlas, which shows how wind resource could be available in a Baltic region. And here is yellow, so it's very windy and very nice for wind turbines. Bluish, it's more or less okay, but maybe not so good. And again, for this model, it takes like 30 years of modeling data. So it's models from 1985 up to 2020 somewhere. So it's modeled data, so about wind resource in complete Europe. And in size, it's around 80 petabytes of data. So if you just compare your hard drives in your computer is around, let's say, terabyte, 10 terabytes nowadays. Here is 1,000 times bigger data space what we need, and to store and analyze this data. And again, so scientists not only stopping on here, and maybe I will show you some video at the end of my talk. So how looks to model galaxy in millions of years. So it's a forming galaxy, and we could model not only small processes in a year, but it's possible to organize and model billions of years of evolution and in distance of hundreds of parsecs. And this quite nice physical model. So again, completely different one. So we're starting from small prototypes and small physical models that we can use and to create let's say drone or vehicle. But there is something completely different. So it's physics which shows how galactic is formed. And yeah, so it's some kind of nice examples. Yeah, I think I will stop here because it's like a mostly introduction of what you will hear and see in next days. So we cover a long list of different and difficult topics of modeling effects of physics, what we can put in numbers in computer and work with them and see how it evaluates in the product. Yeah, so thanks, and maybe we have a couple questions, time for questions, and we'll change to participant view. So I see no in the chat, no questions, so don't hesitate to ask something and to use your microphones as well. So no. In this case, I would stop myself and stop sharing my screen and give floor to Modris Dobalis. Modris, are you here? So I stop sharing screen so you can try to share your screen and continue your presentation about SolidWorks at RTU from academic training to industrial certification. And we can start going in more details about modeling things.
Okay, good morning, everyone. Thank you, Vladislav, for inviting me to your workshop. I'm honored to be here and pleased to share my academic and research experience with you. My talk is much more down to earth, focusing on introductory education in modeling and simulation. SolidWorks plays a central role in modern engineering education, not only as CAD system, but as a platform for developing engineering thinking. At RTU, the focus is on using SolidWorks to connect spatial reasoning, modeling, drawing, production, simulation, and decision-making, preparing students for real industrial workflows. This presentation outlines how academic training can be efficiently aligned with industry expectations and certification pathways. When we talk about SolidWorks in education, it is important to move beyond the idea of teaching a software tool. In modern engineering programs, SolidWorks serves as a foundation for developing engineering thinking, not just creating geometry. SolidWorks, serious enough for engineering, friendly enough for Latvian education budget. How to forward? Oh, got lost control of. Next slide. Okay. Current engineering SolidWorks performs like BIM, using a single shared model for real-time cooperation, coordinated updates and conflict detection, what engineers generally call PLM, product lifecycle management. Concurrent the widespread adoption of practical application of PLM and BIM models across engineering disciplines will only streamline design and collaboration, but will also fundamentally shape how products are developed, managed, and brought to market ultimately defining the future of industry. At RTU, we use SolidWorks to introduce students to the cause and effect relationship between design decisions and real-world performance. Every modeling choice, dimensions, constraints, symmetry, or simplifications has consequences later in analysis, manufacturing, or operation. Another key reason for using SolidWorks is continuity. The same model created in a basic CAD course can later be reused for structural analysis, flow simulation, and parametric studies. This allows students to understand that engineering is not a sequence of isolated subjects, but a connected workflow where modeling, simulation, and validation are tightly linked. Finally, SolidWorks is widely used in local industry, which makes it an effective bridge between academic and real engineering practice. Students not only learning concepts, they are learning them in an environment they are likely to encounter again in their professional careers. After explaining why SolidWorks is important, the next question is how it is actually applied in the curriculum. Here I show my flowchart of two of my courses where SolidWorks is introduced early, one of which was enhanced with European funding. I expect it to be reinforced across multiple study courses and levels, rather than being confined to a single standalone course. The introductory overview course is offered to about 200 students each year across 6 study programs. Students first encounter fundamentals of engineering graphics and the basics of SolidWorks. In the advanced course, the focus is on parametric part modeling, assemblies, and documentation. Advanced SolidWorks I deliver to 60 students, and this course follows detailed prerequisite course on engineering graphics. And here students, along with SolidWorks, progress to learn assembly, structure, and design intent, proper use of mates and constraints, and engineering drawing that follows standards and manufacturing logic. A key transition happens when students move from simply creating geometry to understanding why a model is built in a certain way. Here emphasis is placed on model robustness, clear feature structure, and future use of the model for simulation and modification. This approach intentionally prepares students for later courses where the same SolidWorks models are not rebuilt from scratch, but extended into analysis and simulation tasks. In this way, SolidWorks becomes a continuous learning platform rather than one-time software skill. I use the following teaching method. Practical exercises are conducted simultaneously in 2 computer labs of 30 seats each, as RTU does not have a single lab with 80 to 100 seats, unlike a friend of mine, a professor in Germany. I present short theoretical concepts in PowerPoint, stream them to the second lab via Zoom, and record them for later review. Both labs have 2 large screens, and in the second lab, a colleague assists me. I use flipped classroom approach. The students are required to watch instructional videos before the session and then workflow, work independently in class and on exercises. I manage the computers on both labs using Vayon software and taking control whenever a student encounters a problem to demonstrate the solution. Usually, if one has the question, several others do too. Then I take the control of the student's screen and share it on both classes, demonstrating the solution without wasting time to walk to the student's seat. Something is wrong with so here is the class I showed before, and somehow the synchronization doesn't work well for me. Sorry. Final goal for the task they have to master is to prove the control over the design intent. In the first easiest step, students are are given typically 4 answers, and they have to choose from the 4 answers the correct one. Those who are not patient may submit the solution, but they just get partial credit. For the serious studies, they need to work constantly on this problem in several steps to solve the problem by themselves. The goal is to let the students practice to master design intent by themselves. And Moodle quiz serves purely for self-assessment. The teacher is built into this Moodle system. At RTU, SolidWorks is primarily used for learning and concept understanding. Models are simplified, assumptions are discussed, and results demonstrate just basic principles. In industry, models are more complex and must be robust, reusable, and clearly documented to support simulation, manufacturing, and decision-making. Historically, industry representatives have sometimes complained about our graduates that they have poor skills in interpreting mechanical engineering drawings. Partially, it was caused by decades of limited funding for PCs and CAD software, as well as university curriculum changes after Latvia regained independence. 10 years ago, we still held so-called CAD Olympic contests for the students to challenge them to more industry-like tasks. But today, such contests are too complex to run them at all. Highlighting these differences in studies helps students bridge the gap between education and real industrial workflows. To extend the impact beyond the university, the current course is being duplicated on an open MOOC platform. Its purpose is to lower the entry barrier, spark interest, and guide motivated learners toward more advanced lifelong learning programs. At the university, they have to subscribe for these later. And in recent years, RTU has organized free introductory courses with several EuroCC project initiatives. These courses are not only focused on CAD skills, but also on motivating engineers from the industry and students to use HPC resources for large-scale simulation tasks. Some industry-inspired examples from these activities I will demonstrate in my lecture tomorrow. One practical way to align academic training with industry expectations is through SolidWorks certification. Certifications like CSWA and CSWP and simulations-focused exams provide a clear, externally validated benchmark of skills. There is a list of 14 different exams available to RTU students thanks to the current license subscription. In this sense, certification becomes not just a personal achievement, but a bridge between open education, university studies, and industry needs. The illustrated certification track shows the recommended sequence on how to form a clear skills development pathway. For students, certification structures learning, builds confidence, and creates a recognizable reference for employees. In our course, certification is positioned not as an obligation, but as an opportunity. At the end of the course, students may take the certification exam free of charge, and this serves as a carrot rather than stick, which significantly improves motivation and engagement in compulsory university course. From education perspective, certification also benefits instructors by providing a clear target competence level, objective feedback on learning outcomes, and a shared language when discussing skills with industry partners. A straightforward practical approach to parametric feature-based modeling. I was surprised that industry representatives who already work with SolidWorks daily are still willing to take the time to prepare for CSWA certification exam. Here you can see the schedule of these courses which they took after their working hours and took this certification exam when they joined lifelong learning course at the university. To conclude, I would like to return to the main message of this presentation. SolidWorks becomes truly valuable in engineering education when it is used not only to create geometry, but to support reasoning, analysis, and decision-making. By integrating modeling, simulation, and certification into the curriculum, we can better prepare students for real industrial workflows. From an educational perspective, the key is consistency. Consistent tools, consistent methodology, and consistent expectations aligned with industry practice. Thank you, and I look forward for continuing this discussion tomorrow from more technical, hands-on perspective. Sorry for technical problems while switching these slides. There was some problem with my Zoom.
Thanks a lot. we are very appreciate your talk, and this is again what we need for understanding for beginning of work for next talks. And maybe some questions, and just to be sure I understand correctly. In Riga Technical University, you have a main course for students, and also this course is available for not students as well. Is it right?
That's correct. Yes, they are organized some within other projects, some courses, shorter course and extended course like you saw before, 16 weeks, or just 4 days. And most important is that these courses are free of charge.
Even for not students. So
yes,
anyone
that's correct. That's correct, but they usually are organized just once a year for interest from industry.
And you show a lot of industry representatives also willing to join these courses even at evening times after work. Could you
yes, that's correct. That was my
work?
surprise. I was wondering, they already have work. They work with SolidWorks. And my question was, why do you need this certification? I understood that students need this certification when they are looking for their next job, so they can show that they have some practical skills. But those who are already working, that was my surprise.
Entrepreneurs who are hiring people, are they appreciate these certificates? So they're asking about certificates for people who are looking for work. So how important for like a potential worker or engineer to have this certificate? So how it helps to raise salary or find a job?
Yeah, that's an interesting question to work on this. I have not studied about this. Sorry.
Okay, but thanks a lot. Thanks again. And if any would like to ask questions, I see no raised hands and nothing in the chat. Yes, thanks a lot, and we'll see you tomorrow. So I give floor to Martin Johansson. Folks who have to be connected. Martin, are you here?
Yes, I am here.
Nice to see you, and welcome in our forum.
Thank you.
So, Modis, could you switch sharing of your screen? Okay, yes. So,
and
Martin,
I can also see that Alex is here as well.
I am. Hello, everyone.
Good to see you, both of you. So, Martin, you will start, right?
Yeah, absolutely. And I'm waiting for Alex to start sharing the presentation we have created for this session. But I can just start by saying thank you for having us to mark the first technical workshop. We are, of course, sad that we cannot be on site this year, but we are very happy that you have invited us. And the meaning of our session here is to talk a little bit about the newest features in SolidWorks. And of course, something is from 26 and some are from older versions, but that will be covered by Alex. And I think that I will start by introduce the company we're working for, PLM Group, to start with. So Alex, if you...
Martin, maybe
yeah.
On your screen you have like a black boxes, probably it's Zoom. So if you're able to like put it somewhere outside or just move it a bit like out screen.
Yeah, let's see. It is Alex that doing the presentation. So let's see. He will fix.
Was that better? Was that better?
Yes. Now it's perfect. Yes.
Okay. Great.
Yes,
Sorry.
for interruption. You can start. Yep.
Of course.
Good. So I think that Alex, we can go to the next one there.
Yep.
Next slide. So first we will of course introduce ourselves, and I will start. My name is, as said, Martin Johansson. I work as early engagement team leader here at PLM Group, and I'm located in Värnamo, Sweden. And early engagement for us is that we distribute the licenses for education, for research, but we're also very connected to our SolidWorks for Startup program that we'll talk a little bit about. But that is what I do the most of my working days.
And my name is Alex. I work as an application engineer for PLM Group, which basically means that I spend a lot of time with SolidWorks, doing a lot of trainings. And as Modris just mentioned earlier, I also do a lot of certification. And I have spent right around 14 years with SolidWorks right now, and have conducted hundreds of trainings and also a lot of webinars like the ones we are looking at today. And I am very happy to be able to show you some of the features with SolidWorks 2026.
Was also very nice, very pleased to see Modis talking about the certifications. That is something that I also push the educational institutes to really use to help the students to become as good as they can within SolidWorks, and also use it when they are searching for their work opportunities. And it can also be used as a quality stamp, even if you are a experienced user. It's always nice to have a certification that can prove how good you really are. So, but what we do at PLM Group is that we empower your value chain, we say. So we provide software solution and expertise to support organizations to develop and manufacture innovative products. So with our help, users become more agile with efficient operations, which will lead to a sustainable product development model. Next slide will...
Oh, sorry. Give me a second. There you
Yeah,
go.
no worries. Perfect. So short about PLM Group in numbers. We are a quite large organization or company. We have 190 employees, and we are spread in the Nordic and Baltic countries. So we are in Latvia, Estonia, Finland, Sweden, Norway, Denmark, but also on Iceland. And we speak in 9 languages, which means that we are able to support in local languages, which is very important. Unfortunately, not today we got any of the local resources in Latvia to join this, because they were occupied with other work tasks this day. We are very proud with our customer satisfaction, which means that they give us very high grades when it comes to our support and trainings and consultancy. And as you can see, we work with a lot of SolidWorks users out there, more than 12,000, and they are being helped by our more than 60 own software experts, and all of them have different kind of certifications in different specialties. So this is our value chain. We talk about design, simulation, CAM, PLM, and 3D print. And I will just briefly explain each section of those. So if we look at design, we help them, the mechanical CAD users design with SolidWorks, CATIA, and DraftSight to bring their products to the market faster. And we make sure that they have the correct CAD tools for their design needs, no matter what the size of the company is. And we can, of course, help to expand when that is needed. So we enable the engineers to design and create innovative products by providing the CAD tools needed to take the initial steps from design, and then collaborate across functions and different stakeholders. So by connecting the design and the team in a common platform will increase the efficiency of the design part. Simulation have become a very important segment. It is, of course, very important when you design that you also have the opportunity to test and validate the product before they become real-life products. So we can predict this real-world performance virtually by simulating how the products will behave. And we have the top tier expertise in simulation software and techniques that can help you to become as good as possible in the simulation part. CAM is another segment, and we are a trusted partner to SolidCAM. And as you know, every minute counts, and of course, every CNC machine must also be used to the very maximum. So we empower to optimize efficiency and minimize the downtime in the production for the simple as well as the most complex products needed to be used by using SolidCAM. They are customized to address specific challenges and to achieve the competitive workflows. And also in this segment, we have our own experts with many years of hands-on experience that can help. And the last part of the value chain here is the PLM. And by using PLM, product lifecycle management, we ensure that innovation flows seamlessly from the idea phase to the impact creating value across the entire product lifecycle. And also here we have the best practice frameworks and the scalable technologies. And our platform 3D Experience will help to align the people, processes, and data, all from the customer concept out to the customer. As said, we are local, so we operate across the 7 countries. This to ensure the seamless support wherever you are as a user. So 190 engaged employees. Very proud of our customer satisfaction that is on the level of 98%. We have, as said, offices in the Nordic and Baltics, at least one in each country I mentioned. Except Iceland, we don't have any office there, but we distribute the licenses from our Norwegian office to Iceland. And we, of course, offer the opportunity to scale as a company and use and make sure that you are future ready. And finally, I want to talk a little bit about the SolidWorks for Startup program, because that can be of interest in this forum. So SolidWorks for Startup program is, as said, a fantastic opportunity for newly founded companies where they can take their ideas to real product and become a business. And the startup program actually includes free SolidWorks licenses, simulation licenses, licenses for visualizing the products, and also, of course, access to the 3D Experience platform. It is basically a 3-year program where you start with free licenses first year, then you have high discount on year 2 and discount on year 3. This to really help you start the company in best way. We, of course, offer our local support. We also do co-marketing opportunities, which means that we do marketing cases together with our startups to showcase their products and their ideas. And we offer this design guidance from SolidWorks engineers, our own or other ones that are out there in the different communities. And who can apply to this startup program? It is, as said, for the newly started ones, so not older than 3 years, but we used to say not older than 5 years. So that is perfectly fine as well, but less than 1 million euro in total revenue and less than 1 million euro in fundings. And you, of course, need to develop a hardware product. So the SolidWorks for Startup program is not for engineering services, and you should not be a SolidWorks customer before. So I think that this is a quite natural step when we are talking about how to provide students with licenses, with the opportunity to get certified. And if they want to try to start their own company, they can, of course, use the SolidWorks for Startup program. But as said, it is very important to remember that even most experienced SolidWorks users that have been working within the industry for many, many years also start their own companies and search for the SolidWorks for Startup program. So that was all from my side. Once again, trusted by our industry-leading partners. You might know these logos, Dassault Systems. They are the owners of SolidWorks, Simulia, CATIA, And then we also partner with SolidCam. We have experience in the 3D Experience platform to help customers to start to use that. And it is actually so that every new SolidWorks license that has been sold from the 1st of July 2023 come with access of 3D Experience platform. So it is now a natural part of the SolidWorks license. And DryWorks is also a partner that we work with when it comes to design automations.
Okay, Martin.
Yeah.
Thank you. All right.
Go well. Thank you.
Thank you. Okay, so I'll just go ahead and jump straight into showcasing some of the features you'll be getting with SOLIDWORKS 2026. So the next couple of slides will basically be all the new stuff that has been added to the newly released version of SolidWorks, which is the version 2026. And as Martin mentioned, when you acquire a SolidWorks license, you will also gain access to the 3D Experience platform. The 3D Experience platform is a very large platform of a lot of handy tools, especially when it comes to handling the life cycle management of your products, but also enhancing communication regarding the products that you are designing. With the 3D Experience add-in, a bunch of new features has also been available for the SolidWorks installation. And one of the features that we were very proud to announce last year was a beta version of auto-generating drawings. So I remember Modris talking about some drawings and that there might be some issues with the level of quality that comes with the drawings. Some other honorable mentions is the brake line dimension. If I were to add the entire list of all the enhancements that we find on the drawing side of SolidWorks, it would be a very, very large list. So I've spared you from that. What I basically want to highlight is that the visuals within the SolidWorks drawings in 2026 has been greatly enhanced, which will hopefully assist and support the engineers in being able to produce some very, very good looking drawings for both company and customers. So there's been a lot of improvements on the visuals of the drawing layout in SolidWorks 2026. But before we continue, let's have a quick look on the auto-generate drawings. So we have come up with a model for today's webinar. We've tried to model what resembles an engine bell from a rocket, together with a turbo and some mounting brackets. But for this one part, I would like to try and showcase the auto-generate drawings. So let's say that I'm happy with the way my model looks right now, and I want to generate my drawing, but I haven't got the time to do it, or I want to hurry up and create something for the production line or customer that they can look at right here and now. I can go ahead and click the auto-generate drawing. You can see it's in brackets beta because it'll be upgraded this coming Saturday. I'll get back to that. But I'll just go ahead and click this button. It'll ask for a title and a name. I'm happy with the name it's got right now, so I'll go ahead and click OK. And on the right-hand side of SolidWorks in our task pane, you can see that we have the auto-generate drawings. We have a title, it's the Raptor, a status icon that is slowly loading. I'm not entirely sure you can see this on the stream, and then I'd be able to cancel it. The cool thing to note is that I'll be able to continue to work with my model in SolidWorks while the drawing is being generated in the background of SolidWorks. So I'd be able to continue designing, engineering, creating features, or even go for a cup of coffee whilst my SolidWorks software is slowly generating the drawing. As I mentioned, this feature is right now in a beta version, which is sort of like a work in progress. I am sure you're familiar with the term. But this coming Saturday, so only in a few days, an updated version to the automated drawing will be released with the first service pack of SOLIDWORKS 2026. So status says it's complete, and I'll be able to click open. Since this is a fairly large model, it's a 1-to-1 scale, the individual views of the part is right now somewhat small, but what I can conclude is that the drawing has been able to create some section views for me. It's also been able to import some of my dimensions. I know that all of my dimensions are not here. It is possible to go ahead and modify the information that the drawing will generate for you. But I mean, this is going from absolutely zero automation to the first automation in SOLIDWORKS generating drawings. So this is basically free for me. I can sit back and relax knowing that the drawing is now, it's got some information, and I'd be able to go into my drawing now and then add some more information if I want to. I can also go ahead and delete some views if I don't need it. Anyways, it's still in a work in progress, but it'll definitely save some time for you, and it'll be continuously improved going forward. Okay, so coming back to our PowerPoint, we will be talking about another AI that's been introduced to the 3D Experience platform, and the name of this AI is Aura. So Aura is, for the most part, a chatbot on our platform. And some of the updates to Aura is that Aura will now be able to summarize a lot of information. So right now we're looking at a very large design specification from a customer or a project. And with Aura, we have the feature like Summarize, which will basically shorten everything down. Aura will also be found within SOLIDWORKS. So you can see from here, we are inside SOLIDWORKS software, and we've asked Aura, how do I save this document? A fairly simple question, some would argue, but Aura will give you a very thorough 8-step process of how you can proceed with saving this exact document. So with the introduction of 3D Experience, we have now also introduced some different AIs into our software. All right, the next stuff we will be looking into is some assembly some assembly updates to the 2026 release. What is noticeable is the split configuration and also the fastener automation. So within SOLIDWORKS, we obviously use a lot of fasteners and a lot of bolts and a lot of nuts, and these are usually taking up a lot of work time, making sure that every bolt and nut is positioned correctly within our assembly documents. But hopefully with the new 2026 version, you will realize that the AI will now recognize geometry and automatically attach a nut or a bolt to a hole in our assembly document. First of all, I would like to just quickly jump back into my part. I'll go ahead and close my door, because one of the other news was that for this model right here, I have modeled it both with the turbo and without the turbo on the right-hand side. And when I'm done modeling this one part here, and I have a bunch of different configurations, right now I only have 3, but let's say I would like to go ahead and create this one part of its own. I can go ahead and right-click the configuration, and I can select split configurations. When I split the configurations, SOLIDWORKS will then also acknowledge that there is a drawing attached to this one part, and I can select whether I want to keep it or not. In this instance, I would like to keep it, and when I click Save, SOLIDWORKS will split all the configurations into individual parts that you'll then be able to work with individually. Coming back into our presentation, give me a short second. We will have a look at the assembly updates that I just mentioned. So another thing to have a look at is that working with assemblies usually is a very tedious, time-consuming work, because whenever you update a model, you'd have to update the assembly that the model is referenced by. But with 2026, there's been added some new ways of handling local updates on parts that are contained within an assembly. So if you only do graphical changes to a part that is within an assembly, the assembly does not need to be reloaded and saved like it was back in the day. And all of the work going backwards and forwards from part to assembly is very smooth. In this situation right here, we can see how the engineer is working with very simple parts. So this is not a smart or intelligent part. This is just a part that has been created by an engineer. And as you can probably tell, he is very seemingly just dragging and dropping the components even from the Windows File Explorer directly into SOLIDWORKS. And as you could probably tell, the components will automatically try and snap to some geometry that it recognizes as being a counterpart. So all of this is basically what can be classified as AI recognition of geometry within the SOLIDWORKS software. Next thing we will be looking is going to the 3D Experience platform. So we have this very large AutoCamper that we will be working with today. But the work that I will be doing with this AutoCamper only consists of a few of the parts that is within the AutoCamper. So before I open the AutoCamper, I'll just go ahead and select it. This is in my browser environment. So I'd log on to my Google Chrome or my Microsoft Edge. I'll go ahead and I'll find my large assembly, and then I'll go ahead and add a filter. So I'll go ahead and filter all of the components that I need to work with today. And when I'm happy with what I've selected, I'll go ahead and save this basically as a view, or as it is called right now, as a filter. So I'll just go ahead and name this filter as fridge piping. And when I'm done with that, I'll come back into SOLIDWORKS. So I did all of the work in my browser, but now when I load it from SOLIDWORKS, we can tell that the information that we created or generated in the browser environment is now accessible within SOLIDWORKS. This will greatly enhance the, so to speak, performance issues that might occur when working with large assemblies. In this way, you don't have to open a very large assembly document, then go ahead and suppressing a bunch of stuff. You can go ahead and basically select only a couple of components that you need to edit, and then save them in a browser environment, and then afterwards open it in SOLIDWORKS. This will hopefully streamline your way of working in SOLIDWORKS quite by a large mile. Okay, so with SOLIDWORKS 2026, we've also had some changes to the import performance. We know that a lot of people is working with step files in particular. Step files is sort of like a native language to share geometry from one computer to another computer, especially if the people that you're working together with do not have access to SOLIDWORKS. Stepfile has notoriously been here for many, many years and is a well-supported platform for sharing geometry. But step files also tend to be fairly large. They also tend to take quite a lot of time to open, also in SOLIDWORKS. So one of the new stuff that we've added for 2026 is that when you open the step files, you'll be able, as you might be able to tell from the bottom right-hand screenshot, you'll be able to go ahead and filter components by the size of the component. So in the bottom right-hand corner, there's a picture of a model, and the model contains quite a lot of unnecessary geometry that we don't need. So there's a lot of nuts and bolts within this step file, and we will be able, when opening the component, to go ahead and deselect all of these components, which will then eventually lead to the case that there's not a lot of information that needs to be imported into SOLIDWORKS, and it'll make the import process very, very smooth. But coming back to SOLIDWORKS quickly, so the auto-generate drawings, we already talked about that, and with that feature also comes an import model in background. So this is, again, SOLIDWORKS will be able to import a large geometry. And if I just go ahead and find a step file, like so. So SOLIDWORKS is now opening the step file right now, but it's doing so in the background. And as before, when I was creating a drawing, I will be able to continue to model my SOLIDWORKS part. And right now in the background, SOLIDWORKS is now importing the step file. So this took 17 seconds. It's not necessarily a large file, but you can imagine looking at your SOLIDWORKS trying to import a very, very large step file that takes minutes, and we've seen hours from very, very large files. But from 2026, you'll be able to just go ahead and import in the background, and then you go ahead and click Open File. And when you click Open File, everything is ready to go ahead, and you can start engineering on your step file. So also a very, very handy piece of sort of like background piece of software that came with the SOLIDWORKS 2026. Coming back into the presentation, we are now looking at some of the components that we have stored basically in our cloud environment, the cloud environment being the 3D Experience platform. We saw some changes to the 2026 SOLIDWORKS 3D Experience, which was the ability to go ahead and save configurations as well on the platform, as I just showcased within the software. So this feature was introduced not that long ago, and it took some time to develop this piece of software, because the 3D Experience platform, being a browser and cloud environment, handles our files in a different way that we are used to working with them on our local C drive on our individual clients. All right. Yeah, I've already showcased the split configurations, but I would just like to just mention it for one last time. It is a very, very handy tool to work with a lot of different configuration that represents our product, maybe in different states of the life, maybe in different ways of production. And now with the introduction of split configurations, it's just been very, very easy to go ahead and proceed and utilize all the different configurations that you've been working with. Back in the days, you would imagine that you've built one model and then realized that you'd have to build another model either the same way or in a different way. In this way, you can create a large model file set within one, either assembly or part, and then afterwards you'd be able to go ahead and just split it into multiple different individual parts. One of the new, basically talking about the 3D Experience platform. 3D Experience platform is also focusing a lot of connecting people. So traditionally, when working with CAD files across multiple different users and customers and companies, you are basically used to generating files in SOLIDWORKS, saving them, and then distributing them either as a step file or a pack and go. You will probably today you will be using softwares like Microsoft Teams to share documents, or you might be using any other kind of cloud service. But even as practical as a Microsoft Outlook, basically just emailing stuff in between different partners. With the 3D Experience platform coming into SOLIDWORKS, as you can probably tell from the picture we're looking at right now, we are right now within the SOLIDWORKS software as you are used to, but as you can tell from the right-hand side in what we call the task pane of SOLIDWORKS, you can tell that we are looking at some forums. So these forums has been added to the SOLIDWORKS interface, and it'll basically allow you to communicate directly from the SOLIDWORKS software. So let's say that you are experiencing some issues and you don't know how to proceed. You can basically go ahead and ask the question directly into the SOLIDWORKS forum, and you can attach a screenshot of your model as well. And in this case, Debbie Designer was very lovely and answered us with a question saying, have you tried to use the feature Break View? And we tried to use the feature Break View, and in this case, that was exactly what we were looking for. So we'll give Debbie a thumbs up, as you say, and we will go ahead and validate the answer she gave us as making sure that this was the correct answer for this specific case. So in the future, if people are in the same situation that we were in, they'll be able to see that once Debbie answered this question and it helped us as Eric Engineer, and everyone else in the future will be able to go ahead and use the same solution as the one here. So the 3D Experience platform is definitely trying to introduce a lot of modern technologies, both with AI features, but also trying to basically expand the forums and the communities surrounding and revolving around SOLIDWORKS, basically trying to bring everyone closer together. All right, so unfortunately, a couple of years ago, we somewhat lost the possibility to create renders within SOLIDWORKS. There was an update to SOLIDWORKS, I believe it was 2024 maybe. We lost the possibility to create renders within SOLIDWORKS, but coming SOLIDWORKS 2026, the feature has been added into the software, back into the software again, and this time around it's even been greatly enhanced. So some of you might know the software called Visualize. Visualize is a rendering software that'll be able to create some very beautiful pictures of your SOLIDWORKS models. All of the pictures that you see in the right-hand side of your screen right now has all been generated within SOLIDWORKS Visualize. The model you are looking at is one of the SOLIDWORKS customers that uses SOLIDWORKS to design their Vermeer digging machine. And these pictures has been rendered within Visualize to create some very nice material for both the marketing but also the sales department. And as mentioned, the render possibilities has been reintroduced into SOLIDWORKS, but now also enhanced, which means that the SOLIDWORKS Visualize engine is basically being used within the SOLIDWORKS software right now. So back in the day, so to speak, you'd have to basically somewhat export the document into Visualize, creating your Visualize setup and then rendering the picture, but most of the functionalities from the Visualize software has been attached to SOLIDWORKS directly. So what we look at right here is attaching some very beautiful surface treatments to our model, and as you can probably tell, the enhancements regarding the surface finishes to the material has been enhanced quite a lot. So it almost looks like that there is a 3D mapping to the parts that we are looking at. It is not a 3D map at all. It's just basically been enhanced with what's called DSPBR technology, which makes it look very natural and very lifelike. After this, we will just go ahead and add a background to our SOLIDWORKS viewport, and then we'll go ahead and create the final render. The final render obviously takes a couple of minutes, but I will spare you that. So we'll go ahead and set it to a high quality and click OK. And basically this took right around 4 to 5 minutes, I think, rendering this picture on my PC. So this will obviously differ from PC to another according to your hardware. Okay, another feature that is very handy to look at is the share feature. Because we would love to share our documents with external partners, we will be able to share files in many different ways. One of the ways that we can share our files with is with the share and with the share command within SOLIDWORKS, and we'll be able to share our files with people that don't have SOLIDWORKS installed, which means that we'll be able to share this document, and the person that we're sharing the document with will be able to open this document from a browser environment and look at the model right here. So the new share command will be introducing a process where the recipient do not need SOLIDWORKS to look at the file. The recipient will only need an internet connection and a browser software. Looking at some of the simulation enhancements for 2026, we have some rotational displacement plots, and we have improved on the shell formulation within SOLIDWORKS, and also added some pin connector forces. So we'll be looking at this one model right here. So this model is obviously a very large sheet metal model. A sheet metal model is notorious for being a geometry that is fully drawn, so there is an inside and an outside of the model. But with the shell improvements in SOLIDWORKS, we'll now be able to just go ahead and remove basically all of the inside to the geometry and just defining a thickness which makes the simulation run extremely more quicker than we are used to. So for this study, we have selected our pin as the connector, and we have a coordinate system that we will apply a load to. So with the load applied from the coordinate system to the pin, we'll go ahead and click run, but unfortunately we have an error. So apparently one of our components is missing a material, and from 2026, SOLIDWORKS will now very helpfully explain us which material is missing from what part, and we'll just go ahead and reattach some material, a plain carbon steel, and then we'll go ahead and run the study again. So when we run the study, we will see that the results of this study is somewhat not acceptable. Apparently there is quite a lot of displacement. We'll go ahead and look at the rotation around the y-axis, and we'll go ahead and change it from rads to degrees, and then we'll go ahead and just have a quick look at the animation. And from this simulation, we are not happy about the forces. The forces is definitely too large on our component. So we'll go ahead and jump into our shell manager. So inside our shell manager basically consists all of our bodies within the model, and it's very easy for us to just go ahead and change the thickness of the entire model from 0.25 inches to 0.625 inches, and then go ahead and run the study one more time. So in the meantime, we've changed the thickness of our sheet metal, and from the new results, we can tell that the simulation is much better. What we would then love to, or like to have a look at, is the new vibration plot. So the connector, the pin that was connected to the force, or the force was going straight into one of our connector pins, we can now also have a look at our vibration, our vibration graph. So apparently there is quite a lot of vibration when it comes to a specific point of hertz, and that will then be taken care of by the engineering department. All right, continuing on, I know that we are running a little low on time. I'll try and make it quick from now. We are now able to also include a lot of information regarding our weldment information on the 3DEXPERIENCE platform, which basically again goes to show that we are now able to share a bunch of information regarding our SOLIDWORKS products directly to a browser environment, which makes it accessible for everyone in the company who is logged on to the 3DEXPERIENCE platform. I have a question. Is it I still have a couple of slides left, but I know that we might be out of time. Should we continue on from here, or how should we proceed?
No, I think you could show the slides. I think we can spend a couple minutes more, so it's not a
Okay,
problem.
thank you. Thank you. I'll continue. Obviously, there's been some improvements to the performance within the software. The software is always updated. The software is always being more streamlined. So here's the comparison from SOLIDWORKS 2025 to SOLIDWORKS 2026. And in this one case, we saw an upgrade, or basically an enhancement of 30% faster, basically from the same software, but just the software engineers improving on the codes within the software. Design tables, basically the same as the Wildmans that I talked about earlier. Design tables can be generated from an Excel document. So the Excel document will be making sure that the actual design or the geometry will change according to the Excel document. You have probably already worked with this earlier on. So we are now able to also attach the Excel document to the file that is stored in the cloud, and everyone will be able to access it also from the cloud. These enhancements were also seen in SOLIDWORKS 2026, basically trying to accommodate what you are used to. All of these features are being moved from basically your local client into the cloud as well. Deformable components. I think this is one that we will skip for now just because of the times. One very, very interesting one is the iteration comment. So obviously when we are designing our model, we have a lot of iterations, we had a lot of versions, we have a lot of revisions, and we also have a lot of what's called branches within the 3DEXPERIENCE platform. The iteration comment is basically whenever you save the document, you will now be able to go ahead and add a comment to what changes you have made. And as you can tell from the right-hand side of the document right now, you will be able to scroll backwards and forwards of the individual iterations that you have made. So you will be able to very quickly go back to another time in life of this one product. And if you want to navigate it smoothly, there is the possibility to add a comment of how the part looked back in the day, so to speak. So iterations basically regarding the lifecycle management revolving around the parts. There's a bunch of possibilities with the 3DEXPERIENCE platform as well. My last two mentions is that coming this next Saturday, as I mentioned, we have a big release for SOLIDWORKS 2026. And this Saturday, we will see a new AI being introduced into the software. The other AI I mentioned was named Aura, and the new AI being introduced is named Leo. So Leo will be adding two very important things into SOLIDWORKS. One of them is the assembly structure assistance. Basically, we have a chat with Leo in the right-hand side of SOLIDWORKS specifying what we would like to build in SOLIDWORKS, and Leo will then go ahead and try, as you see from the middle of my screen, will try and build an assembly structure of all the parts necessary for building the actual product that you are looking at. Another enhancement coming with Leo this Saturday is the what's wrong analysis AI, so to speak. So whenever you have an issue within SOLIDWORKS and you are struggling to try and figure out what is wrong and why am I not able to fix my model, Leo will try and help you using some AI-powered engines, and you'll be able to ask Leo what is wrong. And as you can tell from the right-hand side of my screen, Leo will try and guide you through the processes of fixing your issues. And with that, sorry, I know I surpassed the time limit, but with that, that was what I had for SOLIDWORKS 2026.
Thanks a lot. Thanks for you and for Martin as well. It was very interesting and hope very useful for our colleagues as well. Maybe a couple questions if someone would like to ask. I here no response from audience, but I have my questions. Martin, maybe again highlight from your side about startup involvement. So you propose up to 3 years discounted like a license for startups. So its first year is completely free for startups, and startup not longer than 3 years. I think this could be very, very useful for Marte project and Marte community, because we are interested to drive technologies to market, and we are interested to bring new like industry players and exactly startups, students and engineers who are interested in doing their business and doing business in deep tech. And we probably try to promote your advertisement about startup users in much better auditory. Yeah, so it's maybe just comment that this is a nice feature, and thanks for it, because again, from I personally know for small companies it's quite tragical actually to buy a full license. I know you have like a couple weeks free demos or something like this, but sometimes it's completely not enough. And maybe a question to Alex as well. Nice to see IE in like build it in SolidWorks, but is it cloud-based? So you anyway need internet and connection to use this. Is it right? So it's not a people computer.
Yeah, somewhat. Some of it is cloud-based, and some of well, basically, you would need the 3D experience, which is a third-party software, so to speak. CAM Visualize Simulation is also a third-party software to SolidWorks, and the 3D experience platform is also an add-in you would go ahead and download from SolidWorks software. You would install it on your computer, and when you install it on your computer, you basically gain access to all the features provided by the 3D experience platform.
Perfect.
So,
how it's actually stable. So in sometimes using IE, it make not saying errors, but going somewhere wrong direction, and you need to bring it back. So let's say, for example, of automatic drawing recognition and model building. How your experience? How
Yeah.
good is it?
Yeah, so first of all, I've only been working with the auto-generated drawing since the release of the beta version back in November of last year. So it is very, very new. I know that the auto-generated drawing is basically building a drawing from your default template. So the better you also, or the more time you invest into building a very nice drawing template, the better the AI will work together with you. But also, as I mentioned, it was a beta release right now because SOLIDWORKS 2026 is in a Service Pack 0.0. So the Service Pack 1.0 is coming this Saturday, and with that, there will also be enhancements to the auto-generated drawing. So the drawing will not be 100% complete. You cannot leave your head and just click the auto-generate drawing and then go home. But it'll definitely give you quite some free time to continue working with your models, since the drawing has been generated in the background. And we will only see improvements, and you will also manually be able to tell the AI, I would love for you to import these specific annotations. So as a user, you are also able to model the AI into, making sure that these dimensions is definitely important to me. I would love for you to import these. But probably in the future, we will see that the AI will be better at recognizing all of the necessary dimensions to introduce into the drawing.
Okay, thanks a lot. And we're becoming short of time, so thanks for you. And actually, I would like to say thanks for Kasper Ieselnieks from Latvian Thermal Group. He's helped us a lot to setting our computer class. So respectful for this. And so we will keep in touch. And thanks for joining our webinar and workshop as well. Yes, so thank you. And
thank you and bye.
Try to finish our morning session. Now we will have a lunch, and lunch will be until 1 o'clock, and we continue our seminar with more examples, not like overviews of software, but practical examples of what we can do with numerical modeling and modeling of itself. Again, I will try to share my screen and put a program. Please return at 1 o'clock here, or stay connected in Zoom. And people who are willing to participate in hands-on activities can give me a note, or again stay in Zoom, and we will guide you in hands-on activities later at the end of the day. Yes, so any questions, comments from auditory? No. Okay, so you're welcome to have a lunch. Lunch will be provided here just in corner, so in the next room to this auditory, and we will meet here at 1 o'clock. There's a couple persons missing, but I think we can start. Okay, so Christian, thanks for coming, and I will try to announce you. So Professor Christian Tabri from TalTech, Estonia. Welcome here in Ventspils, even remotely. Yeah, let's start. I see my.
Yes. Okay. Good afternoon, everybody. My name is Christian Tabri. I'm a professor at the Tallinn University of Technology and its Maritime Research Unit, Marine Technology Competence Center. And I will now spend about half an hour to talk about how we can exploit contemporary tools, modeling and simulation tools, to simulate what has happened to a vessel which sank a bit more than 30 years ago, and really to show how much we can learn at the moment how the vessels behave using modeling and simulation tools compared to the situation when this vessel was designed and built. So I'm talking of this vessel Estonia that sank on September 1994. It had a bit less than 1,000 persons on board, and out of those 852 died and only 137 persons survived, because the vessel sank in the middle of the sea in very harsh conditions, and it sank quite quickly. And of course, after the accident, there was investigation what went wrong, why such vessel sank, and what could be done differently in future. And official investigation was already published in 1997, and this then stated that the main reason was that the bow visor of the vessel detached under the wave loads, and this opened the access to the water car deck, and of course when the ship got flooded it didn't have enough buoyancy to stay afloat, and that's why it sank. And of course there were always a lot of rumors or speculations around this accident. Was this official cause really what actually happened, or was there something more involved to this accident? And actually in 2020 there was new video footage which showed that the ship had quite a large damage on its side. And of course there has always been speculations that there must be a collision with, I don't know, some submarine or some explosion somewhere, that there must be something which made this ship to sink, and it was not only the bow visor what was the reason. So yeah, those new video footage became available in two reasons. First of all, our technology has improved so much more that we could go into 80-meter deep water and get very good camera image from this water depth. And another thing is that over the time the vessel had rolled a little bit in the sea bottom, so it had revealed what was under under the vessel. And of course, this fueled really a lot of new speculations, kind of that, hey, we told you that there must have been something strange with this accident, because now you see that there are side opening, and this is the reason why this vessel sank. And this then resulted in new investigative activities in 2020. So quite soon it was decided that the preliminary investigation has to be conducted to understand whether the whole investigation of the accident should be reopened. It's a little bit like official terms on between those accident investigation bureaus. So this initial investigation has now taken 5 years. Now it has been completed, and we can then draw the conclusions what we found out. And the aim of this new investigation was then to collect the new evidence and really to model more or less the whole accident, how it happened. And the investigation include quite a lot. It include a lot of surveys at the wreck site, sea bottom studies, wreck studies. A lot of different robots were used. The bow ramp of the vessel was taken to the surface for the investigation, and the whole ship was really scanned in as detail as possible to get the full 3D image of the shipwreck as it lies in the sea bottom. And of course, this gives us a lot of information or the validation data to see that if we simulate something, do we end up in the same condition and the situation what we see there at the moment. Of course, we have to keep in mind that 30 years has passed, so the vessel has shifted in the sea bottom. It has degraded further. There is some corrosion. Of course, it's 80 meters deep in the sea bottom, so there is not that much oxygen there, but still some oxygen for the corrosion. But anyway, a lot of evidence was collected. Quite some material was brought on the surface, which then could be used to validate and to see how well we can simulate this accident. But little bit of the background for the accident. The first Ro-Ro ships appeared in the Baltic Sea in 60s. Yeah, it was quite a new vessel type where the cars just roll on the ship deck, and also it takes on board the passenger. So it was quite a novel ship type in the Baltic Sea. And Baltic Sea is a little bit specific with its relatively short and sharp waves. But it turned out to be so suitable vessel type for our waters. So this number of ships started to increase with enormous pace. And actually the increase in the numbers of these Ro-Ro ferries in the Baltic Sea was the greatest in the world. So nowhere in the world did this ship type see so large usage as in the Baltic Sea. So for example, at the beginning of 1960s, 900 trucks was transported by the sea. But in the middle of the 90s, it was already 140,000. So you could imagine how much more capacity there was at the sea to transport all these trucks. The ship itself was built in 1979, so it was designed then a few years before. And you can imagine how the computer looked at that time. So you didn't have this amazing set of tools and computational power or artificial intelligence nowadays. Then your Apple computer looked like that. So you didn't have that many tools to design the ship. It was mainly paper and a pen what was used for the designing. And also the numerical simulation methods did not really exist at that time yet. They were there in the universities, maybe in some bigger aeronautical companies, they used already some of the simulation tools. But in the marine engineering field, the numerical tools were not really used because they were so new tools. There were no computational power. So it took 15 to 20 years before the numerical methods, what we use nowadays to design ships or maritime structures, really started to have their role in the engineering or maritime industry. And yeah, we talk about computational fluid dynamics to simulate hydrodynamic loads on the ship. We talk of finite element method to simulate how the ship reacts to the loads, or fluid structure interaction methods that then allows us to put together the water and the structure. So these methods were not there when the ship was designed. Also, that kind of progressive flooding simulation softwares, which allow us to simulate in very complex ships like the Ro-Ro ships or Ropax ships or cruise ships are, how the water, if there is some accident, how the water flows or moves inside the ship. These tools started to emerge only in the middle of 2000s. Before that, it was very hard to assess such complex ship, what would happen if it gets flooded. So there was quite limited availability what you could use. And the accident itself happened in 1994. And then this first official investigation report, this was then published in 97. But what was this really an isolated accident? In the Baltic Sea, actually, there was a lot of accident with this ship type and a lot of accident with the visors. So each of these red dots basically indicates some issue or some accident with a bow visor of that kind of vessels in the Baltic Sea. This one, which happened a year before Estonia accident, this was also actually quite serious. I think the ship basically lost the whole visor. But at that time, this information was kind of hidden. It didn't go into public that well, and no one really knew that much of these accidents because all the ship owners tried to hide the facts that they had some problems with their ships. And actually already in 1986, so 8 years before the accident, the ship owners agreed that they will not build anymore the ships with that kind of structural configuration because this configuration is not good enough. So the knowledge was there, but the ships, of course, still kept sailing. So basically what we could say that these ships came to market because the economic competition was so harsh and there was so strong need for the vessels. But really the scientific knowledge and the design methods and the simulation tools, they didn't really pick up. So there was no tools to understand how these ships would behave in the Baltic Sea. And actually Estonia had very poor design. It had, how this visor works. The visor opens, then the car ramp is lowered and the ships could go into the car. In Estonia, the design was such that the car ramp was relatively long. So it means that this car ramp had to be fitted partly inside the visor. So it means if the visor falls off, it pulls open the bow ramp. But the bow ramp for this ship acted as a collision bulkhead. Ships require a collision bulkhead that if something happens in the bow part of the ship, then this collision bulkhead should prevent the water entering the ship. But in Estonia, this collision bulkhead, which was the bow ramp, the design was such that if the visor failed, the collision bulkhead also fails. So if one piece falls off, then your enormous car deck is free for the water to enter the ship. Little bit what's the situation at the moment? At the moment, seagoing ships can't have the visors anymore because the design is not safe enough. So here is a ship with a visor. If you go to a modern Ro-Pax or Ro-Ro ship, you don't see a visor that opens up. You see the bow doors, which opens sideways, and the cars enter through these bow doors. What's the principal difference between those two solutions? For the visor, the wave loads try to open the visor because they try to push it up, this rectangular part. For the bow doors, the waves try to close the doors because you can imagine the doors are here, waves are pushing against these doors, and it pushes the doors next to a ship hull. So much safer solution compared to a visor which has to fully open. So now all the ships which go far to the open sea, they need a bow doors instead of visors. But anyway, our aim in the project was to really simulate this whole process. So we did quite many different simulation models. We started with wave loads that were acting on the visor. We looked on the model scale experiments, which were done in 2007. We prepared so-called computational fluid dynamics model, which allows us to simulate the wave loads numerically acting on the ship. We also prepared so-called multi-material arbitrary Eulerian model, which allowed us to evaluate if the visor was already open, how much the loads changed in that condition. And when we had the loads, we had very fine finite element model of the bow area of the ship, where we then applied those loads. They are waved, they come and go, they come in sequences. So we could then apply these loads to the visor and see how would be the visor respond, and whether the wave loads, what we estimate that they were there in the night of the accident, whether they are sufficient to break the visor structure. And then we also prepared the whole ship model to simulate the bottom contact to see whether it's possible that those damages, what were really found in these new video footages, is it possible that they occurred when the ship hit the sea bottom? So basically that they had nothing to do of the sinking of the ship, but they already occurred as a consequence of the accident. So computational fluid dynamics simulations look like that. You have a ship, you have a waves, and you can then see what's the pressure distribution, and how this pressure correlates to different wave heights and wave directions. So you could get quite good understanding what's the loading condition in your bow structure. We also then did a bit more complex simulations where we were modeled our bow visor as a separate part from the ship so that we could allow it to pivot. Because obviously when the bow is closed to the ship, the visor is closed, it experiences some kind of loads, but when it's already allowed to move, the load level drops a little bit because the visor simply moves away from the waves. So this was just, we needed this to construct the realistic load sequence so that we could really start simulating the process when the visor is fully attached until when it's really torn off from the ship. Yeah, these are the details of the model. We really had to model it in very high detail. We also had to model hydraulic cylinders, how they move, how they get compressed, how they get extracted, because all this played a quite big role in this accident. So very detailed model, a lot of moving parts, like different hinges, different locks, a lot of details in the model. For the final bottom contact simulation, yeah, then we had a full ship, and we also modeled the sea bottom During this investigation, some specimens were taken from the sea bottom to understand where we have stiff clay, where we have some softer clay, and where we have actually hard rock or acoustic sea bottom, so which is basically a rigid surface. Because where the ship lies at the moment, it's hard rock covered by soft clay, but partly this hard rock comes out from the soft clay, so this gives a very local points to the support to the ship when it's at the sea bottom. And yeah, then more or less this is how the simulation looked. We started in the condition when the ship was already approaching to a sea bottom, and then simulated how it fell to the sea bottom. I will have some videos a bit later. Also, some specimens were cut from the actual shipwreck to see what are the material properties. So we were really using the actual materials that the ship was made of. And yeah, this is now the visualization, what happened with the bow structure first when the large waves hit. The first lock, which is also called Atlantic lock, was broken. Then the ship had also side locks, which failed very quickly after the bottom lock failed. Then the ship had some hinges here on the deck. These hinges were also broken quite fast. And then the visor remained attached to the ship only through those quite large actuators or hydraulic cylinders. But, sorry, it's restarted. And you see that the bow, I scroll a little bit back, you see that as this visor is moving, it also pulls open the car ramp already. And the movements are quite violent. So what happens that these cylinders, which are still holding the visor in place, they are pulled through the ship basically. And in front of the ship, it really pulls through those cylinders from the forward wall or forward bulkhead of the ship. And we really see in the shipwreck also these locations where the cylinders were pulled through. So this is more or less how we foresee what happened. We also had then a lot of evidence from the shipwreck, what was left in the wreck, whether our simulations corresponded to this. Also in our simulations, we saw that the cylinders were pulled from the deck plating and pulled through the front wall of the ship. And also in the wreck, you see very clearly where those cylinders have been pulled through. So our simulations correlated actually quite well to the reality what we saw. Also, the visor itself, it has been brought out already years ago. It's in Sweden, and it has quite a lot of damages actually on the visor. And we also were capable of explaining very well from where those damages came from. One damage, which is here, came when the visor fell off and hit the bulbous bow. Then the visor rolled itself around and remained floating in front of the ship for a few seconds, and the ship hit the visor once again, causing this very large damage. But its damage shape corresponds very well actually to ship bow shape. So with nowadays tools, we could really explain almost every scratch in the paint. Of course, it's a bit of an exaggeration, but you could really explain most of the deformations, what we see in the structure. Same with the bow ramp. The visor starts falling off. It opens the bow ramp. Bow ramp also experiences different kind of deformations. And in the simulations, we could repeat those deformations quite well. Another interesting assessment, what we did was that after the accident, the bow ramp was still attached to the ship. And that was more or less the initial condition. The shipwreck was in the sea bottom and the bow ramp was still attached to the ship. But now in those recent investigations, I think in 2021 or 22, they discovered that the bow ramp has fallen off. So what we then simulated, that we tried to estimate where would be a corrosion damage in the bow ramp and what could be the corrosion during 30 years or 20 or 25 years. And we're simulating how would, if this corrosion has developed and the ship, and of course the ramp is still attached to a vessel, how would it be torn off from the ship? And actually, we also managed to achieve the situation what we see in the wreck at the moment. That piece of the bow ramp is still attached to a ship, but the ramp itself has been torn off. So, yeah, we assumed that the corrosion is the strongest in the regions which get a lot of plastic deformations during the sinking, because that's where your paint gets damaged and you are more open for the corrosion. And also, if you look on the shipwreck, then we see that the bow ramp lies next to a ship, and part of the bow ramp is still attached through two hinges to the ship. Part of this is not now our work, but it's German consortium which was subcontracted by Estonian Accident Investigation Bureau. They also simulated the different scenarios. Let's say, how would the ship sink if the visor is open? How would it sink if there would be only side damage? And how would it sink if the visor is open and there is also side damage? So you could really simulate nowadays those different, you could really take the different assumptions and see how would the ship behave in those different conditions. Only with side damage, the sinking was much, much slower compared to what happened in reality. With side damage and open visor, it was a bit too fast. And actually, if the open visor was assumed, then the sinking sequence and duration corresponded quite well to the witnesses' testimonies. And I scroll a little bit further, but yes, how these simulations ended. And yeah, then we also conducted the simulations how the ship would hit the sea bottom. Here we only visualized the acoustic sea bottom. We have removed the soft sea bottom because otherwise it's not that easy to see what goes on there. But that's basically how this bottom contact process was simulated. And as a result of that, we could get quite good estimate for the damages, what should be on the ship structure. And we could then compare these to the basically 3D model of the shipwreck to see whether these correspond well. And yeah, also just to show that we also had this very soft sea bottom action on top here. And this is how this soft sea bottom is pushed away. And from some regions where the center part of the ship is, you see that this acoustic bottom becomes visible. And this acoustic bottom is then this rigid bottom, which causes the main damage to the ship hull. I see that I have only 1 minute left, so I quickly scroll through a few more videos, which see how our simulations correspond to a current position of the shipwreck. Does it this brownish transparent model is the ship's current position. And in our simulations, we achieved quite comparably the same position for the shipwreck. So it means that our calculations are not too off. And then we could also look locally, what are the deformations and damages to the ship hull, and also what's the extent of damage in the ship. So if we cut the slices from the ship, then we see that in the middle of the ship, the damage is actually very extensive. You have like 1/4 of the ship completely pushed together. So what we could see from those videos, they present only small part of the damages, because a lot of damages are actually covered by this soft sea bottom, and we don't fully see them. And yeah, also this, what we saw in the simulations and what's the actual condition of the ship, it corresponds quite well to these damages, what we have seen in the shipwreck. Yeah, very quick conclusion. I don't want to go over the time, but that kind of major accident typically means that several things should go wrong. So in the case of Estonia, yeah, you could start from that lessons were not learned. There were a lot of accidents with those visors, but this didn't come to the requirements. This didn't come to the flag state tables. So the ship owners kind of kept it a little bit hidden. Rules didn't really follow the ship type, and the rules were not appropriate for these ship types. It was a poor design. It was a poor construction as well. And perhaps also inspection and maintenance was not done as it should have been done. So quite a lot of issues which have to go wrong for that kind of major accident to occur. Okay, and that concludes my talk. I went 2 minutes over the time, and sorry for that.
No, thanks a lot. It was very interesting and very comprehensive models that were showing. Yeah, it's okay, a very big strategy about Estonia. But again, it's a lot of lesson learned probably after the strategy. And
yeah, of course.
Remember, right, you show a plot with accidents. And after Estonia, I think it's much less accidents happen in Baltic Seas.
Yeah, obviously. And the ships are much more safer. There were really a lot of changes in the legislation after this accident.
And very interesting how you model so different and difficult and big constructions actually. So it probably takes a lot of time for model.
Yeah. It was quite big group and several companies and persons involved. So it was obviously a team effort. I think in addition to our university, there were 3 or 4 engineering offices involved to prepare the models and conduct the simulations. So yeah, a lot of partners to deliver that kind of study.
And maybe good outcome from it. So it was a lot of speculations about like a human factor and so on. But showing your models, it's clearly seen what is just technical things, technical faults actually.
Yes, but of course, in those technical issues, you also have a human factor a little bit included, obviously as well. That why wasn't this information shared properly? Why wasn't something done already before the accident? But that's how it often goes, that you need one big major accident for the legislation to change.
Thank you. Any questions? Yes, please.
Well,
probably not. Could you come here or just loudly say? No, here.
Sorry, I have one question. Hi.
Hey.
Regarding those hypotheses, did you make any other simulations, like for other speculations, like this was some kind of
Human opening, something like
human
this?
opening and some kind of explosions, just to make sure that the other hypotheses are definitely
those flooding simulations, they were also done for different hypotheses, but not we didn't study any collisions with other objects because it would be the study more or less the same scale as this. And so it can't be done just without really very solid plan and very solid team. But I would say for us, it shows that this all can be explained, what we see now can be explained by the laws of physics, basically. So in order to construct a sequence which is different from that, you would have to have very lot of events with extremely small probabilities lining up. So I would say, yeah, if the physics explains that, is there really, you could always construct some very strange scenarios, but we didn't do it.
Okay, thank you.
Yeah, but good question. Thank you.
Oh, thanks a lot. Very helpful. Yeah, sure. We have one more question, and I think we can verify coming. Yeah, so next speaker would like to ask.
Okay, good.
My question is, you did really impressive work. I really appreciate it, and thank you very much for sharing that with us. But my question is like that: do you really think then, with the tools which existed in 90s, it is impossible to simulate to get those findings which you got? Because let's say we have a good estimation of wave pressure on this how it visor, yes, and we have a good mechanical model for this visor, just mechanical and pilot element submodels from Hinge, for example.
Mhm.
Set, maybe that set can give already that answer already in 90s if someone would look at it.
Yes, I would say, yeah, this official investigation report in 1997, it more or less reached the same conclusions how we did. So they had, in 90s, they said already that this is the most probable cause. But of course, when the ship was designed, the tools were even less. So,
Yes.
and apparently the pressure values, what they use for wave loads and slamming, they were significantly underestimated. This has been proven. And the legislation for the visor locking changed a few years after Estonia was built. And while Estonia had, Estonia had 3 locks. And in those new regulations, it should have had already at least 7 locks. So it was realized quite quickly after the ship was built that there should be much larger number of locks, but this didn't apply for already built ships. But in 90s, they more or less came to the same conclusion already.
Okay, thank you very much.
Yep. Okay, thank you.
Thanks again. Yeah, I think we need to continue with next speaker. So thank you. And I will give floor to Norman Jakobsons. And please, could you stop your screen sharing? Well, I want to try to run.
Can I stop it or can you stop it? Because
no, probably you need to do it somehow.
oh my God, I don't see the option to stop sharing because there's only share option.
You can
Maybe I can start sharing it.
Maybe you can just take it over from me.
Possibly, yes. Yes, should work. And this one, right?
We can go back.
Did you manage to take over?
I think so. Hope you see our screen.
Because for me it still shows some green. Green.
It should be our screen.
Share.
Yeah, it's shared. It's already shared.
Screen share. They have to see it.
Okay, I think now it's your screen. Okay. Thank you. Thank you.
Thanks for your talk and moment.
Yes,
Let's start. Yeah.
Okay. Good day. My name is Norman Jakobsons. I am working from Latvia University and I am consulting sometimes about engineering and modeling. And today's I am not involved anyhow in any modeling related to C or Martin, yes, unfortunately. But therefore I will give more broader presentation. I will just talk about about my experience with open sourced software for modeling in some kind of real world problem situations. Maybe it's used when Vladislav invited me. That was the only thing which I can propose. So how can I get to next slide? Okay. I would like to briefly summarize approximately 20 years experience, and I will show some systems which can be modeled. And that doesn't mean I am then you can, perhaps one can do much more with OpenFOAM, but it at least can give some inspiration. Maybe that's all. I am not aiming on something very large with that presentation. First, what is OpenFOAM? I'm sorry about about my boring fast slides. Later on will be more with pictures. But when as the beginning definition, I just put some text. And OpenFOAM, it's kind of, I would like, by my words, it's a library written in C++ for numerical linear algebra, and with some kind of tensor analysis elements, and around that library is some solvers which are built around like computer fluid dynamics solver, which works as volume method. Yes. Finite volume method solver and also finite element method solvers exist, and all this package is first was commercial. Then since 2004 it went free and went open sourced, and it can be compiled on Linux, Unix, Windows. And this code is maintained by three companies, generally now three parties. One is OpenCFD Ltd, which is holding trademark. Code is open, but trademark is not, which with property. Then CFD Direct Ltd, which I think more development is on their side right now. And another branch is one of the developers for Yasax, this branch which is called OpenFOAM Extended. I like it the best because let's say when they split, it kept some new model, very interesting advanced models like diesel engine with cylinder with piston and with ignition. Everything was else with very impressive mesh morphing, and also rotating coordinates. Rotating mesh was first introduced in that version, but nowadays any of those versions can be used. What is basic traits which maybe we have to know when we start to use that? Calculations are driven by files. We have some files in directory tree, and it's almost normally no one uses graphics. Files can be modified. A solver is running. Solver is giving you some results, and if you modify those files, you can get solver react on that. And let's say if you say from that moment we will use another numerical schema for velocity discretization, then you can get next schema for velocity discretization. It will load next library, and it will work. It will continue to solve your problem. It has limited mesh generation force, block mesh, but those are really limited, and they are not really on so advanced as in commercial software. And for visualization, here is a ParaView tool, which is outside product, but also open sourced, is usually used. And generally, it can use unstructured mesh. They are one of the first, I think they are first, who used cells with arbitrary shapes. So you can use arbitrary polygons. Later on, it was incorporated in ANSYS software, for example. They took it from OpenFOAM as much as I know. They have multi-domain. Nowadays, they have multi-domain approach, and you can have different domains with different physics in domain. We can also use multiple fields and multiple physical systems in different parts of the model. Also, it's very good for parallel scale computing. It's very well parallelized. It's scaling good on lot of on systems with more cores, and you also in systems with more nodes. Yes, because core number of cores is limited. Here is also GPU solvers, and it's more important, of course, it's easy to modify code. When I started it, it was 2005, and it was I know some my friends, I know some group in Latvia University. We did some collaborations, and they worked on crystal growth research. And they did their work for crystal growth companies in Germany. Actually, for a certain time, I think 1/3 of they consulted those companies and they did research for them. And they needed some kind of software to go forward for numerical simulations. And here it was decided that it will be open sourced, and we started with OpenFOAM at the time because it was first introduced. It was recently open sourced, and it was recently, and it's looked as best as on the moment what can be. And this particular example, and then I started. It was very limited at the time, and I wrote some additional libraries and code for that. Let's say for buoyancy, I think my implementation of buoyancy is first correct implementation, because OpenFOAM itself got correctly it in, I think, 4 years later. I can be proud of that. But yes, and the example itself is, which I'm demonstrating you, it is crystal growth example, and this by so-called floating zone model, where we have silicon beam, which is heated by electromagnetical inductor. Then it melts, and the melt is in that middle, yes, in this neck. This melt is just falling down, and here below is melted zone, and below this melted zone, crystal is starting to grow. It's growing, and this the device is pulling it down, and that was first model. I spent almost 1 year, and it was very successful. And this is actually because here is buoyancy, here is temperature, and so on. But it's in general, it's correctly described phenomenon. Next example where it was used, it was here in Ventspils University. I worked for some time with in Ventspils University College, and our group attention, we did some we had some modeling group was focused on wind turbines at that time and we did some simulations related to vertical wind turbines, as you see on the pictures. First, such a turbine was first. This possibility was to do that correctly was introduced in commercial software in 2002 in ANSYS, I would like to say fluent. But already in some 2006, I think it's even earlier, there was some division in Canadian people, guys who introduced it in this extended open form version, which I mentioned. So everything was in place, and we started and we did some simulations. The main idea is that we have two mesh. One is staying still, another is rotating, and they are not non-conformal mesh. In this rotating mesh, we have turbine or propeller, whatever. Since this mesh is rotating, it's rotating with all solids inside, therefore boundary conditions are simple. But between those meshes another boundary which is opened and closed at every time step. And so this was already stock solver in development version, not stock. I don't know the software code, but anyway we compiled it and it worked. And we did try it on different blade configurations. And also there was some experimental checking of that, and finally we got pretty well fitted curves. So that was also one successful situation, and it can be also used. Such simulations can be used also in aviation, and can be used in some maritime things, because related to some kind of rotating machinery which is emerged in liquid or in liquid or air. Third is my example would be maybe related to more distant things. For years I was involved in some kind of collaboration with Paul Scherrer Institute in Switzerland, and what they did spallation they used spallation targets, protons. They used, which is in general it's proton beam, which hitting some kind of solid, some kind of matter, doesn't matter, solid or liquid, and neutron. And since this beam is very high, this beam is produced by high energy accelerator, and the energies of protons are very high, and as a result with small particles, neutrons coming out, and then those neutrons, which are called spallation neutrons, can be used for different things. Let's say for material science, for neutron tomography, cancer therapy, and so on. Their usual target type was solid target, which was composed on a number of rods filled with lead and cooled by water, which flows around them. And the proton beam is coming here on downstairs, where you see those arrows. So and neutrons are coming circularly outside, and some channels, and then they are taken from those channels. Specimens they put specimens close to this that target, and that target is very safe, but not 100%. Sometimes some bad things happens, like you see here, and those rods are some cracks appears on those rods. They are opening. The lead is it's molten because it's very high temperatures inside. It goes out and makes some and it's bad situation for safety. So they asked us to investigate numerically, and again we used OpenFOAM to analyze those structures. And also at that time, it was already past 2010. Here was some lot of work done even in stock OpenFOAM, related to liquid-solid interaction. So we did some modeling of liquid-solid interactions related to those growths. And these models have some models, and this model is more work on that is done by Sabine. She will present you, will do some open forms demonstrations later on during her doing her PhD thesis. And also in PSI, they built some kind of experimental system, which you see here, and we did some validation. And finally, it went well. Sabine got her doctoral degree. So that was the result. More recent things. Some multi-physics simulations, which I'm doing right now. I am implementing some dynamical extensions to OpenFOAM at the moment and this is related mainly on my work in Latvia University, the Institute of Physics. We are doing some kind of pumping systems, let's say basically pumps, for liquid metals. Let's say lithium, sodium. Lithium pumps can be used, for example, for production of batteries for your laptops and so on. In those factories, they use lithium pumps. Also, some of those pumps are used in so-called different branch of research and engineering for aero fusion project, which is so some of them are also just packed and given by aero fusion project. And the pump works like that. Then we have magnets here, which are connected to rotor. They are rotating, and those magnets are surrounded by pipe, which has a channel which has omega shape. And then that channel, some electrical field goes. Magnetical field induces electrical eddy currents, and electrical eddy currents interacts with that magnetical field, and finally we get some volumetrical force, and this volumetrical force be giving a pumping effect. So that is also something which is we looked at on COMSOL, we looked at on ANSYS, and all those models wasn't really what we wanted to get for the system. There was some problems with harmonics or and so on. So I just implemented it as C++ class inside the additional library added to OpenFOAM, and finally, and with that small trick, that small library, I was able to simulate those pumps. I can do that. And the accuracy is more or less acceptable. You see this is here, you see the productions, let's say 63 liters per second. So that is typical speeds, velocities pretty much actually. And here is some kind of 2.96 is experimental result and 2.86 is calculated. So they are pretty close anyway. And the difference can be explained because the pump is sectioned by mechanical aspects and some more additional tuning, additional code is needed in the model in order to get those currents flow through the sections. Because at the moment our model assumes those sections insulated, which is not reality. And finally, last one is something totally different. I think Monty Python had this without wording somehow. something totally different, yes. And this is related to OpenFOAM calculations, which are used in medicine, in pharmacy science, and we are modeling it right now in some project drug delivery systems. we are modeling how tablets of paracetamol, for example, how it dissolved during the time when there's some kind of flow is around it. And yes, also again, we are using extensively rotating coordinate systems and different turbulence models, large eddy simulations, time. This is not stationary, it's dynamical models. And when we are looking on results, then you can see those curves, which I think is pretty good. We can see this guy's different rotational speed for this pendulum, which you see for such a kind of machine which is mixing water, and the bottom here is tablet. And during this mixation, the tablet is dissolving. And the dissolution speed by this rotational speed, you see there those curves here, and you see that our prediction it's kind of we cannot measure it because it is we can measure just average. Therefore, experiment is straight line, and prediction is something which you see this due turbulence phenomenon. It's stochastic. It's not really constant, and it's pretty much in average fits the expectations. So this we do together with Riga Stradiņš University. So those are major, so few examples. I am not demonstrating here some kind of body, full over body, well, let's say, of our because I have such simulations, but those bodies usually are some kind of unmanned airplanes or something like that, which I cannot basically show to you. Sorry, it's not my choice. I cannot legally do it. But this can be done as well. So those are just for inspiration, few examples where OpenFOAM is successfully used, and it's for free. If someone says we have to pay much, no, but not really, you have to learn. And my final note is I would like to consider as viable alternative in some, not on all cases, but on some cases, the commercial solvers or package for both, even for both, for academic research and for more practical, even engineering, some kind of real world engineering. This software package can be used. The strength is that it's for free. We have excellent community support. Nowadays it's very simple to add new physics or more elaborate numerical models. It's easy to tailor this OpenFOAM for particular problems. And as I told at the beginning, it scales well with numerical. You can get rapidly results. You can scale to numerous cores and several nodes with those cores, KPC plus clusters, and you can do calculations of GPU. And it's for free. You don't have to pay for more CPUs, for example. The main drawbacks is then we have no advanced mesh generators. Post-processing is more or less organized well, but I would like to see better mesh generations for pre-processing. Somehow steep learning curve, and something which I didn't tell, it is constant change. Then as those OpenFOAM, as all open software evolves. People coming for open software community, people going from open community, and they do change, and new versions are coming, and that is okay because things have to evolve. But unfortunately, no one almost are interested in keeping compatibility with previous versions, and it's not problem if you are just using stock solvers. But if you are doing your own code base, which in my case, I have a lot of code, then you are experiencing frustration maybe and some problems with keeping up to date. New version can be incompatible with previous, and since it's incompatible with previous, nothing is works in new version. Okay, let's use this previous version, but for some time, after some time, this old version doesn't compile in modern Linux distribution, for example. And you are pressed to port all your code to the newer version. And sometimes it's like that, then this interface is replaced by new interface, and then they find that the new interface is not good enough and replace it back to the old. And that is something which maybe is a bit more stable in commercial world. But otherwise, I would like to suggest sometimes to have a look on open source package as well. Thank you very much for attention. Thanks a lot, and I would like to make the certificate of attendance and making the right talk in our workshop. So thank you very much. And any questions to Normans? Maybe some questions to auditory? No raised hands. No, I have. Yeah, so I actually have questions that you already answered on it. Your previous works of models like 2006, 2012, in this case, you are not able to just take it and run in newer software. Well, I updated everything.
Yeah.
I am regularly updating all my libraries, and I am making my code compatible with some software drifts, so it works on all versions practically, but it's take a lot of work to keep it that way.
And one more question about compatibility with high performance computing in GPU. I remember from previous time it was rather challenging to run it on clusters, but how it works now in your version?
This development version, which is extended version, yes, which is not really official version, but extended version, it has CUDA solvers inside. So the thing that you need a proper compiler, and you can put the cards, NVIDIA, and then it will work. I am not really, I don't know how it's about AMD. This another branch, which is OpenCL, for example. That is something which I don't know.
So thanks, and so it's a good example of free software, not like a SolidWorks is costly around 15,000 per license. So it's for just like a small enterprises. I think it's very complicated to pay with licenses, but OpenFOAM is more affordable.
Yes, sometimes yes, but of course you have to count inside your work as well. But,
yes.
Okay. Yes, so that's but people coming and asking to do some. Yes. Okay. Thank you very much.
Thank you, and we continue OpenFOAM topic. And next speaker Sabine Ottner. So I need to run your presentation. Yes. Yeah. So don't changing sharing. Should be fine. You are visible for online participants as well. So, yeah.
Okay. Thank you. And hello. Yes, my name is Sabine. At the moment, I work at Riga Technical University, and I will continue or keep promote OpenFOAM. Yeah. And what's what? Yes, as you already heard in the last presentation, OpenFOAM has different versions. And just for clarity, I will use for my next presentation, I will use latest version of one of OpenFOAM, which comes from OpenFOAM Foundation. Basically, OpenFOAM is developed for Linux systems, but nowadays it's also possible to run on Windows machines as well on Mac. And yeah, my demonstrations will be on Windows subsystem for Linux. If we install this on Windows machine, then we can also install OpenFOAM. And yes, and at the beginning, also, as it was mentioned previously, OpenFOAM is more or less text-based option, and there are a lot of cases, and these cases in general contains at least 3 directories. Yeah, my topic will be more technical comparing to previous. Yeah, therefore I will show you some specific things related to OpenFOAM. Yeah, and the first what we need to know is initial and boundary conditions. So we need to define these conditions for all fields, what we would like to analyze and calculate, for example, velocity or pressure. And if we work with turbulent problems, then also parameters which are related to turbulence, like kinetic energy or something like this. Next, there is a folder constant, which contains mesh and also description of physical properties and things related to turbulence model, if we have them. And the third typical what we have is called folder system, which contains numerical settings and control our calculations. As well, for the latest versions of OpenFOAM, this contains also a dictionary for mesh generation if we use built-in functions from OpenFOAM. And yes, now I will try to show you how we can do things in OpenFOAM. And I will start with geometry and mesh. Of course, there are also options to import already created mesh in some other softwares like ANSYS, but I will show you what we can do directly from OpenFOAM. And the simplest from geometrical point of view, if we have simple geometry, which we can build from blocks or from some cylindrical objects, which we can describe as curved edges, then we can use a tool from OpenFOAM, which is called block mesh. And I will show how to do this. Yeah, so this is my screen in Windows machine where I installed this VSL on Ubuntu. And before we go to mesh, I would like to show also that we have option to get a list of available examples or tutorials. If we install OpenFOAM, then we can move to this installation folder, and there are tutorials, and you can see different categories what we can look into and try to find something what is close or very similar to our problem, and then we can copy this to our folder and do some calculations. And here I will show you a cavity example, which is very beginning. All materials which introduce OpenFOAM start with this cavity example, and it's just it's a two-dimensional problem which describe flow field or flow in rectangular geometry. And yes, and as you can see here, we have these 3 folders which I mentioned previously. And yeah, so idea for this is that we go to system folder, then we click on this block mesh dictionary, and this is how looks our rectangular geometry. So with definite vertice, even if I said it's two-dimensional, we need to definite for all three coordinates. And yeah. Next, we definite blocks, which is as hex here. And in this place, we can say how a lot of cells we have in X and Y direction and only one in Z direction. And it's because we would like to solve it as a two-dimensional problem. After that, we should definite all boundaries, give specific names for all of them, and select corresponding type and also corresponding vertice. And here is one specific type. Front and back is definite as empty, and it actually means that this will be two-dimensional problem, and solver will not be calculating that direction any things, equations. Yeah, so this is the simplest way if we have simple geometry. And next will be example. Well, here when we have rectangular domain with cylinder, but for more complicated or realistic cases, it's good to use some parameters. And here we can see that we definite only one parameter diameter, which describe diameter of cylinder, and all other things related to geometry we definite as variables like radius or domain dimensions. Also, you can see that we are not using some constants, the same for vertices, but we use variables. And it allows us to change only one value at the beginning of this file, and we can obtain different case what to solve. And the same for layers. Also, there is used it's as a parametric way. And the same way, definite blocks. In this time, we need more than one. And this also is two-dimensional. You can see that we have only one cell in that direction. And for the curved edge, OpenFOAM has a specific option arc, which allows to use a curved boundary between two vertices. And next is the same, so we definite boundary, in this time inlet, outlet, and cylinder as a ball. And yeah, so this is how looks these simplest geometries. For more complicated options, there is Snappy Hex Mesh tool, which allows us to generate mesh by snapping it to the geometry and refining it locally. And there are three steps what we can do during this Snappy Hex Mesh tool. So we have some pre-built surface like STL file or something like this, which we can import in OpenFOAM, and then using Snappy Hex Mesh, we can get the corresponding mesh. And for this, I will show you motorbike example. So the same, we start with block mesh dictionary, and here we definite this computational domain, full domain, which will be as and after this computational domain, we select all things, these 3 steps. We can choose what we would like to do. Then we say what kind of surface mesh we will use, like here motorbike. Then we definite some refinement box, which will create smaller elements around this motorbike. And then follows list of different parameters what we can change. You see quite a lot of them, but the good thing is that there are comments which explain what each of these actually means and what we can do with these things. Yeah, I think I will not go into details, but yes, at the beginning you can just use default values, and then if need, then go forward to check what we can improve. And here will be shown how it looks. So this is ParaView, also open source software, freely available. And this is our computational domain. And then we will take a slice, and we can see that here is our motorbike, which we imported as a surface from outer sources. And we can create some specific regions with smaller elements, and the same around these walls as well. Yeah. So this is how looks our geometry and mesh. And now I will continue with this motorbike example to show what we need to do next when we have mesh. And next we should definite boundary and initial conditions. And this will be in the folder with name 0, because this is our initial calculation. And yeah, so here, this will be a model which use turbulence model. Therefore, we have not only velocity U, pressure P, but also K and omega, which is related to turbulence model. And similarly, as we could generate a mesh using parameters, we can also apply similar methodology to definite boundary conditions. So here is specific separate file initial conditions, which contains all numerical values related to our conditions. Similarly, we can definite boundary conditions, which will be repeated in each of these fields. Like here, for velocity, at the beginning, we say that we will use this initial condition file. We can definite this, for example, fixed inlet from outer file. And yeah, next few words about this boundary condition. So fixed values from mass, it means that it's a Dirichlet boundary condition, so it's specific value for inlet or any other velocity. In this time, it's lower wall, which will move with some constant value. And no slip is applied for walls, which means that the velocity on walls is 0. And in similar way, we need to definite these conditions for all names what we definite in our geometry and our mesh when we created. Yeah, and next you will see the same we apply for all parameters what we will calculate, or all fields what we will calculate. This is example for kinetic energy. The same, we need to specify boundary condition and value if we have such a value. Yeah. Let's move next. Now we have geometry, mesh, and boundary conditions. Next, we should say what we will solve, and this will be definite in constant folder. First of all, we see that we have some geometry here. Next, we think about momentum transport file, which specify what kind of turbulence model we will use. If we use, in this time, it's K omega SST, and turbulence on just means that we will take into account turbulence for our calculations. And we also need to specify physical properties. In this case, there is only one, it's kinetical viscosity, and viscosity model constant means that it's a Newtonian fluid. And the last things are systems folder, and here is this tells the code how to solve. You can see there's a list of files, but most important is this control dict. Actually, solver start is this file, and here we definite the solver name. This will be compressible fluid. We definite time interval and how often our results will be saved. As it was mentioned in previous lecture presentation, OpenFOAM allows us to work in parallel. So in this, we can definite, for example, that we will use 6 cores or 6 processes. We can choose methods, how to divide our computational domain in 6 parts. We can also definite some additional terms, what we would like to solve, for example, force coefficient, and so on. And then in schemes, we definite how to convert partial differential equations into a system of linear equations. So here we are talking about discretization schemes. And for example, in this case, we use Upwing scheme, but there are, of course, several already available schemes what we can use. And the last one is SIS solution, which dictates how to solve these large matrix, and we specify solver for each parameter what we have. And in this example, as it's steady state case, we use simple solver to calculate pressure and velocity current coping. And yeah, we can definite some other things as well here. And yes, and then the last, when we definite all things related to our case, then the last step is running our calculations. For new versions of OpenFOAM, all of these cases contains this all run script, which actually already definite step by step what we need to do. In the first time, we don't need to change here nothing, but what we can see here is that we take this geometry, then we create block mesh, then we divide in cores or do this decomposition, as Snappy XMesh typically need a lot of resources, therefore we do this there, and then hit enter, and all processes start working and solve. Number 1. We will solve 1. Yeah. This is how it looks when case is running. One notation that not so quickly. For demonstration, I just skip several minutes, but typically it's not so fast, especially if we are running some real life problems, then this will take hours, days, or weeks, or something like this. And therefore, it's very good if we can do these calculations on HPC cluster. And yeah, what happens when these calculations stop? Then we have all log files, which we can check. If there will be some problems, some errors, we can find here in these files. We can read and try to find what is the problem. If no, then we will obtain a result. Like this file contains all results step by step, including residuals, which is important for simulations, including some false questions and so on. Yeah, and as we used in this example 6 cores, then we have here for each of them available data. And also we can get in other formats output data for post-processing as well. And the last is our results for the last time step. As this is a steady state case, then we are not interested in all time steps, but just the last one. And as you saw here, it looks very strange, but it's because the format is binary. It's take less memory, but we could save these results also in ASCII format, and it allows us to read these data from each of these files. And the last or one additional post-processing option is to create VTK files, which allows us to look on obtained results in graphical way, and this will be shown here. The same open form, and we should find this VTK file which we created, then click on apply, and then we can do analysis of our results. Here I will show only a very simple case that I take the same slice and I look on flow field around this motorbike. But there are more options. We can create vectors around some objects. We can apply some thresholds, or a lot of different other things that we can do here. And I guess that's all from my side. Here are a few points, but yeah, I think I can stop here. So thank you.
Thanks a lot. Focus and constant. What also for it was like the old schools, Total Commander or Midnight Commander, binary files and text files. But finally, anyway, you get the visual results, and you can just cut it in slices and rotate it again to just use visual results, not data. But finally, anyway, use numerical data, like the numbers, to analyze it.
Yeah, we can do both. We can look on these graphical things using, I don't know, Python or something like this. We can create graphs, and we can look also on these fields using ParaView, and this allows us to get more complicated analysis for analyzed problem.
Yeah, thank you. So we will conclude the room. No. Thank you for inviting to talk. You'd like to see the principles. Yeah. Okay. Yeah, so we'll continue with our next speaker, Marina Konjuhova. I hope Marina is here.
Yes, I will try to share my presentation.
Could you be a bit louder?
Yes, I will try to louder. Okay.
Okay, we see your screen.
Okay.
And so, yeah, so let's start. So Marina Konjuhova, another way of modeling data, like using console. So floor is yours. I switch my camera and switch my microphone, not to disturb him.
Thank you, Vladislav. Hello, everyone, and thank you for the invitation. My name is Marina, and I work at Places.
Marina, maybe a bit louder, so I don't know why, but your voice is not so clear.
Now, do you hear me?
I hear, Marina?
I try to light it with both.
Okay, yes, I think it's okay, yes, sorry.
So I'm from the Institute of Solid State Physics and Ventspils International Radio Astronomy Center at Ventspils University of Applied Science. And today I will present our work on the numerical modeling of hydrogen compression using the liquid piston process. This study is based on multiphysics simulations performed in Premsel multiple. As all you know, hydrogen is one of the most abundant elements on Earth, and it's widely seen as a key energy carrier for the clean energy transition. And it's especially important for sectors that are difficult to electrify. For example, heavy industry, long-distance transport, and maritime applications. Hydrogen also enables energy storage from renewable sources like wind or solar power, helping to balance their intermittent nature. For this reason, hydrogen is strongly aligned with the European Union's goal of achieving climate neutrality by 2050. And it's expected to play a significant role in future marine and maritime energy systems. However, the use of hydrogen at sea comes with specific challenges, particularly in terms of storage and compression, which require safe, efficient, and cost-reliable compression technologies. On this picture, you can see a typical hydrogen compression infrastructure from production to high pressure storage. And hydrogen can either be delivered to the site or produced also locally using electrolysis and often powered by renewable energy sources as wind or solar. And in this case, we usually refer to green hydrogen, which does not produce CO2 during production. After production, hydrogen needs to be compressed from low or medium pressures to the high pressure levels and required for storage and distribution. This compression stage is key part of the overall infrastructure. In marine and maritime systems, the same concept applies, but of course, additional requirements appear. Equipment needs to be compact, reliable, and suitable for offshore conditions. This slide shows the concept of a hydraulic hydrogen compression system based on the liquid piston principle. This compression concept has been developed by our research group at Ventspils University of Applied Sciences and is protected by several national and European patents. In this system, hydrogen is compressed in several stages using a hydraulic working fluid, in our case it is silicone oil, which acts as a liquid piston. The use of liquid piston allows smooth and well-controlled compression. The system includes primary and secondary compression stages, high pressure storage, and set of valves that control both gas and fluid flow. One of the main advantages of this approach is a relatively small number of moving parts. Also low noise levels and improved thermal management. And in general, this system can reach pressure of up to 100 megapascals. That making it suitable for port infrastructure and offshore platforms. This slide summarizes conventional mechanical hydrogen compression technologies such as reciprocating piston, linear, and diaphragm compressors. And all technologies are well established and widely used in stationary and automotive applications. They can achieve high compression pressures and have proven performance. However, when we move to marine and offshore environments, some of their limitations become more pronounced. Mechanical compressors typically involve many moving parts, which leads to higher maintenance requirements as well as increased vibration and noise. And as a result, conventional mechanical compressors are not always, let's say, the optimal solution for marine hydrogen infrastructure. And this motivates the search for alternative compression concepts that can offer a little bit simpler design. Here you can see the alternative solution. And in this liquid piston concept, in this approach, hydrogen is compressed by a liquid column that acts as a piston inside a fixed volume chamber. And this allows the compression process to be smooth and also well controlled, while avoiding many of the mechanical issues found in conventional compressors. An important feature of the liquid piston is its thermal behavior. The liquid absorbed heat generated during the compression and can be cooled more effectively. And as a result, the overall compression efficiency can increase from typical value of 17% to over 85%. To better understand how hydrogen behaves during compression process, we use a numerical model. This allows us to study how pressure and temperature change during the compression process and to design a more safer and more efficient system. One of the main advantages of simulation is that the different operating conditions can be tested without physical experiments. We can change compression speed, the geometry of the chamber, or working fluid, which saves the time and cost and helps improve system performance. Here you can see the model. It has height of 145 millimeters and a diameter of 100 millimeters, and the total volume of little bit more than 1 liter. Hydrogen is located in the upper part of the chamber, while oil acts as a working fluid below. As the oil rises, the hydrogen is compressed. The simulation includes heat transfer between the hydrogen, the oil, chamber walls, and the surrounding environment. And this multiphysics approach allows us to analyze temperature variation, heat losses, and pressure development during the compression cycle. Here you can see liquid piston compression chamber that was implemented in console software. We used, as I talked previously, a multiphysics approach that combines compressible gas flow for hydrogen, incompressible flow for the liquid piston, and steady heat transfer. The model includes all the main parts of the system: the hydrogen region, the liquid piston, and of course steel chamber walls. During compression, the gas and liquid are compressed together, and heat transfer between the hydrogen working fluid and the chamber also is taken into account. This allows us to analyze how pressure and temperature change during the compression cycle. In console, implementation begins with model parameterization. All all key parameters are defined in the global definitions section. This includes key geometric values such as piston stroke, cross-section area, and compression chamber height, as well as initial conditions. Defining these values as global parameters mean that the same values are used consistently throughout the model in geometry, in physical interfaces, and study signals. The next one slide shows that we set the initial conditions using global variables. This includes the initial pressure, the initial gas, volume, the mass of hydrogen in the compression chamber, and also compression time. The key point here is that the gas volume and density are described by time-dependent expressions. This allows us to represent the compression process continuously rather than a series of discrete steps. And in this way, the thermodynamic behavior of hydrogen is directly related to the geometry and motion of the fluid. In the next step, we determine environmental conditions, such as temperature and pressure. This allows us to account for heat exchange between the chamber walls and the surrounding environment. This allows the model to include realistic heat losses, which is important when analyzing temperature change during a hydrogen compression process. Model geometry. Here you can see the geometry of our model. We use a 2D axisymmetric model, which is well suited for this type of cylindrical system. The chamber is divided into three regions: hydrogen domain, steel chamber, and liquid piston. And this configuration is sufficient for realistically studying compression and heat transfer effects. Besides building the model directly in CAMSOL software, the geometry can also be imported, for example, from the SolidWorks. This slide shows how material properties are defined in CAMSOL model. Material parameters are defined for all regions. We define key physical properties such as thermal conductivity, heat capacity, viscosity, and density, which directly affect both heat transfer and fluid flow during compression. And these properties are used consistently across all associated physical interfaces. You can use materials already available in CAMSOL software, or also it's possible to enter them manually. This slide shows the physical properties of the material used in the model. For hydrogen, we use standard thermodynamic properties such as molar mass, heat capacity, and heat capacity ratio. These parameters are necessary to describe the change in temperature and pressure during compression. The liquid piston is characterized by thermal conductivity, density, viscosity, and heat capacity. This slide shows how chamber geometry and piston motion are implemented in CAMSOL. The fluid piston motion is achieved by moving the boundaries using the deformed geometry feature, rather than moving the entire mesh. This approach allows for smooth changes in gas volume during compression, while maintaining mesh stability and avoiding mesh rebuilding at each time step. And as a result, we can accurately track the compression process with good numerical stability and reasonable computational costs. This slide shows how heat transfer is considered in the COMSOL model. For all major parts of the system, hydrogen gas, liquid piston, and chamber walls, during the compression, heat is generated in the gas and partially absorbed by our liquid piston. In the model, volumetric heat sources are defined within the liquid regions, and appropriate thermal boundary conditions are applied to the chamber walls. And this allows for the description of both heat generation within the system and heat loss to the environment. With this setup, COMSOL solves the coupled problem of fluid flow and heat transfer. In COMSOL, hydrogen is described as a creeping and compressible flow. Due to these low velocities, inertial effects can be neglected without loss of accuracy. At the same time, the compressibility of the gas is fully preserved. Since pressure change during compression are the key physical effects we want to account for. The isosymmetric formulation further simplifies the problem while maintaining the correct flow physics. And taken together, this approach provides a stable and physically consistent description of hydrogen behavior during the compression stroke. The motion of a liquid piston is implemented in the COMSOL model in the next way. The liquid piston is not modeled as a mechanical component that I have already mentioned, but this component moving inside instinct, its motion is driven through a moving boundary at a specific velocity. This boundary represents the interface between the liquid and gas and moves upward during compression. And as a result, the gas volume continuously decreases, making the compression process controllable and physically consistent. A significant advantage of this approach is its numerical stability. Since the mesh itself does not move or deform significantly, remeshing is not required during the compression cycle. Here you can see the mesh in the COMSOL. The finite element mesh is generated for the entire computational domain, including the hydrogen region, the liquid piston, and the chamber walls. To ensure sufficient accuracy, the mesh is locally refined near the solid-liquid interface, as this is where strong velocity and temperature gradients are expected. Specifically, boundary layers elements are applied along the all chamber walls and in the region of the moving liquid piston. This mesh design allows for the correct consideration of both flow and heat transfer effects without excessively increasing the overall number of elements. And as a result, this achieves a good balance between numerical accuracy and computational efficiency for simulating transient compression. The model uses a triangular finite element mesh. In the hydrogen region, the mesh is relatively coarse, as the flow is smooth and the velocity are low. But at the same time, the mesh is locally refined near the interfaces between the hydrogen, the liquid piston, and the steel walls. These regions are crucial for resolving heat transfer and boundary effects, so boundary layers elements are used there. As the liquid piston moves upward, the hydrogen volume decreases step by step. The mesh smoothly deforms with this movement, following the change in gas volume without restructuring. And in total, the mesh contains approximately 21,000 elements providing a good compromise between numerical accuracy and computational cost for unsteady state simulation. We used the time-dependent study. The simulation type corresponds to the specified compression duration, and in our model, the longest compression was 20 seconds, and the faster 0.5 seconds. All physical processes are solved in a fully coupled way. This includes the flow of compressed hydrogen, the movement of liquid piston through the deformed geometry, and heat transfer in gas, liquid, and chamber walls. This model allows us to track continuous change in pressure and temperature during the compression process. After running the model, we obtain results and can review and analyze obtained data at each calculation step. The average temperature is calculated separately for each region: the hydrogen gas, the liquid piston, and the steel walls of the chamber. This allows us to clearly separate the thermal behavior. By examining average values rather than local peaks, we can trace general heating trends during the compression process. This analysis is particularly useful for understanding the role of liquid piston as a thermal buffer and for assessing the efficiency of heat transfer to the chamber walls. And this information also is important for optimizing the compression rate and geometry of the chamber. Once the calculations are completed, we can calculate the average temperature in each domain. You can see the temperature, for example, at 5, 10, and 20 seconds. We can see also the average temperature results for any time period. This slide shows the temperature distribution inside the compression chamber at different points of time. On this slide, the results are presented for 3 characteristic times: 3, 10, and 20 seconds. During the early stages of compression, the temperature increase is primarily concentrated in the hydrogen region as the gas is compressed by the liquid piston. As the process continues, heat is gradually transferred to the liquid piston and then to the steel walls of the chamber. And this becomes more notable after 10 and 20 seconds. And also these graphs clearly illustrate the transient thermal behavior of the system and show how the liquid piston and chamber walls contribute to the redistribution and removal of heat during the compression. Thus, the process occurring during a single compression stroke was simulated using the presented model with compression stroke time varying from 0.5 to 20 seconds. The initial hydrogen and oil temperatures were set at 300 Kelvin, and the compression ratio was equal to 5. The calculation results for 2 scenarios are shown here, and one with an initial gas pressure 3 megapascals and another one with 20 megapascals. Figure 16 shows the temperature field distribution within the cylindrical chamber. The figure shows the variation of the gas temperature over a 20-second stroke at time interval 0, 10, 15, and 20 seconds. And these results highlight the significant heating effect within the gas as compression progresses, especially at high pressure. Figure 15 shows the temperature change over time during a single compression stroke for hydrogen or working fluid and chamber walls at initial pressure of 20 megapascals and compression ratio 5. That was a lot of time, maybe about results. The results of the compression process simulation allow us to estimate the temperature increase of the gas and the working fluid, in our case, is liquid oil, and therefore determine the energy expended during the compression process. On these figures, you can see how the average hydrogen temperature and oil temperature changed during one compression stroke, depending on the initial pressure in case of 20 and 20, 15, 10, and 3 megapascals. Here you can see the temperature increase predetermined in the model corresponds to the energy expended in the hydraulic compression process of hydrogen and stored in the hydrogen, oil, and cylinder body in walls. The amount of energy stored in the compressed hydrogen, oil, and steel is determined using an equation based on the laws of thermodynamics. Here you can see energy distribution at initial pressure of 3 and 20 megapascals. And this diagram shows that most of the energy is concentrated in hydrogen during the compression. But of course, under real conditions, hydrogen and oil mix and exchange heat. When mixed, the gas cools and the oil heats up, resulting in a more balanced overall temperature regime within the chamber. This slide shows temperature change for varying compression stroke duration at initial pressures 3, 10, 15, and 20. The next one slide, it shows the relationship between the power required for compression and the duration of the compression stroke for 4 different initial pressures. Results link. Figure 24 shows the increase in hydrogen temperature at different compression chamber heights. We have changed height of the chamber. The results here really illustrate how chamber geometry and compression duration affects the thermal behavior of hydrogen during the compression. On these figures, you can see that the chamber size has a significant effect on temperature change at low volume, but eventually stabilized. And these trends suggest that while large chamber volume contribute to greater heat release, their effect diminishes at higher volumes, indicating an upper temperature limit beyond which increasing volume has little effect on temperature increase. I will skip this for this because it will be a conclusion. And conclusions. In conclusion, it should be noted that numerical results demonstrate that liquid piston compression provide effective thermal management during the hydrogen compression process. And chamber geometry significantly influence both temperature and energy consumption, making the optimization necessary. Due to their compact design and favorable thermal characteristics, liquid piston hydrogen compressors are well suited for use in the marine and offshore hydrogen industry. So thank you for attention. Are there any questions?
Thanks a lot. Any questions, comments? Yes, we have question from Norman Jacobson. Norman, can you come, please? Down.
Excuse me, did I get correct? So then your compression cycle is about 20 seconds. Is it like that?
We can change. We can start from 0.5 until 20. Yes, but on as a result, you saw that we compare how this compression time depends on pressure.
Okay, half a second is faster and 20 is slower. I'm just wondering about and how high, what is the height of your, how long it is your cylinder?
145 millimeters. It's very small, 1 liter.
So this velocity is well below 1 meter per second in any case, average. So, but then my question is, you are using boundary finite elements. Boundary finite elements is usually used for boundary layer to reveal boundary layers. Physicist Frankl introduced them in the previous century, beginning of previous century. And do you think this is really needed to use boundary layer elements in the case when your velocities are so low? Because this can be avoided.
It's a discussable questions, and because we have no mixing between our domains. Yes, it's separately hydrogen and liquid piston. And maybe I needed more that when we developed this model, our local Latvian Process Analysis and Research Center helped to us to create this model, because it's very tricky in this in total to model a compression process. And they decided, they help us to create, and they help this question, and they offer.
Okay, that was their idea, to put boundary elements on the NEARTS walls.
I will fix this, and maybe we are planning to continue our modeling, so maybe we will something to change and improve our model.
Yes, I would like to suggest to do the same modeling without boundary elements and check what is the difference. I don't know, maybe it has something else which I missing, which I didn't see at the moment now, but my suggestion is to do without them and see, did you have different solution? Thank you very much.
Thank you very much. Yes, I will be really see your recommendations.
Thank you. Thank you, Norman, for comments. Yeah, actually, in this case, we have different kind of speeds, because minimum speed is 0.1 second. So, and compression speed would be several, even 10 meters per second, even more. But yeah, so we will try to investigate this as well. Thanks, Marina. Any other questions? No. Yes, thank you for all listeners and participants and speakers as well.
Okay, I think it's time to start our second day session. So welcome to Mark's first technical workshop regarding physical modeling and blue and green transitions in Baltic Sea and beyond. Today our focus will be on industry insights and some practical results from physical modeling and how we can do some kind of product and how we can use this. And our first speaker in this morning, Laura Agapova, Latvijas Flotte, is it correct? No. LVR Flotte, with her talk, Maritime Innovation Examples from LVR Flotte, Fleet Modernization and Collaboration Models. So I give floor to Laura. Yes, so come here and
Thank you.
yes, so you can start, yes.
Okay. Good morning, those who are present and those who are watching us from a distance. My name is Laura Hoga. I am Development and Communications Project Manager at LVR Flotte. And I wanted to thank you for inviting us to this workshop and for inviting us to the project, Marta. We have joined very recently, only in December, in the status of interested stakeholder, which we definitely are, as we support maritime innovations and maritime technology, since maritime technology excellence, since as a technical service provider, we are dependent on maritime technology on a daily basis. I will be honest to say that I myself, I do not have any competency in deep tech tools or physical modeling. But what I am is fond of connecting the different fields, different disciplines, as learning the unknown widens our perspective. And I hope that you will find interesting our take on maritime innovation from the point of view of a service provider who works in the port daily. So I will speak about our fleet modernization and our development project. So, but before that, I'll briefly introduce you to our company. So we are a technical service provider for ports. We are a subsidiary company of the Port of Riga Authority. We were established to carry out these technical functions related to ports infrastructure management. So a lot of times our work is invisible, but without it, port cannot operate in a safe manner and be open to navigation all year round. So realizing this responsibility upon us, our mission is thus to provide high quality service, so thereby contributing to the competitiveness of the Port of Riga and also to other ports in Latvia as well. We work both onshore and in the waterways of the port with 8 service lines in our portfolio. So hydrographic surveys, that's a full set of services starting from the data collection, analysis, processing, and creating final measurement plans tailored to clients' needs. Icebreaking, this is a strategic function, and actually this is a historic moment. As I left to Ventspils yesterday, our icebreaker Varma went into service in the Gulf of Riga. So yes, this is a matter of navigation safety, and we're very proud of Varma's work. Maintenance of aids to navigation, another core competency of ours. We service floating and shore-based aids to navigation, and also provide monitoring for navigation aids. Pilot transfer, our job is to make sure that pilots reach vessels and then get back safely to the pilot base station. This service is offered 24/7. Oil spills response, from preventive measures to operational response. And while our vessels are not used for our functions, we offer charter opportunities for long or short term. On the land side, we provide infrastructure management. This might appear as a single item in this list, but actually it's a comprehensive set of services, and it requires coordination among different divisions. So we take care of the railroad network, of roads, territories, snow clearance, waste management, security systems. So it's a comprehensive set of services. All of these services we provide at the Port of Riga, but as I mentioned in the mission statement, that we work in other ports of Latvia as well. So with only 4 of our services: hydrography, vessel charter, maintenance, aids to navigation, and to a certain extent also oil spills response. Now we provide we deliver our services with our fleet, which consists of technical fleet and fleet of vessels. Those are our main assets. It's a small but capable and efficient fleet enough to service our ports. We work with an icebreaker, multifunctional vessels, pilot boats, hydrographic vessel, and drone. You would see Otter. And if we speak about technical solutions, I wanted to bring your attention to Drone Otter, and I will speak about it more in a minute as well. But this drone has completely changed the approach how we deliver hydrographic surveys. It has increased our mobility to reach also those places that were previously inaccessible. So you see on this map, this is our operational area. In inland waters, we deliver hydrographic surveys, and we have been with that as well in Nasva and Klaipėda. Along the shoreline, we provide mostly maintenance approach to navigation, monitoring approach to navigation, and also engage in vessel charter deals with other ports. Taking into consideration our operational area and our professional expertise, in long term, this is how we see ourselves, that our role would be this platform through which technical resources and technical competencies among ports could be exchanged. So we support, we promote a closer collaboration of ports in the technical sense, as that is the matter of resource efficiency. But now about our development projects and maritime innovation. So innovation is one of the pillars of our strategy, and we always try to find a way on how to become more efficient. And in the areas where we can not innovate ourselves, we give this opportunity to others to test their ideas or products in the real maritime environment. The only principle is that those projects which we undertake or in which we collaborate with, they must bring value to either our resource efficiency or would be beneficial to the Latvian port system. So first that I want to mention is the most important project of 2025 of last year. We have introduced, we completed a major fleet modernization project with the support from EU military mobility funds. And we have acquired a new multifunctional ice-class vessel with dual-use capabilities. This vessel strengthens our operational capacity in the range of the services that we already provide, and also it expands the tasks that we can perform. The vessel is built on shoalbuster design, and it is suited to a variety of tasks in various maritime environments, which supports our strategy. Currently, Laura is involved in ice management. So since she has ice class, she does ice breaking. And as a matter of fact, today Laura is in Ventspils, not for the ice breaking, but for helping out our colleagues in Ventspils with aids to navigation. They must be lifted out during the winter conditions. So you might see Laura today if you're at the port. During the technical planning, we consulted closely with our clients, with stakeholders, and also with partners in the defense sector to ensure that the ship would meet the needs of our partners at ports and at the military sector. So the result is this, and a bit about the technicalities. So the vessel has a spacious deck. This was a requirement from the defense partners, as this vessel in the military aspect could serve as a supply vessel for military needs. But also it is important for us, since we now are able to place 4 buoys on the deck. the vessel has equipment suitable for transferring heavy objects. It has waterfall winch, hydraulic deck ring with capacity of 12 tons outside the vessel, but 19 on the deck area. A-frame that is meant for leveling works, tugger winch, also universal bracket for research equipment, also if necessary. And yes, an equipment for emergency assistance, latest navigation programs. So this vessel can also serve as a platform for further innovation. Another thing, this is our first hybrid propulsion vessel. It is able to run on battery power for, officially it says 1, but we tested in up to 2 hours. And of course, this is an important step towards reaching environmental goals. But for us as well, it means the resource efficiency. Now, when we there were various aspects that we considered when choosing the batteries. So one of the things is that we chose batteries because they can be charged using the existing infrastructure, so you don't have to build something anew. It was important for us to keep the vessel dimensions unchanged, but the batteries take space. So this is the amount of space that we could devote for battery room. But when thinking also about our further fleet modernization, for example, in the plans of modernizing our pilot boats, these are the conditions that we consider. There are quite a few alternative fuel possibilities, but we must ensure high speed. We must ensure the ability to work in ice conditions. We must take into consideration resource availability and many other aspects. So, and if you have something to add about this, then I welcome the discussion afterwards. So yes. Now, Laura, she supports all of our services, as I mentioned, especially the icebreaking operations. But with this vessel, we can also develop new service lines. For example, leveling works or support for dredging projects. The vessel is fit for transfer of personnel and equipment, as I mentioned, in the supply, as a supply vessel for military needs. Emergency technical assistance, and actually this was the first task of vessel Laura. She helped another vessel in distress. And also the direction in which we look at is offshore infrastructure servicing, wind farm servicing. And this is not actually, we had an example just in December. We collaborated with EOLOS as their subcontractor for installing for 2 smart buoys in the Elvin project. So Elvin project has chosen 2 sites in Latvian and Estonian waters. And so before starting the project, they must do their research. So I'm not really into smart buoys. I cannot comment on that matter, but our job was to make sure that these smart buoys are placed in their right locations. And since we have the technical capability and also a team, experienced team, navigation team, so we managed this project, and now these smart buoys are located in their rightful places. And we assured ourselves that we can participate in Growth FRBs. And so since we will speak about wind later today, I also wanted to let you know that such technical support is available in Latvia. Now back to Otter. Our drone Otter that I mentioned before, these are not new news. Otter has been in our fleet since 2022. It was the first of this type of drone in the Baltic states. We have worked already for 4 years with Otter, but it is not about introducing some trendy technology in the fleet, but it's a matter of efficiency again. So efficiency is the main principle in any project that we undertake. And yes, now we are able to offer this service also to the clients that previously could not even have this service, also, as it would be very difficult to reach inland waters with our vessels. So now we do not plan to retire our hydrographic vessels, not at all, but this just adds a multimodality aspect. We continue our work with hydrographic vessel in the port of Riga for regular measurements, and we service other clients in Latvia with the drone. So that is more attractive to the client, as that reduces costs for our, as you can see. Yes, that has really increased our client base. There are advantages to each type of vessel. Of course, you can use drone, it's convenient, but in the meantime, when the weather conditions aren't that good, then we can employ a vessel. So to continue on, we collaborate also with R&D community. We participate in research projects. For example, this project that I really like is the collaboration with a local scientist who came up with the idea on how to reduce emissions from diesel engines. As a fleet operator, we understand that not all of the fleets can switch to alternative fuels or do retrofitting. It is a matter of course, of the finance, or for example, what to do with those vessels who must operate in ice conditions. So we found that this could be an interesting. This could be an interesting project, and so during this project, a prototype planned and technology was developed and tested on board our vessel, Liiva. Of course, it is not supposed to be on the vessel Liiva, as Liiva does not produce that much gas emissions. Someone else's.
Inga Kalniņa, could you please speak to microphone?
Overpress atsūtīja rēķinu par papildu darbiem.
Inga Kalniņa, could you please switch your microphone?
1790, tas ir autoru uzraudzība 2 dienu, restīvi viņi sauc autoru uzraudzību. Es jau līgai vairāk kārtīgi es teicu, tas ir tas, ko viņi stāsta mūsu sarunās par papildu darbi, papildu cenu. Viņiem nebija jātaisa marketi, viņi neierēķināja sākotnēji lietām, bet šobrīd mēs viņiem grafam taisīt marketus, attiecīgi viņi ierēķina. Pieslēdz mikrofonu. Aizrunā.
Fine, thank you. So sorry for interruption. We can continue.
Yes, thank you. No problem. This happens. That is very common. So back to the project with on Liiva. So this technology is not supposed to be on a vessel Liiva. There are types of vessels that have shown interest already about this technology. I think Stena ferries, and also it can be used for plants on the ground for the emissions as well. We will continue collaboration with this project, and we're currently looking for funding programs for the next phase of this project. So it could be an alternative to scrubber systems. Of course, our long-term partner has been Of course, our long-term partner has been as well Latvian Institute of Aquatic Ecology. So we also provide this technical support for their research activities at the sea. This is very new. Just a few days ago or last week, a pilot project was approved for funding. So in this project, we collaborate with Baltic partners in the topics of decarbonization of pilot boat fleet. The leading partner is Tallinn University of Technology. I don't know if anyone from Tallinn is present, but we are excited to begin this project. So each partner will have will develop their idea on how to decarbonize their pilot boat fleet. Our idea is to develop an integrated monitoring system so that we could, through that monitoring system, also optimize our engine performance, improve maintenance strategies, encourage fuel efficient navigation practices, as a lot of times this depends on the human factor. We collaborate also across industries, our partner LMT, with our partner LMT. So we are two completely different companies, but we have an innovation open mindset, and we both recognize the 5G potential in maritime industry. Connectivity for us is important, not just because 5G is something it's trendy, but because when we provide hydrographic measurements that produce so large volumes of data, and 5G allows for faster data exchange. So this could improve our service provision. Also, the same applies to dredging projects. Those also produce large volumes of data. So we explore different options how to make that data transfer from the ship to the shore faster and in real time. So we have been part of many 5G initiatives. Also, very recently, we participated in the demonstration day during the technology forum, and together with our partners from LMT, Submerged Baltic, Bayron, Riga Technical University, Spark Technologies, each partner demonstrated their own digital solutions, or for example, their products. So from drones to edge computing solutions and autonomous drone deployments. So let's allow to serve as a mothership for the drones. In the innovation projects, it is very important to have strong partners by your side. So during all of our work, we have build this innovation ecosystem around us. Now, this is not an exhaustive list of all our partners, there are only a few of them, but it is important, and that's the key to developing sustainable solutions, because there are many great ideas that are left on the shelf as a prototypes and do not see actually the market. And in order to get past that, you must have your community that supports and validates your ideas so that they can be introduced in the industry. And our collaborative approach also extends across borders. In last summer, we concluded a memorandum of understanding between Latvian and German partners to promote cooperation in digital innovation and maritime technology. So this partnership brings together both ports, Port of Hamburg, Port of Riga, both fleets, ourselves and Flotte Hamburg. We make friends with other fleets abroad as well. The objective of this memorandum of understanding is to work together to find practical digital solutions on the challenges that both ports face. For example, us, together with Flotte Hamburg, We work on solutions for large-scale data exchange, as I mentioned in the example with the large volumes of data produced in hydrographic measurements, and also solutions for monitoring system of the technical condition of ships for predator maintenance. So that was a brief overview of what our company does, and I hope that gave you a worthwhile insight or a perspective of someone who works at the port daily. And the message that I want to leave you with is that we provide technical services for safe and efficient use of the port infrastructure. We focus on innovation and partnership. And if this overview has sparked any questions, I welcome the discussion. So please come and talk to me. I welcome the conversation. Now, I thank you for your attention and wish you a fruitful day. Thank you.
Give it some questions as well. Looks, maybe colleagues online. If you're brave enough to just give me a couple minutes for creating questions though. Again, so thank you for coming. So Tuesday we have two Lauras from Riga, requesting conventional. Yeah, so it's nice to see, and it's very interesting because I think you have no contacts with Penfolds University, so probably it's a good time to establish also some kind of research and developing with Penfolds, and I think we can talk about and discuss it a bit later. Yeah, so no questions. Wait a second. I would like to hear your
diploma. A first diploma from Penfolds University. Thank you so much.
Yes. So thanks again, Laura. And we are going to our next speaker. And so Jēkabs Piedītis, both come here, University of Latvia, and he installed wind solar powered energy systems for autonomous coastal and offshore infrastructure. So this actually, Laura, your talk was very beautiful start of the day, because the next talks are somehow related to your mentioned activities, and we try to find out how developments could be connected with Baltic Sea and using your fleets to use services what you provided together with the new technologies as well. So Jēkabs, please come and try the presentation. Yeah, thank you so much. Yeah. Good
morning, everyone. It's a pleasure and an honor to be here today. So quick introduction about myself. I am Jēkabs Piedītis, a bachelor's level student of physics at the University of Latvia. I also work as a physics teacher at the Rīgas Natālijas Delziņas Vidus School, and I'm also an aspiring researcher working at the Numerical Modeling Institute of University of Latvia. And what I'd like to share with you all today is the research that I've done at the Institute with my colleagues for the past year or so. Mostly all of us still undergrad students, we've been working on assessing the potential for autonomous infrastructure. Infrastructure that works purely on the basis of wind power and solar power with the assistance of battery storage. We're focusing mostly on communication towers in particular, though any infrastructure, these principles would apply to any sort of infrastructure. So given this topic's connection and relevance to this seminar, I hope that some of our findings are of some value, or at least spark some thoughts. So without further ado, quickly the sort of structure of this presentation. I'd firstly like to speak on the objectives of this project, then the importance for coastal and offshore applications, then most importantly, the results, and finish off with conclusions and further areas of research, the plans for the future. So the primary aims of this project are as follows. Firstly, during the first stages of the project, The initial goal was assessing whether such infrastructure is even feasible in the first place. If it was found to be either technically too impractical or too expensive or too unreliable, then I would probably not be here today. So assessing the potential and the feasibility was the first important goal. After that, the next was mapping the potential of such infrastructure across all of Latvia, and in later stages across all of Baltics, in order to find the most suitable places for the development of such infrastructure. Because even with such a relatively small area as the Baltics are, the differences can be quite significant, not just comparing the coastal and offshore regions to the inland ones, but also within these categories. This is also a time to admit that most of the research was primarily done for inland applications at first, as the prototype for the power is located inland. However, for the purposes of this presentation, I'll try as much as possible to bring an offshore and coastal perspective to all of this. So once we had a clear indication that all of these towers are feasible, the next step was to look at ways to optimize them. So if you want the system to be as effective as possible, then we would have to look at, for example, what kind of combination of solar, wind, and battery would give the most efficient and the most cost-effective outcome. What the differences for this most optimal system would be across various places in the Baltics. How large should the battery bank be, and just a flurry of similar questions that have to be answered in terms of optimization. Another important part of the project was identifying the shortcomings, the various periods of outages, when they occur, how long they are, how severe they can be, and even if the outages are relatively rare, then understanding the exact conditions under which these outages happen is crucial for improving the systems and also showing what kinds of applications it can support, which leads to my next aim, determining what power usage profiles could such systems be useful for, and hence what applications could sensibly be run on them. Of course, we're talking about relatively low to medium power infrastructure. We're not talking about off-grid factories or data centers or anything like that. Mostly medium power infrastructure such as communication towers, monitoring equipment, certain categories of measurement devices, and similar distributed systems for which such setup could be practical. And finally, it's also worth mentioning that this is not merely a hypothetical project, so not something that is merely from the passion of some students. All the calculations, the modeling, and the configurations have actually been used to build a functioning tower in real life, which means that all of this analysis has also practical grounding, not just theoretical. And although the tower is set to run, have the wind turbine spinning and the solar panels working only within the next month or so, it has been built in real life so far. So moving on, for the importance in particular for the offshore and coastal applications. These regions, I'm sure all of you know better than I do, come with their own sets of difficulties. Infrastructure in these regions is quite sparse. Grid access can be limited or non-existent, and weather conditions are harsh enough that any system of this sort not only has to be self-sufficient in terms of energy, but also be physically robust. And the further from land you go, the more difficult everything becomes. There is also the less pleasant, but unfortunately unavoidable factor that, given the current political landscape being as turbulent as it is, the importance of a two-layer safety net is more important than ever. Unfortunately, this is no longer some theoretical, hypothetical doomsday scenario, but rather this deliberate interference, jamming, GPS spoofing and other forms of electronic interference are real risks, and the Baltic Sea in particular has seen plenty of such activity, which highlights the increased need for such infrastructure. So the results section, I'll organize it by starting off talking about the inland point, the one that we have already built, then move on to a more broad perspective across all of Latvia, and then focus on a coastal point. So this inland point is located in the central southern part of Latvia, near the city of Dobele. For a very important piece of context about the further slides and calculations that are done, this current tower configuration contains a 5 kilowatt turbine at a height of 56 meters, solar panels with a total power of 18 kilowatts, and batteries at a total capacity of 25.6 kilowatt hours, which of course doesn't mean much if we don't know the power consumption. The most important part to scale it against is the power consumption, which we found that of these sorts of communication towers, we used an analogous one in a similar location. We found the average to be 2.1 kilowatts, slightly more during winter and slightly less during the summer. And using 30-year data from the new European Wind Atlas, as well as ERA5, and simulating a battery which every hour takes a certain amount of energy from the solar powers and turbines, and uses up a certain amount of energy from this power consumption. We modeled the way that this tower works. So finally getting into the real results, one of the beautiful things about a hybrid energy system is the fact that during the months in which the solar power generation is relatively lower, the winter months, the wind power is slightly higher, which helps significantly to ensure the autonomy of such infrastructure year-round. It is important to mention that during the winter months, the generation is still lower. The wind during these months is not as high as the solar power during the summer, though especially with us placing the solar panels at an angle which is most efficient, in particular for the winter months at a 60-degree angle, the situation is made to be slightly better for autonomy in the winter months as well. When modeling the outage percentages for this current configuration in this inland point of the tower, we found that the average across the entire year would be roughly 6%, essentially non-existent during the summer months. However, the real problematic areas would be the winter months, in which it ranges anywhere from 15 to 18 to 19% during these months. Which is of course not the most ideal outage percentage. So this is something that would certainly have to be improved, and therefore we also ran an optimization algorithm to find the most ideal, the most cost, and therefore we also ran a 99% uptime for this inland point, and we found that for this power consumption profile with an average of 2.1 kilowatts, ideally, most efficiently, we would use solar power of roughly 37 kilowatts. Wind power would not change so much. A 6 kilowatt turbine would do the job, and a battery capacity of 54 kilowatt hours would be sufficient. And when it comes to cost, we also calculated the cost using the current energy system, current panels, inverter, turbine, and batteries used in the project, which were deemed the best by our project partners. And we found that the cost of these power systems not including the labor to set it all up, and also not including various minor installation components. At an inlet point such as this would be roughly 45,000 euros. Of course, that's by all means significant money, but it's also important to note that renewable energy systems are decreasing in price and time, and also given that something like this is very low maintenance and can potentially run even for a couple of decades. This is, I believe, to be quite a worthwhile product. And the wonderful part about it all is that this is for an inland point, quite deep into Latvia, for a more windy area, and for an area with a slightly higher solar potential as well, such as this beautiful city of Ventspils or any coastal region. The results are even much better, as we had mapped during the early stages of the project. The coastal and the offshore area has, I'd say, roughly 1 to 1.5 times more to 2 times more total power generation potential than, for example, a point that is deeper inland, than, for example, the valleys of Gauja, the river Gauja, which were found to be of much lower potential. Therefore, this sort of infrastructure could be particularly strong in the coastal and offshore areas. When we had mapped the outage percentage using, again, the same system that we're using in the inland location, using the same power consumption profile, we found that in the coastal and offshore regions, the power outage would be of this system would be 2.5 to 4% compared to, again, locations that are deeper inland, which reach up to 10%, up to a 10% outage percentage, which further shows how much better such systems could work near the sea. So finally, moving on for results at a coastal point, I chose a point at the very coast, roughly between Ventspils and Liepāja, near Pāvilosta, in the center of this western part of Latvia. We found that the average power outage time is more than 2 times lower. Again, we have the same problem that during the winter months it is higher. However, in total throughout the year, it would be only about 2.6%. And also, again, trying to find the most efficient setup that reaches a 99% uptime, the needs and the cost would also be much lower. Solar power would merely have to be about 25 kilowatts. Wind power is roughly the same. These same 5 to 6 kilowatts would do, and a battery capacity of 47 kilowatt hours, which would create a total cost, a significantly lower total cost, and just a slightly higher cost than at this current location of 38,000. And such a trend of the price being much lower is visible all throughout Latvia. This project is still currently ongoing, so we're working on adding more points and adding a proper interpolation throughout all of it. However, in a map like this, with the points that we have, it is very visible that at a coastal, at an offshore, at an offshore point, this system would be much cheaper and work better. So to conclude, I think the most important takeaway is the fact that the idea of an autonomous renewably powered communication tower or anything of a similar power consumption profile is not only technically feasible, but also genuinely promising for the future. And even with its limitations, even with a limited size turbine at a limited height and then undersized battery bank, the system works decently well. And if we found that the system works decently well at the inland point in slightly, I guess you could say, suboptimal at a suboptimal location, we can infer that the system would work even better at a coastal point, for example. Which brings me also to the second major conclusion, that location matters more than anything else. The difference between central Latvia and the western coast is quite enormous. Coastal regions benefit very significantly from a higher wind potential, which in turn drastically decreases total outage times and the total cost for ensuring these low outage times. And the third and maybe slightly less important conclusion is that autonomous towers of this sort are incredibly important, especially with our current geopolitical situation, due to this signal interference being increasingly common. Therefore, improving resilience in these coastal and offshore regions is crucial. And as for future research, there are several ways forward. The most important one would be that after this tower is fully set up, after the turbines starts running and the power starts being generated, we would have to compare these real life data to our simulations. It's one thing that everything works well in our computer, but validating all this data against the actual model, real weather, real power systems, and the real hardware quirks that always come with this sort of project will certainly help refine the methodology and make the system better and more robust. Another direction would be expanding this research for infrastructure of different consumption profiles. Communication towers, which we focused on, are just one example. However, as I previously mentioned, any monitoring stations, navigational beacons, offshore sensors, coastal radar equipment, and other similar sorts of low to medium power infrastructure all have different energy needs, and quantifying exactly what those needs are and at what times and what is the most optimal way of ensuring the proper working of all this infrastructure is something that I think would be extremely valuable. And there's also room to explore, let's say, more advanced forms of optimization, making sure that the system works well also for near future weather forecasts, also integrating small scale backup systems such as hydrogen storage. That was another point of research during this entire project. And of course, also extending this model across the entire Baltic region and even to the island territories as well. It would also give a broader understanding of where these systems could have the most potential and where they could be the most impactful. So thank you very much for your attention. There's
Let's do sorry.
That was the comment. When I signed up the graphs, I think looks like to record something called that. Then we just get carried away.
Unfortunately.
Well, I think that's one of the most mistakes. Kind of how to and here's the progress where we actually.
I'll work on it, I promise. It's coming.
Actually, it's coming to my side. So we are in Ventspils University and Ventspils International Radioastronomy Center. And one of our activity is study of black holes. They're like the most darkest objects in the world, in the universe. And actually, so maybe it's not now, but in part of future, it's an enormous source. It will be used in very compact as well. But it will be not in 100 years or maybe even more with time. But it's part of future. Thanks again. And there are some questions from my side. This solar panels, 25 kilowatts, how big are it? 25 kilometers.
Sorry, the area? That is, for context, you could think that one of these solar panels, which were used for the project, is 450 watts. Therefore, it could be roughly 50 of these panels. How large a panel is
meters, around 50 square meters. It's very yeah, so good. So
it is certainly a significant area.
Yeah, and it's again a nice result of coastal areas is most promising for these autonomous systems. But probably if you go far away from a food, that it's additional expenses for deploying towers and so on. Also on a platform, that's something like
for sure, yeah.
We have additional price, but it's probably not need some big towers and not so big solar panels. Yeah. Yeah, thanks a lot. And yes, we definitely were experimenting with by products at what the type of I could put the
in the project, we found that the typical the typical axis, I'm currently forgetting, I think it's the horizontal one now, which is used for most wind turbines, was also the best one for this application.
Yeah, thanks a lot. There you go. Another for the two is able to increase the component costs.
That would be another potential line of research. During this project, we have not done any research on that. However, that certainly has a lot of potential, and that would have to be looked at.
Actually, in my presentation about linear generators, I have a couple of slides about the rate turbines. So I will explain it now. Okay, so yes. So thank you for coming, and you also thank you so much for your talk. Thank you. So thanks again, and any activity from participants online. So if you have any questions, raise your hands, make notes in chat, or just turn on your microphones. But now I continue with our next speaker. Uldis, are you here? Yes, I see you.
Hi.
Good morning. So I think I can give floor to you, please. So I have your presentation, but do you mind to share your screen, or I need to run it?
I think I will share the screen. It's probably save both a bit of time, but we have plenty of time. And
we save some time.
And also, yeah, and also maybe it's I will share the entire screen, so it will be a little bit. So then I will put it in full screen mode, and maybe.
No, yes, perfect. We see your screen. We see you.
Yeah, maybe you don't screen some logos, yeah.
We see everything. Yes, thanks. So sure, you can start. Yeah, I turn my microphone off.
Yeah. Okay. Thank you very much. Thank you for inviting to this Marine Technologies workshop. And my name is Uldis Bedfers. I'm director of the Institute of Numerical Modeling in the University of Latvia. My background is physics, but mostly our group is doing numerical modeling of almost everything. Yeah, but one of things is oceanography, and particularly operational oceanography. And if you do some marine modeling, then from this you can develop some products. And one of such technologies which addresses coastal zone of Latvia and port areas, including port aquatories, is a information system Hivasport. I will show what is it, what's behind it, and what's new in it. This system is developed by the help of Copernicus Marine Service. There is user engagement projects running occasionally. The main thing is that Europe has quite good Copernicus services, both atmosphere service, marine service, and other services. but the results are quite complicated and require some special skills. In our case, we use them as boundary conditions. Okay, so the idea of this Hivasport product or service is quite simple. By the nesting of models, we can blend together what's happening in the sea with what's happening inland. For instance, in river estuaries, in port aquatories, and so on, you see these small places, for instance, here Riga harbor, where we have marine model outside and some riverine model inside. And also in the modeling community, sometimes these two people don't speak to each other, groups of people, of course, or groups of researchers. People who are doing ocean never do rivers or lakes or estuaries or whatever. Anyway, if we go for the summary of this system, then recently by my time scale means few years ago, in 2024, 2025, we developed two new downstream services in our Hivasport system, well, of course in Baltic Sea, in Latvian waters. We developed this blending or seamless transition between the sea and inland waters. And second thing, we did something for the sediment transport in coastal zone. Yeah, and in this system, we also have some observations by port authorities and third parties, for instance, Latvian Environmental, Geological and Meteorology Center. And here is the link, probably, if you wish, but you can access it through Water.lv. It's quite easy to find. Okay, let's see what technologies are behind the scene of this online system. We take two Copernicus marine service products, which are called Baltic Physics and Baltic Waves. These are operational forecast products, and we took just boundary conditions from them. So the outer points and time series, of course. When we run hydrodynamics in our modeling domain, it's Hiram Booth model in operational setup by University of Latvia. So it's run on our premises on, we can call it supercomputer or computing cluster of my institute. And we are also a member of Hiram Booth modeling consortia, and hopefully this Hiram Booth model probably will be open source. It's in transition at the moment. Whatever is the model itself, the main problem always is to implement, set up, and customize the model. We have did it for parts of Baltic Sea, except Botnian Sea, Gulf of Bothnia, and yeah, that's it. Sea and some Danish waters, but Botnian Sea, we have 7 levels of Bothnia and yeah, that's it. It means and some Danish waters, but from nautical mile in far sea down to tens of meters for inner ports where berthing places and maybe some shore areas is very important. Then for waves, we use in-house model for port aquatories and do not calculate waves outside, just use a Copernicus product. And these days we are developing artificial intelligence, or better, neural operator model for operational calculation of wave field, because strange as it can be, modeling of wave fields nowadays is more computationally expensive as computation of hydrodynamics, mostly because of very fine meshes which are needed for discretization of computational domains. Yeah, okay, and for sediments, we use Hiram Boost model. There are appropriate models for the sea in our setup. And in-house sediment transport models for the coastal area where we calculate longshore sediment transport in wave breaking zone. Of course, setup of Hiram Boost model doesn't allow to account for wave breaking, which is sometimes happening in depths of tens of centimeters. So it's about models behind it, and now let's go for the services. One thing is seamless transition between the seas and the inner ports. As you see in photograph, the sea weather can be quite different behind the wave breakers. You see this wavy conditions outside and quite calm sea inside. And if you go for navigation, when captains of ships encounter a rough change of sea state at the sea gates of the harbors. And this is a part where most of the traditional models fail to provide a good solution, because you model either the sea and put the boundary conditions at the sea gates, or you are modeling the river or estuary or port aquatoria, whatever, and put your boundary conditions in again at the same sea gates. And so we try to use this nesting, which is available in Hiram Boost model, to overcome this problem. And in our model, when this transition between the open seas and the inner port is quite seamless. For waves, currents, sea level, sea temperature, salinity, and wind is not in our model, but it's very important for the navigational purposes and other port operation purposes. And if there are some observations, of course, it can be meteorological stations or wave rider buoys, as it in Liepāja Harbor, and I think also in Skulte Harbor, then they also can be included. So let's see how it looks like. For instance, I will show some examples on Liepāja Harbor. Liepāja Harbor is quite interesting because it has 3 gates: Northern Gate, Main Navigation Gate, and Central Gate. Here you see the wave field by the color scheme. You see how the waves go inside the aquatoria, and you see that there is no disruption, and more or less it's smoothly these models represent the wave field. Despite that outside we have Copernicus product, and inside our wave in-house wave model. And you also see that wave field in the harbor may be quite unpredictable if you just go by common sense without modeling. And it's quite good to have 2 days ahead forecast for planning your berthing operation or some movement of your vessels inside the harbor aquatoria. If it's a port like Liepāja, where huge territories are exposed to waves. You see what they have built internal wave breakers and jetties just to protect berthing areas from sea waves. Yeah, and here of course you have northern winds, and it's not the most dangerous situation. So let's go further. Here is example of salinity and currents. It's also somehow quite interesting because in so-called commercial channel there is connection between the sea and Liepāja Lake, which is also modeled as a reservoir, is quite good, but it's shallow lake. But we model hydrodynamics also there in Bārta River. You see the plume of brackish freshwater coming out of the lake in this situation. There are some westerly wind situations when seawater can intrude also in the lake, but it's not the case in this modeling scenario. You see also that here is some transit flow in probably the water is entering the northern gates and flowing out through central gate and this one. By the points here are shown some specific points of interest or observation stations where some data can be also shown as graphs. Let's go further. Here is an example of a graph at the main navigation gate. At this station, Liepāja Harbor has installed a wave rider buoy, and you see by dots in this graph the wave height, measured wave height and wave direction, and by continuous line you see the model results, which also somehow helps for validation if you go to study this for some scientific reasons. Yeah, and model performs quite well, but I think it's not a story I'm going to tell you today. The next graph is some example of water level. Water level is also important, especially for smaller ports where low water levels may limit the passage of the ships in the sea entrance channel, and also loading of the ship, how much you can load in it, if it's because at lower water levels you operate in more shallow conditions. And here again are two water gauges. This is in the lake. As you see, the lake experience quite smooth and stable water levels with slow change. And then there is fluctuating seawater level, which is lower in this case. As you see also here, the water is mostly flowing out of the lake. But here, previous to current time, there have been some time moments when water is flown in opposite direction. Therefore, you see salinity, which is non-zero in the navigation channel. Yeah, and the solid line is hintcast and prediction of the water level by the mathematical model, operational mathematical model. So let's go to the second service, which is new in this Kivasport system. We are the nice words is supporting of coastal management and marine conservation in Latvia. And the things we are so showing in the system are also listed as seabed disturbance indicators in the coastal zone if you go for a different classification of processes. But actually we do two things. We included the operational map of sediment flux density just to see where and how is potential sediment flux in the Baltic Sea. And another thing, we put some mesh of points along the coast of Latvia for calculation of longshore sediment transport in multiple locations. Yeah, and then we can see how this longshore sediment transport can be compared with climatic values like seasonal and annual cumulative values. How this season compares to the 20 or 30 year long climate of sediment transport. Okay, I will show you how it looks. Again, we have plenty of these points or regions. There are some pictograms on the screen. For instance, we can take Ventspils Harbor. It's somewhere. And when we have this sediment, longshore sediment transport cross sections, which are also somehow named. On one of the fields which can be shown in the open sea is the density of the sediment flux, with some units which seem strange, but it's the only meaningful units if we go for sediment transport. And of course, more sediment transport is closer to the coast, where there is a wave action, the typical mechanism how the sediments are moved in the open seas, but waves mobilize the sediments, and then the currents carry the mobilized sediments away somewhere. Yeah. Typically in longshore direction, because the currents cannot cross the sea-land interface, and so they are always parallel to the coast. If we go for cross-shore sediment transport, for instance, taking this profile, it's a vertical. I'm sorry, it's cross-shore profile which is perpendicular to the coastline, and we calculate the longshore sediment transport. The longshore sediment transport is the feature which dominates the sandy coasts, and Latvia has sandy coasts, of course. And this sort of phenomena occur because part of the wave energy, especially in wave breaking zone where this energy dissipates the most, is transported to the so-called longshore current. So this wave energy does two things. Breaking waves create suspension of sand, and part of this wave energy transforms to the current. It's a dangerous sort of currents which carry away swimmers as well. And this current carry away along the coast also the sediment. Yeah, and for each of these cross-shore points, in our case, we took sediment load at Majuri, we draw 4 lines. We have pre-calculated the climatic sediment transport in eastwards direction and in northwards direction. You see that most of the sediment is carried in towards Riga at this Majuri point. And then we calculate the sediment load which happened during the last year. I prepared this screenshot in April-May 2025, and in that time we can see that this sediment transport in eastward direction was smaller than sediment, or of the same magnitude as sediment transport in westward direction. And we also could see that the total sediment transport was smaller as a climatic value. And if you remember last year, when there was a quite strong storm in 30 of I think it was 30 of July 2024 when there was a big damage in Jurmala, where also the farmers complained about loss of crops in Zemgale region, and it was heavy thunderstorms, rain, and northern wind. This profile was exposed to this northern wind blow in this direction, so the sediment moves to westward, and it's this very big event. And one can see that all events of sediment transport, most of the sediment transport occurs in the event, like here, and so on. Yeah, okay, let's go further. It's the same for in the seasonal. Time scale and season in this case is 3 months from the current day, and there again in April 2024 there was a small storm which can be shown here. And yeah, one can see how we are doing in the climatic context in different places. Of course, for ports, it's also important because there is possible to relate this information with siltation in the sea entrance channel, which is one of big issues also in your port city. So what else? Yeah, thank you for attention. I think I also saved some time for questions. You can access the system at this address, WaterLV Hivasport, or you can go for WaterLV to see some other free products by our institute. I don't know why people advertise free products, but I'm doing it at this moment. And if you want to learn what we are doing, you can visit our webpage or write me an email. And I also, well, last but not least, I also invite you to one conference in Riga, August this year, Artificial Intelligence for Inland Water, Atmosphere and Ocean, if you are interested. So that's it. Thank you.
Thanks a lot. Thank you for your talk. It was very interesting and interesting products that you're delivering. And I understand this is already online in WaterLV. Everyone can use it, right?
Yeah, it's online, and I will stop sharing. This system is online, I think, for some 5 or 6 years. We have also some user community. It is free, and it is free mainly because our main profit is from developing. To put in place some subscription system where you get 5, 10, 20 or 2,000 euro per user, it's not easy. And it is also harmful for your public relations.
Sure. So yeah, but thanks a lot. So it's interesting. I have a couple of questions. Maybe any from audience on online, and so also no hands. But about prediction. So this system can predict up to 2 days, as I understand correctly.
More precisely, for 54 hours, but it depends.
But it also counts some kind of extreme events like storms or snow melting and floods, or it's not included, or it's not possible.
Yeah, everything of it is included, but in the system there are parameters which are listed. There are marine parameters mainly, and from atmosphere parameters there are just 2. It's wind speed and direction, and air temperature. And if we talk about sea ice, I think it's oceanographic parameter. There is quite sophisticated data flows. We use numerical weather forecasts plus Copernicus boundary conditions and Copernicus wave field in OpenSea, and then we run our models. And of course, we use operational weather forecasts, operational Copernicus products, and operational wave fields have this future component of, say, 60 hours.
And for inland waters, it's the same models or it's something different?
Yeah, it's we run a nested Hiram Booth model.
Yeah, thank you.
Okay, what I'm showing, everything comes out from our models. We use this atmosphere and Copernicus far sea points as a forcing. So it means 4 times a day in our computational center, we rerun these models for the next 54 hours. So it's routine task, which is maybe not that typical for university. But this system, once it's set up, it runs. You need not to put much effort.
And covering it's cover Baltic Sea or just Latvia, Estonia?
The model, the model area covers most of the Baltic Sea, but the visualization area, which is or this front page you see, covers a limited part of Latvian coastal area and limited number of ports. And we have 8 ports included in our system. And only for 3 largest ports, we have also hydrodynamic model inside. It's for Liepāja. Obviously, you saw it, yeah? For Ventspils and for Riga. In our hydrodynamic models, we run also Liepāja Lake, Ķīšezers Lake, Jugla Lake in Riga. And also Daugava, starting from Riga hydropower plant, and Lielupe River starting at upstream point near highway to Ventspils Bridge. But these parts are not included in visualization because it requires some effort in data transfer.
Thank you. Maybe one more curious question about sand and seabed movements. Is it constant? So in your plots, it's like a average per year, some cubic meters. I just worrying about Ventspils. So is it all time same direction and like a sand moving?
No. At every moment it's in different direction, but most of sediment movement occurs during strong events. It's if you are looking for operational things. If you are looking climatically, then of course these lines become smooth. Because in climatic means every winter day there is chance of a storm.
Yeah. Thanks a lot. And so if no questions, so thank you again, and we go to our next speaker. So yeah, in our program, Andris Krauklis, Latvia University of Life Sciences and Technologies, and he will make a talk about modeling hydrothermal aging and degradation of polymers. Sorry for again. That's the presentation. No. Я думаю, что morning. Well, yeah. Floor is yours. Thank you so much.
Yeah, can you hear me well?
Is it working? Yeah,
Perfect. So my name is Andres Krauplis, and I'm an associate professor at Latvian University of Life Science and Technologies. And there are a bit of people. No worries at all. So yeah, and basically, so what I'm going to talk about today is the hydrothermal aging and degradation of polymers and polymer composites as in relation to that. And how do we model this using physical methodologies, so physical modeling and multi-scale modeling approaches. And then without further ado, let's look into the technology that we have to offer here. So let's start with the big picture. So the introduction is that, let's say, polymers are everywhere in our modern life. So they're also environmentally, they can be exposed to water and humid air environments, especially in our climate. It's also the temperatures and let's say the cold and so on. So there are really a lot of issues that come with the environment. And we are also looking into the aging of polymers with the effect of temperature and the effect of, let's say, humidity, the presence of water, the acidity, and so on. So all the environmental factors that can be there and affect the material. Looking at different polymers can be quite different from one to other, and we'll explain in which sense that is and how that can come into hand when analyzing the behavior. And also that means, however, that while the materials can differ, it means that the aging mechanisms can differ also quite severely. So all of that has to be assessed individually. And in case of polymer composites, it's not only the polymer, but it also is a reinforcement material, which is typically, let's say, if we're talking fiber reinforced polymer composites, that can be a glass fiber or a carbon fiber, or more recently, natural fibers and basalt. And also there's the third part, the secret ingredient, the sizing of the fibers, and then therefore also the sizing rich interface, which can also affect the aging of other constituents. So let's take a look how we can, let's say, work with this very complex interaction. And for, let's say, to break down this complex, let's say, process of aging and all underlying processes, we try to build a multi-scale modular approach. So to break down a very complex issue into smaller pieces and to try to analyze mechanistically how each of them is working. So let's look into molecular mechanisms, kinetics, and interconnectedness of the constituents. But also, why do we need that? So in the modern times, let's say, it's especially important to understand the lifetime of a material. So how long does a material survive and can be put into use? For example, we're looking into towers like wind turbine or towers. That is something which currently is an issue in Europe in a way that with the recycling, because in real life, these turbines can live much longer than they're actually commissioned before. So because we are over, let's say, we don't want to risk anything. That's very smart, but that means that also we lose 10 years of real use of a turbine, for example, in the practice conditions. And the problem at the moment is also what to do with the with the material that is waste, because composite recycling technology is still being developed very, very eagerly, but there are a lot of problems still. So lifetime. So now, as you know, life cycle assessments, that's a hot word. Life cycle assessment and the cost analysis, LCA, LCC. And we want to have a method reliably to predict the lifetime of polymers and polymer composite materials. And in order to do so, we propose the development and advancement of the modular modeling framework, which is presented here. And also we look into one case example, which is, so I'll go a bit into more detail, QSPR methodology that we developed to looking in a case of a PLA polymer, environmental agent of that. So lifetime prediction. As I said, the process is very complex and can be broken down. So the interaction between the polymer and the environment can be broken down into many smaller parts and parameters. So environmental factors, temperature, moisture, pH, mechanical loads. There's a lot of inherent processes, physical aging, hydrolysis for some, post-curing, internal stress relaxation. And we have to look also on different scales. So it is something happening on the molecular scale, the micro. Then it is the engineering properties that being affected, the macro properties that we're looking, and then there's the bridge connecting it all together, the mesoscale. So also, in some cases, we want the material to degrade. So for example, if it is something bio, like a compostable material, so we also have to know the composition criteria in that case. So we have to look at a two-edged sword. So in some cases, structural materials, wind turbines, we want them to stay healthy as long as they want, or as they can. So it's a safety criteria we take into account in the modeling. We have biodegradable, biocompostable cups or something which have liner made of polymer. We want it to be able to degrade it fairly quickly. So that's a favorable decomposition criteria. Now, let's take a look closely into the composite polymer composites. So we have three constituents matrix, the polymer, respectively, reinforcement, that's a fiber, and the interface region. And then when each of these components is intact, in contact with the environment, there's plenty of various sub-processes which go on. So let's start. Mostly we concentrate on the polymers today. So I will talk about the processes which work and affect the polymer. And also a bit of, I will show the interconnectedness with the other modules, but let's look into that in more detail. First of all, let's say we look environmental issue. We have a polymer which is immersed in water, or we have a rain, let's say wind turbine standing there and the rain is dripping and affecting the polymer matrix. So water starts to diffuse into the polymer. Initially we have, let's say, a dry state. Although here we have a true water content, so nothing in reality is completely dry, right? So we have a equilibrium with the air, humidity of the air. And then it reaches certain equilibrium, the saturation level. So the material, the polymer is completely saturated. In this case, it's a very common, the most common epoxy polymer used in the market, the Digiba epoxy thermoset. And so we can see it can take up about 3.5% water. And we can model this very efficiently, usually use a Fickian law, so Fick's law, and typically for polymers it works quite well. There are some exceptions, of course, but Fick's law is usually the standard way. So let's take a look. If we have polymers of a dry state, then the saturated state with water, and then we want to see if we re-dry to the initial state, is there any change, for example, or does it, so is it the water content the only parameter that affects the property of a polymer, or something else is there? When we look into composites, so polymer composites also, it can be even more complicated that we have not a blue saturated line, but with time we can see that, for example, it can also drop. And I will explain why is that. Now, I mentioned that polymers can be different, and in terms of material-environment interactions, this is important because the hydrophobicity of plastics is let's say, the property that is interesting to us. And in some cases, polymers can uptake a lot of water and be swollen and can be affected by hydrolysis, such as nylons, polyamides and PLA. Although on the other case of the spectra, for example, polypropylene or polyethylene, they are very hydrophobic, so they don't uptake a lot of water at all. Next, when we have water inside the material, it can cause the plasticization, and also it can be inside, let's say, inside between the polymer chains and starts to swell, so increasing volume. And in some cases, some polymers are affected also by chemical degradation, so hydrolysis change station. When the water is inside, it can also leach out the chemicals inside the plastic, and that is basically the water diffusion, but the diffusion out. So it's the same principle. We can use the same Fick's law, but with the other direction. And the degradation and all this plasticization, swelling, and change station effects, they also affect the mechanical properties and of the material. So let's take a look again at this example of the most typical Digiba epoxy resin. For example, here we have in one of our papers, we identified the weak spots where the mechanism happens of the degradation of the epoxy network. So here's a bit of an explanation what happens. For example, there's cross-linking, which affects the glass transition temperature of the epoxy. And so when we redry the material to the initial state, we cannot regain all of the properties that we had before the aging, even if we have the same content of the water. Then also, as we know, very typically, this is important for in art conservation, for example. So epoxy is a glue and used in art also as a, let's say, to protect the piece of art. And with time, this particular epoxy and most of epoxies, they age and they become more yellowish or grayish, so they change their color. And the reason for that in this case is a carbonyl formation. So the oxidation that happens even with quite low temperatures just in outside air. So it's not by sun, it's not photo-oxidation, this is thermal oxidation. So to kind of sum it up for this material, this is just an example for one material, but every material is different, as I mentioned. So it can be a lot of mechanisms: plasticization, hydrolytic excision, thermal oxidation, in this case, changing the color, leaching, thermo-oxidative cross-linking. We can check all of that, let's say, with different methods as we go, so infrared analysis or so some spectroscopic methods. We can also test mechanically and see how the properties of a polymer, let's say in a wet and re-dry state are changing, both statically and in fatigue. Then in terms of hygroscopic swelling, as I mentioned, so the water that is inside between the chains starts to swell the polymer. And this one is quite easily predictable, so we can use simple modeling tools for this one physically. It's almost like a thermal expansion, but it's just hydrothermal expansion. And this one can be done both analytically and with finite elements. With polymers, this is a linear correlation. For composite, it is orientation of the fiber dependent. But let's get to the more interesting part. So in this case, let's say how can we predict the property of a polymer if we don't have any testing facilities with us? So here we offer the QSPR methodology. So it's originally not ours. It's based on it's QSPR and QSAR. QSAR methodology is quantitative structure activity relationship. QSPR quantitative structure property relationships is something, is a method that has been developed mainly for drug discovery, so for medicinal pharmaceuticals. But It has been taken over also in the polymers and the material sector by DuPont. And the idea is that we have any chemical structure, and we can use the mathematical graph theory to analyze the Lewis diagram. So the graph theory allows us to break down any structure into a number of parameters, in this case, atomic and bond indices. So it's a 4-parameter. And with the mathematical operations we have, so these 4 parameters as simple valence and 0 and first order indices, also called structural parameters. And the interesting part is that these parameters, they are unique for any chemical. So let's say if you have one polymer or another polymer, they will never be the same. So that's what gives it a fingerprint. And by using this combination of these 4 parameters, we are able to predict the properties by using an extensive data that is available to us. And now with the modern techniques, especially with the data science and machine learning and so on, this method has been given a new life in a way. So also another way to look into the prediction of properties of wet, for example, so saturated polymers, and also the effect of temperature, if we have the viscoelastic effect. So for example, we have a material creeping over time. The principle of time temperature superposition has been known for years. And it means that for polymers, for materials which have viscoelastic behavior, we can superimpose the effect of time and the effect of temperature. So they, let's say, creep at higher temperatures, they creep faster. However, what we have shown also that the effect of water present in the polymer can also be superimposed on that. So we have, for example, the blue is a dry master curve, the red is the wet, the saturated polymer master curve. And the interesting part is that these 2 master curves can be superimposed themselves by using, as we call it, dry to wet shift factor, which corresponds between the glass transition temperatures of the dry and saturated states. So if you are interested in this, for example, what can this do? Is that's the graph on the right, for example, in one paper that we wrote together with our colleagues in Hamburg, is that it allows you to predict how long a polymer will survive under given water content, temperature, and load, mechanical load. And you can use it as a surface basically to predict, let's say, at 20 megapascal, it will survive for this many years. At 40 megapascals, it will be less, and it will be this many years. So that's kind of how it can be useful. For some polymers, as I mentioned, for example, this epoxy that we looked at, it doesn't go hydrolysis. But there are many polymers that are used in our daily lives, such as polyamides, nylons, for example, or PLA, or one of the more common, let's say, first biopolymer in a way that is used a lot in 3D printing. They undergo hydrolysis with water, and it means that the reaction is typically non-reversible. So the properties can be lost over time until the material breaks down. So the hydrolysis can be predicted with such modeling ways, for example, the time-dependent decrease. However, let's look also in the case study, interestingly, to combine the QSPR methodology. So the way how we can predict the properties of a material from their chemical structure to further this approach into the aging. So this is something that has not been done before. We just published this last year. And this is basically the proposal that we had, in a sense that since the QSPR methodology can be used to link the chemical structure with their final properties, and we know, for example, how the hydrolysis happens, we know how the material will look as a structure, chemical structure after the hydrolysis has happened, and therefore we can put the parameters, the structural parameters of graph theory to the aged polymer and see how basically the end case looks like, the start case looks like, and then to using the chemical kinetics to get in between cases. So what this means. So for example, for structural applications, we can have Young's modulus being predicted using the cohesive energy of this QSPR structural parameter via the QSPR structural parameters of a polymer, in this case PLA. We know that the mechanism is hydrolysis of ester bonds, and then we use infrared Fourier transform spectroscopy to measure the change in the intensity of the peak and to see the reduction over time. And then this FTR data we feed into the QSPR model, and then we obtain the predicted mechanical properties. So, for example, this is the kind of results that we obtained. So, if FTR data with over time of aging of PLA in water is on the left, and then when we feed it to the QSPR, we're able to obtain the modulus. And this one was compared with the experimental, so it was validated. And the validation was looking something like that. On the left case, we have only aging. On the right case, on the right side, we have also recycling. So it was a little bit, we couldn't catch the effect of recycling with this, which was not that surprising because we have the hydrolysis model inside. And recycling is something in plus that. But let's say the QSPR was able to capture the decrease of modulus for pure aging. Now, if we take a look a little bit onto, let's say, the expansion of the aging of polymers inside the composite. Here, for example, we have a polymer composite aged for 9 months in 60 degrees water. And as we see, the mass keeps dropping. So what is happening there? I promise to come back to this one. So if we take a look at the same principles of, let's say, polymers and interface is mainly made up of a polymer itself, but different type, and also the chemicals that bridge the fiber with the matrix. Typical interface composition is about 80% film formers, coupling agent about 10%, and the other chemicals for about 10%. The film formers are polymers, so it's about 80% polymer. And typically these sizings, they can also be degraded with time. It's also very small amounts, which is on the fibers. Therefore, it's really hard to measure experimentally, but we try to use a chemical engineering principle for the mass balance approach to get it. And if we look, let's say, how big is this interface? It's pure, it's just barely less than a nanometer. So experimentally, it's very tough to look into this covalently bonded part. But also the one which is called the interphase, right? So that's the difference between the interface being 2D and the interface being 3D. It's kind of like a mix of this film former together with the matrix. This can range up to 500 nanometers, but it's it's quite rough surface. So by knowing all of these processes that we have described, sub-processes for polymers, we can try to make mass balance approach. So if we have a gravimetric measurement and we know all the sub-processes that we have obtained, then the only parameter that we don't know is the dissolution of the interface, and therefore we can try to obtain that from estimate. That's not a very precise method, but still we can estimate the aging of interface. What happens is that, for example, we can see that the photographs, the micrographs of the composite and how it starts to degrade after a long time. As I remind you, at 9 months at 60 degrees water, and how the fiber matrix starts to debond and the cracks start also splitting along the fibers. So there's the interface which being filled in. So there's like a void being made. And if you see the dotted line, that is when the saturation with the Fick law is obtained. But what we interestingly see is that based on the composition of the fibers, and then you see the longitudinal and transversal fibers, the longitudinal, they start to increase in mass. So the water is being uptaken for 9 months. And for the C3, we saw that it keeps decreasing. So it's quite small, but from 0.96 to 0.87, but this is not statistically significant. And we found also a different source in literature by Peter Davies at IFREMER that they found a similar behavior. And what happens is that the whole composite, it keeps degrading, and they're like a pores, like voids that are becoming inside of it. And these pores are being filled with water with time. So it's not like it's chemically or physically bound, but it's just filling the voids. And therefore, we have this increase in volume. However, when this volume starts to connect together, they make a channel. And this channel can leach out this water outside, and we suddenly lose this mass. And this is for C3 composition, for the short fiber, for the transverse, it happens very quick. So we can see that we don't see an increase of weight uptake. And it straight goes to the degradation. So here, for example, data from Peter Davies is 10 years. So you can see that it's a composite which is in 60 degrees, for example, for 10 years straight in water. So it's a long process. And as I mentioned, temperature accelerates aging. So if we have 20 degrees water, for example, it's much slower process, but it's still the same mechanism. Interestingly, so I'm coming close to the conclusion already about, let's say, these various methodologies that we have inside this package. So with this with the mass balance approach that we looked at, we could obtain, as I mentioned, very rough estimate of this kinetic constant of the degradation of interface. And it has the same, so we have 3 scenarios because, as I told you, sizing is hard to analyze experimentally. So based on the models that are available in the literature, we had 3 scenarios. And in all 3 cases, so the scenario 1 is very improbable. That's maybe a little bit, yeah, I have to go into too much detail maybe. Why is that? But the idea is that basically, so in short, is that it depends on the coverage of the sizing, how it is distributed, and also basically this profile of the fiber being aged with the water, being attacked by free water. So the first case is not very probable, so it's most likely scenario 2 and 3. But in any case, this gives us some boundaries of the, let's say, degradation time from 22 to 30 years of this typical composite at 60 degrees. And interestingly, that this kinetic constant that we estimated for the degradation of the interface is very similar to the degradation kinetic constant of glass fiber, which makes sense because it's silica or silica bonds that connect matrix and fiber. So to conclude, basically, I would say that we have proposed this modular approach, and I apologize, it's a lot of information that we tried to put together. It's many years of things that we tried to do. Basically, it's that we have a complex process broken down into smaller pieces. We try to attack each of them individually, and then we obtain this physical-based models for each constituent, and we try to, let's say, make a framework usable for as many different combinations as possible. So this framework was actually implemented in a marine composite standard by the NVGL, so the Norsche Veritas, and they use some of our models in the standard practice. So these quantitative models and methods, they can provide practical tools for the industry. And the main idea is that in our modern age, in a way, that we try to replace as much testing with the modeling which we trust, let's say. Let's put this, that we can be confident with. So if we can be confident in the method, we want to replace the testing, because the testing for the industry means a lot of money. So for example, when they introduce a new composite material, it can take at least 1 to 2 years in a full like testing house. So they book a testing house for a year, and it means millions of euros. For new companies to introduce new materials, it means that they have a bottleneck. They don't have this money to introduce new material. So even by substituting the rigorous physical testing by 20–30%, maybe we can cut the costs by 200–300,000 euros, for example. So this multi-scale approach then provides the means to analyze the environmental aging of composites. It can also be used, I didn't write it here, but it can be used for looking into the microplastics, right? So the microplastics being generated by the aging of polymers. We can use the physical modeling also approach to give a bit of the mechanistic look into this process. Yes, I would say that future work should include the improvement and the interconnectedness of these modules. And we still have some limited understanding of the interface, in my opinion. But this is, let's say, something that the whole composite material is working on. So thank you very much.
Bye-bye. The point of the lens was some curses on my side.
Yes.
Maybe which we are just where you hope on the bill would be speeder call.
So
the big brown lights more like
so the PLA was it was basically in a consortium that was done about recycling of polymers, and it was in collaboration with the 3D printing. So they are very much interested in, let's say, the ABS versus PLA, the kind of typical old school polymers being printed. So PLA was chosen for this one, being the greener one of the two. Yeah.
Okay. But I had some questions on my side. When you test on these samples, how big are it? So it's like nanometers and something like that?
Yeah, so it depends which test, but let's say I have one picture here with the size that is for mechanical testing. So here we have a dog bone shape. This is something that we do for establishing the stress strain and the fatigue. Yeah, so that was pure polymer. With the composite samples, we usually do 3-point bending, so we don't strain them, typically a bit more complicated. We have how it's called, like I-beams, for example. Yeah, profiles.
And one more, this is water, just pure water, or it's some kind of salty water or
yeah. So in this case, I didn't want to overcomplicate this pure water that we look. So the ionized water, yeah, basically like a distilled, pretty much. But also the effect of pH and the effect of salt, for example, it all affects the degradation for some cases. So it can affect the speed. In this case, we didn't look into that. However, more interestingly, it affects more the fibers than the polymers. So, for example, if we have glass fiber, then the aging of glass fiber will be very strongly affected by pH and salt movement.
Yeah, probably if you going to lithium-dusty and lanes, which is glass fiber and composites. So, and this is exactly what we're trying to find out how long we are the color degraded.
Right, exactly, yeah. So we want to know the lifetime and how long, let's say, how long is it safe, and we are confident that we can use the material, and also let's say we have to understand how does it degrade, right? If we want to be confident about it, not to have any surprises.
Yeah, and your slide was like 22 certain years. It's exactly about composite materials.
Well, that was about interface, but if the interface fails, then the composite material will no longer be usable. But this is very much geometry related. So if you take a different geometry, it will change the number. So individually, we have to include this information, let's say maybe in finite elements to have their geometry.
But yeah, people in real life, because like frozen water and melted water, so they're like an intensifier, for example.
Yes, so that typically here, the higher the temperature, the faster the reaction with Arrhenius approach. But if it is frozen, there's the freeze thaw. So if it goes around 0 degrees, it's another process which here it's not included, but it affects mechanically damaging the material. So if it is the ice that is being built inside them. Yeah. And currently, there's also research in the cryogenic aging of composites, especially interesting for aerospace. So they are looking very much into these freeze thaws and very low temperatures, and also a little bit in the Arctic, like -40 degrees, for example. Around that, they look how does it, the brittleness, the aging, and so on, how it's affected.
Actually, it could be very interesting for us exactly cryogenic systems, because radio astronomical telescopes use cryogenic seals, which are cooled down up to 20 Kelvins US, and how plastics will survive in salt? It's a good question.
Yeah, so the typical problem, I would say, is the cycling. So it's not maybe the temperature itself, but it's the change of the temperature. So it's like, especially if it changes quickly from very low to higher and then again. So these cycles, the thermal shocks that are.
So it's mostly for ice, but still like sort of like.
I would say so, yeah. But still, also hydrogen, liquid hydrogen, the containers, the vessels, the pressure vessels that are being. This is also a topic which is where this comes in.
Yeah, clearly. Thanks a lot.
Yeah, please.
Good question.
Yeah, sure.
To this thing with picture with
No. To be honest, short answer is no. We haven't looked into tribal physics here, but it could be certainly for the surface. Like we were looking more to bulk, but I imagine that it could be like let's say some defects, right, that can be made on the surface, which can then start the crack, which can accelerate the process, for example. That can be, yeah.
Gravel, and very fast, right? But what I want to like so kind of contract of lots of wood cut. Later first go back on what was not to go one but one fights.
Right.
Like still for them. But it's a movement stall on that. Out of the brands that will also the
yeah, certainly it could be looked into it as well. I think here we kind of we're looking more into this bulk materials in a way that industry wants. They don't, kind of closer to the real life, not laboratory made material in a way that they want. What I mean by that is that, for example, industry, well, if it's not aerospace, which they're very careful, but let's say it's something like a wind turbine. They just make it in one go, like the whole turbine or something like the whole chap. And so the process is not perfect in a sense, like it's not laboratory controlled, So we want to have this kind of real life relevance in a way. But I don't think they would check, for example, the tribal, like the whole surface, you know. But it could be in the future, like with Ironis, for example, that they have these robots going on the blades. They could monitor maybe how the surfaces as well, like with the future functionality. It could be the case for the future, I think. Yeah.
Thank you. Thank you again.
Yep.
Sure,
We can do that.
Thank the certificate.
Thank you.
Thank you for coming.
Thank you so much. Thank you.
And yeah, and we go to our next speaker. Not here.
Okay. Yeah. Thank you.
So
on more things.
okay, so you connect to Zoom yourself?
Yes. Mm-hmm.
So probably I need to switch.
Yes.
Yes. Yes, it's correctly.
Well, yeah, thank you very much for the invitation. I will present something a little bit different. This will not be a scientific presentation. This will be a path that we've gone through in the last couple of years, in the last 4 years to be precise. And this is a presentation about our attempt. I would say it's quite a successful one, to commercialize something in the water sector that we have developed in the scientific sector. So I'm Martin Valtius. I'm a leading researcher at the Institute of Solid State Physics, and I'm the head of optical materials laboratory. I usually, in my day-to-day basis, and in the last 13 years that I worked in the institute, I work with nanomaterials. I work with the preparation and more like scientific research. But this is a rare case that we have the ability to commercialize something, and I would like to share some experience of how it went and what went wrong and good or bad, and what someone should do or shouldn't. The structure of the presentation is very simple, but the first thing I would like to say is that this presentation is not an advice. Don't do everything that we are doing in the same way, because I believe that for every startup and every company that wants to acquire public funding or private funding or VC funding or whatever it is, the path will be very different. And also, I would like to say that for the Spectrum Marine, the whole company, the close ties with the academia and the research institutions are very crucial, and that's why I think that it's very relevant. I will also say that this presentation will cover the one of the hardest and
yeah, sure. So we need to kind of, yeah, because you're also translating it.
I see. Okay, then I'll close the mic.
You'll see as well.
Yeah. All right. So there are many different ways to how to commercialize scientific results. I guess everyone is very familiar with a couple of those. Is patenting and selling, licensing patents. I would much rather sell a patent or license it from the institute than do whatever we've done here. The same. So let's move forward. Right. Let's just look at the problem of water analysis as a whole. If someone wants to analyze water and determine the quality somewhere in any way, there are many different possibilities. Most popular one is just taking the sample and bringing it to the lab. We have many of those in our country that they will perform for a very low amount of money. A lot of measurements. However, the issue is that you have to bring the sample inside of the lab and you have to manage the samples, and you will lose frequency. But there are a couple of solutions, even drones and all the satellite imaging is very popular, where you can acquire a lot of data with much bigger frequency and with lower cost. But you will lose data quality, so nothing will compare to the laboratory data. So the from the triangle, you have to always choose only two, either your data quality and data frequency or other variants. And that's what we try to solve with SpectruMarine. It all started with our pursuit and day-to-day job of creating scientific setups. Once we got the ability to create a scientific setup that can be applied in field, so at TRL 5 level, this basically the whole concept for it. But we deliberately chose only the technologies that can be as low maintenance as possible. So from all the different methods of analyzing water, from the like manual sampling from the pH sticks and all the super expensive 100,000 euro sensors that use electrochemical analysis and everything else, we chose only the methods that can be used unattended for many months. And this is the idea. So SpectruMarine is a metal box. You see it on top. It has a lot of electronics inside and optical systems, and also a computational unit. It is a fully automated unit that you put the whole box inside of the water. You connect it to the internet directly with the RJ45 connector. So it's like your router or web camera or anything like that. It connects to our databases and does the data analysis by itself, and you get the dashboard with data that's relevant to you. Of course, the frequency can be as big as you want, up to 1 Hz. We haven't found anyone that wants this type of frequency for any even industrial process, but I guess we'll look further and we'll look at someone that will challenge us to the speed. But it will generate quite a lot of data by itself, even at like 10 measurements per minute. What it can measure? We mainly focus on the optical system. So we measure everything that has fluorescence or absorption in the UV visible and some of the infrared range. So chlorophyll, ficosamin, biological substances, all the bacteria that has fluorescence, be it pink phosphor-eating bacteria or chlorophyll, green, blue, whatever it is. Of course, it can measure dissolved organic matter, so everything that's connected with decomposed bacteria or something that, like the algae that didn't survive. It can measure some metal oxides, because you can see that if your water is contaminated with iron, it will be more brown. It can detect that. It also has quite a strong UV irradiation, so it has the ability to measure hydrocarbons, so fragments of oils and fuels and everything else inside of the water. And how does it work? It's quite simple, actually. This is the approximate excitation emission matrix for the chlorophyll on your screen. This is typically what you get if you want to measure fluorescence for the chlorophyll inside of the lab. So we have tunable light source and full spectrum measurement. And through measuring the spectrum with different excitation wavelengths, you acquire something like this, and it corresponds to different biological matter and processes inside of the bacteria. Typical sensors, fluorescence sensors, you can go to AliExpress right now and buy one for like $10. They usually use only one single excitation wavelength and one single measurement value. Some of the systems use a couple of the excitation wavelengths and a couple of measurement values, but still it's a point measurement. And then you correlate these points to whatever you need to, like the chlorophyll or whatever it is. The issue with that approach and why those sensors are not frequently used for the very important industrial processes that this signal can be very much affected by other parameters like sun or dissolved organic matter background or anything else, and you will get false reading quite often. And what SpectruMarine does, what we have developed, we put an actual spectrometer inside of the box. So we still do multiple excitation wavelengths, but we measure full spectrum. So across the whole measurement range, we acquire quite a lot of data points. I think it's somewhere around 500 data points for each spectrum. We then perform quite an extensive analysis and peak fitting. It's mostly peak fitting, but right now we are transitioning to more database-based approach, because we are approaching the amount of data that will allow us to do so. then we analyze the data set as a whole. So we use different excitation wavelengths, we acquire a bunch of spectra, we acquire also data on temperature, salinity, and pressure, and then we do correlation with some calibration. We also developed our own calibration procedures because this is a nightmare to calibrate. This goes really bad, but if you solve it correctly, and we have a procedure for that, then it gets you quite an impressive amount of the results, right? And then, of course, we get the sensors, we connect it to the internet, it's all powered, and it sends the data constantly every second, not every second, it's every couple of minutes to our server. Then we do analysis on it, comparison with different databases, calibration procedures, and then we present the user with the graphical user interface, or most often no one wants to see this amount of data. They use it for the automation purposes for their processes. So we developed the system inside of one of the publicly funded projects, and then we thought that what we would do with it, like whoever needs it, or should we even spend our time to massive amount of time to commercialize it. And the first issue is that you have to find the clients, right? You have to find something that will catch this idea and put it to good use. So we got quite a bit of a list of processes that you have to follow if you want to commercialize something. For us, the first question was the money directly correlated to the water quality? For example, in environmental studies, it's not a sustainable business model because in environmental studies, if anything happens to water quality, it just happens, and it's bad for the people, and people will care, but it will not affect the main value proposition for a business, right? Is there a way to control water quality based on data? There are many processes where water quality can affect the business itself, but it's not correlatable to anything, so we cannot do anything with it. A couple of examples are fish industry in the coasts of Spain, for example. They got contaminated with pollution quite extensively, and they just moved everything to Peru. So they just didn't have the ability to solve anything. Can the pollutant be measured with the device? Let's be real here. This device doesn't measure anything and everything. It measures only specific parameters, only things that we can correlate to. And it's quite an extensive list of things compared to other systems, but we got very often asked like the questions if we can measure, for example, I don't know, uranium concentration in water. We can't do that, right? We can measure only things that are at fluorescence or absorption. We are looking for places where the conventional sensors fail, and we have to solve an expensive issue. So the sensor is not a cheap thing. We have to get money from the business, right? So we have to solve an issue that's substantially more expensive than the sensor itself. So it's much more easier for them to buy the sensor. If you don't find a fit, you will die. In any business, you will just for it's not only water sector, it's anything else. And we of course looked at the fisheries, water treatment sector, where they have direct correlation to all of those parameters, fish farming, and farming in general in water, like shrimp farming and anything else. Desalination, HVAC industries, and everything else. We looked at it, and we decided to start with fisheries. During the first project that we developed this device from, we connected with Pescanova. Pescanova is the largest shrimp manufacturer in the world. I think that there is a 30% chance that if you buy a shrimp in your supermarket, it comes from this company. So they produce insane amount of shrimp. They have like thousands of staff, and they have. It was very funny to visit their R&D institution because it was bigger than my institute, just for this shrimp. So we sent the sensor, we pitched them. They are always looking for those types of things, and we pitched them. They said, send the sensor in. We tried the sensor, we developed anything that we could in the institute. We tried our best to do it, and we got approximately 2 weeks of usable data throughout the whole year, because the system was actually trashed. So it was so bad, it was insane. It failed in every possible way. Every component that we had, except for the window itself, broke. So we decided that we have to take a break from this approach because we will lose this contract, because you have to make them, you can make mistake only once. If you twice make everything wrong, they will not talk to you again. But we got quite lucky because another industry contacted us. They found us through one of the platforms that we were active from, and they contacted us and proposed another case for the sensor yield. And the another case is the salination industry. We are quite lucky here in our region that we have fresh water everywhere, and it's quite cheap. But for the Middle East and for MENA countries, it's for Saudi Arabia, for example, every liter of water you get that's fresh comes from the desalination factory. So it somehow went from the sea through the desalination factory and to your tap, whatever it is. So the industry is crazy huge. And they contacted us. They very quickly determined what the problem is that we can solve. And the problem is membrane biofouling. So most of the desalination plants, or I would say above 90%, use reverse osmosis and membrane filtering for the water. So the idea is quite simple. You just get this membrane filter, and you put water with a massive amount of pressure through it to get the salt out, and then you get brine and clean water. And the main parameter that damages those filters is biological matter. So if the bacteria goes inside of it, it starts to grow in it, starts to biofoul and kills the filter, and this is a very expensive problem. And this is an expensive problem not only because you will have to pay 100,000 for a new filter, but because you will have to pay for the electricity for the increased pressure of the pump that you will have to push through the water, and you will have to stop everything to replace the filter. It's quite an expensive problem for them to solve, and the idea is very simple. Just put the sensor before the membrane filter, directly before it, but after the pre-filtration. Pre-filtration in their case, if you want to create millions of cubic meters of water, is basically filtration with a lot of chlorination in it. So it's chlorine, and that's how they kill bacteria. We put our sensor after the pre-filtration, before the membrane filters, and try to determine where the biological matter starts to go inside of the filter. So when it fails, right? And this resulted in quite a successful cooperation. We are currently have 2 pilots running inside of the Saudi Arabia. In one of the biggest plants inside of the Arabia, but we just this year transitioned from the test plant to the operational plant. So it goes to 307 now, and through this successful collaboration, we got the insight that this whole business thing might actually work, and we might want to pursue it further. For the timeline of the company and the whole process is it looks approximately like this. So we started with the LEA project. It was mission C 2030, and it was in 2022. It was a 1-year project. It was quite rapid because it was just the timeline was very short. We developed first prototype that year and tested it this area with the fish industry, and happened the same year. And we of course tried to do a patent on the technology, and it was submitted through the institute, so no company was existing there. We continued with Saudi Arabia tests in 2024, and at 2025 was the year that the breakthrough year that we decided that if it doesn't work out, it doesn't work out. Let's move forward. But we were, I wouldn't say lucky, but we were fortunate enough to get an pre-seed investment from the Netherlands, from the NOM. So we got the pre-seed money from a Netherlands fund that is partly operated by private individuals and partly operated by the government. So they have a huge scouting procedure, and they scouted us, I guess, and gave us the money to continue forward and to pursue the idea that we can commercialize it successfully. And in August last year, we established the company in the Netherlands. Interoperability, a couple of words, and then the next part of the presentation will be just the insight that we went through. Again, take it with a grain of salt. You don't have to relive it if you want to do something. And I completely understand anyone that doesn't want to do something like this. But intellectual, let's quickly go through a couple of insights from the business, right? Intellectual property. We got quite a bit of patents in the pipeline right now, but when you start in the academia, you have to always remember that the patents are very expensive if they are not needed. So if you want to submit a patent, and you have to clearly understand what will happen with the patent later on. Of course, there are a couple of programs with public funding right now that require the submission of patent as a deliverable. Just submit Latvian patent, the cheapest one, and forget about it in 2 years. Just do it. But if you see a proposition of value for business that can be acquired and costs money and saves money for them, you absolutely should patent things, right? And it will be quite a bit more interesting for the investor if they see a patent and value outside of your idea or concept. This will help us. What's helped us a lot. And of course, patent only necessary part for the Spectrum Marine part. I would say only 20% of the IP is patented. Everything else is closed source. So this is the state of things. Funding and business strategy. The lessons that we have learned throughout this journey is that if you can use public funding, use cooperation with industry and cooperation with institutions and with industry, submit projects, BioFots, LEA, Horizons, Eurostars, whatever it is, whatever your ambition is. Public money is very sweet, but the investors usually will ignore it. The in-house advantage, if you're developing something that's hardware related, that's at low TRL, tier 2 or 3, that you probably want to keep everything in-house. So don't outsource anything that you don't need to outsource. We did this mistake. We outsourced a couple of parts, but the lead times usually is what destroy the progress and iteration. Constant client validation is a must for any startup. So just if there is no one to tell you that they need something, it's not because they don't understand, but it's because they don't need it. So the right, you have to find something and problem that you can solve, and not look at your solution and find a problem that can be solved with this screwdriver or whatever it is. And yeah, business people, I'm quite far away from business talk at the level that the venture capitals and everyone else is talking to, because I'm a scientist. And I frankly am not very interested in those. That's why business people are, if you want to commercialize something and you're a scientist, please employ a business person. It's a very different beast. And I wouldn't suggest any scientist to do business talks to his clients, right? And you have to have the right team. For the investors, we have a team of 3 people, 3 core members for the whole company, and we've got the impression from the investors that it's like at the limit. If you have some more people in the company, you have to have very, very good justification why they are there. So don't take your whole project and move to the company. It's not a good strategy. What helps Spectrum Marine through all the journey is that we accidentally proposed value that we were too blind to see, because we are scientists and we developed a cool technology that can measure spectra and sense the data, whatever it does with the different algorithms and everything else. And the thing that clients mostly cared about is that it's just connectable to the internet, because they operate with the premise from other sensor manufacturers that if you buy a sensor, you have to buy a data logger, you have to have an engineer that will connect everything and do whatever it is, your proprietary dashboard that you will have to connect with some API, or it's a mess. And you will have to pay every step of the way. And for us, the main value proposition. It's not the main value proposition. The data is still the main one, but the big value proposition is from the fact that for the client, it just takes out of the box and puts it in the network and just opens the phone. That's it. This is quite a good realization. It's not connected with the core technology, but it's good to have. Close ties to academia helped us a lot. I covered it already. Work with the institute. They are very much interested in spin-offs and commercialization of ultrasound of some sort, because institutions will show you to everyone that wants on the fence about giving the institution money, because they will show that we have some business and value here. So the institutions and the academia as a whole is a good also source of brains. The students, when they are graduating, they are usually the smartest part of the life. They don't want to expand their knowledge. This is the best time to get them. Very rapid iterations. Again, keeping everything in house helped a lot through the whole process. Through the 4 years of development, we've developed. I think this is the 9th version that we are deploying right now, and the 10th version will, by the way, will be made from the polyethylene, not the aluminum this time, because aluminum, if you want to deploy something with Black Sea, aluminum will be eaten away, especially if you have electronics inside of it. Yeah, so 10 iterations of the devices in 4 years is quite a lot. 8 generations. So, but the 10 is in the work right now. Good balance between all parts to make it happen. Yes, the early employment of early connection with business people that can push the technology to clients gave us the opportunity to see the motivation first and get the proper deadlines, because for any hardware startup, it's very easy to lose yourself in deadlines and just forget about what you were doing and fiddle with electronics for 2 years. It will not happen if you have a Zoom call in 2 weeks with potential client that wants the device in April, right? You have to have proper strict deadlines. And again, this also means that if you develop a product, then you have a direct eye to look at it and validate it through the real case, right? Networking is key. It's just, I would say, from the hours we spent on the business itself, I would say at least 30% is networking. Just talking with people, talking with companies, validating, signing all the paperwork, going to the Netherlands to some convention, or sending sensors to Saudi Arabia, solving logistical issues, looking at shrimp in Spain, proposing a Horizon Europe project with Portugal that we also participated in, sending sensors to USA just to know that OSHA will not allow UV sources inside of public waters to get it shipped back. We were working on that this year. Norway, where we got our first clients that paid actual money for the device. Baltics with the Interact project that is currently running, and we will also develop 6 of the sensors to be deployed in public beaches in Latvia and Lithuania. Singapore for the HVAC industry, Germany with the couple of 2 sensors currently operating in post-mining operations. So they just collect mine water and analyze it. Poland with buoy manufacturing that can do very good buoys, but want better sensor. And if you have something of value, you have to be where the most movement is. And for the Europe, if you want to work in water sector, Leeuwarden is the place to be. It's basically a water hub. It's like a Silicon Valley for water technologies. In Europe, there are quite a lot of companies there that have valuations of hundreds of millions of euros that just do water stuff. And we are established there. We were invited there by the Netherlands, the NOM itself. And also, if you want some contacts for the idea validation, feel free to reach out. We share contacts very freely if you have some idea to validate with someone you want. feel free. We have quite a lot of contacts that can actually help you to get to know the industry better. Let's do no mistakes. First mistake, if you have decided that your text is TRL6, you can tell it to the clients that this is TRL6 and even do pre-pilot. So you pre-device to someone and say that this is a lagged example. This is like rough. This is TRL6, right? He will say yes. 2 weeks will pass and he will forget about it. He will think that this is a product and it doesn't work immediately. So this happens to us a lot. If you want to like move something through the business structure, the person you will probably get in contact with is the R&D department person that understands what TRL6 is. But as soon as you send the first invoice, as soon as you try to do a pilot or anything else, they will forget about the TRL part entirely. So they will think that this is a product. Not taking system testing seriously enough, we have twice now sent a device that failed in the first week. I don't know how this happens. It just happens. We are taking it quite seriously right now. So all the prediction modeling, all the calculations, scientific stuff, simulations, or good engineering seeking for advice will help a lot. So it's a crucial part. So not to just make mistakes with the shipping of the devices that don't work. We have the device that was working for 3 months inside of the lab correctly, perfectly. We shipped it, but we failed because in the shipping they moved it wrong, right? They were crazy. Feature creep a lot. Yes, it's very easy for hardware startups, and I don't suggest anyone to do so. Is to feature creep, meaning that when you propose your technology for a client, he will usually say, "Can it also do X?" And don't try to implement this X in your device every time that you're asked for it, right? If you do, you will get the device that has many different features, and it's very sad for you to fail a device just because a feature that was not requested by this particular client failed, right? So we don't do that. Just have a strategy, work. If it start to do it, if it doesn't work, just scrap the strategy, change it. The team, 3 people, myself as a chief operating officer of the company. I also am responsible for the scientific part of the whole operation. Gib Fuzzelens, a wizard, was the emails. So he sends 150 emails per day, easy. He books, he looks at my calendar, decides where I have free time, books a meeting with some person, briefs room before it, collect all the different contacts. He has a CRM. Does anyone know what CRM is? Yes. He has a whole system just for the emails. He has like the lists of contacts and everything else just to follow through with everyone. And that is 2 man's extremely smart guy, extremely antisocial guy. So he will never do a presentation about the whole thing, but he can write you, and he can deploy an SQL, fully deployed SQL database like in 1 day, if you want to do it. Crazy smart guy, please respect for him, but you have to have the whole selection of those people, right? Thank you very much. This is the text, and we are always open to collaborate in the Horizon Europe or any other project as the Institute. I'm still affiliated with the Institute. I work half my time there, and with more investment, I guess we'll transition to a bit more, but I don't think that I will ever lead science in my life. Thus, if you want to submit Horizon Europe project with us, if you want microscopy data or some crazy scientific setup that we have at the Institute, feel free to reach out. And also feel free to reach out if you want to submit some project with the SME. So the Spectrum Marine is SME in the Netherlands, which can also provide quite a bit of power submission of the project. Thank you. Well, thanks, personal stuff like give us about of the note.
Now goes the comments that I work with support for strategy events like I also cite as from the business perspective, that we must always build those your support systems or ecosystems around you to validate your ideas, and that is the tool to success. Otherwise, you're alone in all that pool of revenues ideas, but if you have some partners by those sides, you're able to move that forward.
Absolutely, the validation from the companies. If it's very hard to grasp as a scientist, because we usually assume that if they say no, that you haven't explained something right, or they didn't understand something, but they did understand. That's don't want it, right? Or want it. I don't know.
But if you really don't understand obviously what the fault to get to switch that stuff in your rather than searching your hostless that you want to like, the help that real successful also
we prove it here. So this is the point. Like, I think that the Latvia and Baltics in general, with different varying success, is a great place to build something like this. Just because of a single fact that since we are not a lot of people, we help each other quite a bit. And from my experience with building business in Germany, for example, in Germany, if you want to build a business, it has to be a business. For us, you have much more leeway to make mistakes or get results. For example, if it's also in science, it's the same. In business, it's quite a bit different, but in science, the same story. But if I want to, for example, acquire a SEM image of a very particular material that I want to employ in the device, in Germany, I will absolutely have to pay a lot of money for it and wait for a couple of weeks. Here, I know a guy that knows a guy that can get my sample inside of the microscope today, right? And it's just an extreme case of it, but for any other operation, I haven't seen anyone that looked at the SpectraMarine and said, all right, I can help you, but I won't. Everyone helped whatever they can. So this is also the BioFOD program is huge for that. Absolutely apply for the BioFOD calls. It's crazy. You get money just to develop things that you can sell later on. And for other countries, it's not the case. So it is built in Latvia, but it has to transition to the Netherlands to move forward because of the it's not a development anymore; it's a business, right? And if you are an investor and you see a water tech startup, you assume it's from the Netherlands, and if it's not, then it's a red flag, right? But we are still here. Right. We have a obligation to move operations to the Netherlands, business operations to the Netherlands, but the development will stay here for quite a bit.
Absolutely. Listen about Baltic marketing skills, like on both users. I fully interested in your product and maybe another question. Product is sensor or data and because it's like you create a sensor, I'll send in sensor to client and it gives full access to data, or other access data yourself and help with I got three questions. First question about data. We do sell a sensor as a sensor, but the whole idea of SpectraMarine that it's a system. So it's not only the sensor. In fact, from the development, like the development of the device of the system, only 40% is the hardware and 60% of the database and data analysis and everything else in software. Thus, we have a business strategy where we sell the device and you can actually draw data from it and some basic analysis that can be performed on the device. But if you want some advanced data analysis, you will have to pay subscription fee because we will use our video cards for that and the servers, right? So this is the first idea, the first question. Second question, Baltics there are not a lot of clients that use water as a crucial part of the business. So there are not a lot of fish industry there. We have some on the rivers with the salmon and everything, but there's no business client that can facilitate for the growth of us, right?
In Baltics, we focus on public funding and projects where we can apply the device to get data for public use. And the Interreg project is one of the examples where we will produce these 6 devices on 6 buoys on 3 different lakes in Latvia, Lithuania, in the border side, and get data completely free to everyone that needs it for the researchers. This is the main idea for the Baltics, and this because the Baltic doesn't fit in the whole structure of the value proposition for the business. And the third question, can you remind me?
Wait, so data on Baltics, I think it's fun and things like that's
all right. So
the question about pieces with Packle and so if you're a company and university institute, Packle is the one institute, but this is by company. So how will you divide or give the shape of questions for Packle?
Yeah, excellent question. I think that for the scientific person, it's a quite a different process than is expected for the company. But the thing is that if you create something on the institute or the Ventspils School like this, everything that is created here belongs to this place, right? So if it's created by public funding, it should belong to the public.
Mm-hmm.
And if you want to commercialize something and get value from it or get investment, this is a crucial part for the investment to get the patent to the company. So they will not give you an investment if it's based on the patent that belongs to someone else, right? So there is a patent transfer procedure that you have to follow if you want to buy something from the public university, and it's very much the same as the public procurement procedures. So you just go through the open market, and you get the procurement procedure from the institute to everyone else that needs it, and everyone has to compete for the better price. And Spectrum Range just competed for the better price and paid for the patent.
Yeah, that's correct. Yeah. Well, thanks a lot. I think because it was fun, but
sorry about that.
Very strong, but I think you can continue talking well.
Sure.
Yeah, so I have to switch to my talk. Wait a second.
Oh, thank you very much.
So
thank
you for your participation.
Thank you for the invitation.
Yes, so Antika continue right now. Thank you. Yeah, so we have 10 minutes left until break, so I try to show my presentation as fast as possible. Not to make it long. And the topic is mostly for modeling, but it's again. Yeah, thanks a lot. So, yes, yeah, stop. Yes, this screen was shared from another computer. Yeah. But now it should be fine. Yeah, thanks a lot. I actually continued topic about trying to make some kind of product and showing how you can use modeling tools. So it's like a both in one presentation, and starting about some discussion about permanent magnet generators and components of them. So we actually use a lot of permanent magnets in our life, and okay, so I'm back. Sorry for some technical issues, and I hope you hear me and see me as well. Wow, yes, so on place participants are so good. So yeah, so yes, so I will start. Permanent magnets are very usual and useful things in our life, and we try to make some kind of versions of these permanent magnets, and usually so for permanent magnets, permanent magnet generators, and normally it's stator and rotor. So rotor rotating, we have conductors and magnets and coils, and generating electricity. But it's like one of standard ways of what we can think. In life, here is some kind of linear permanent magnet generators, which located in a linear way and starter, the stationary part is connected to, let's say, basement, and translator or alternator going one in another directions and producing same electricity, but not exactly rotating. And these enormous ways of using these generators, normal one, like a rotational and linear one. So it's like a wind turbines, so hydropower, like a small hydro systems, any electric vehicle. So we now almost all electric vehicle has their generator itself. A lot of portable generators providing renewable power source, outdoor activities, construction sites, emergency backup powers, and so on. Same also maritime applications to generate electricity from wave or tidal energy. And this exactly case what could be interested for our solution. So in this case, linear generators, let's say for tidal use like a effects of moving waves, and here is some stationary part and rotor, which is just going in linear direction and producing electricity. So in our project, we focusing on linear generator models, but a bit different way for bicycle generators. So it's like a small power generator, but it could be also scaled for a bit different aspects. And the main change between rotary, this type of generators, which are like a very usual and general type, this type of generator is quite easily could be modeled. So it's symmetrical, and we can make like a full-scale modeling of a magnetic field distribution, or make slices and see symmetrical patterns everywhere. But in our case, and this is also become a kind of a prototype in pilot products with Friendina trademark, so environmentally friendly small power generator with rotor linear motion, and it's like a use concept of linear generator, but make it on a like a brakes of a bicycle. So it's like a standard brakes more or less, and it's added additional design with the generator itself, which could power bicycle electronics itself. So it's not very powerful system, because when we are driving on bike, we producing several tens of watt maximum. We are not very powerful creatures of the man itself. And historically, it started in 2009 with some prototypes making in lab, or again some student projects, and student project become a more general ERDF projects, which brings us idea how we can do a modeling of linear generator, how we can create them, and how we can make some kind of field prototypes and products. These technologies for linear generators, several iterations and versions, was patented in Latvia and European patents as well. And as Alexei told, Latvian projects mostly asked about deliverable as a patent, and we satisfied with our public money. And after that, it was made some series of prototypes, which we can try to test and find out like a bad and good things and features of it. But there is problem. So if we are trying to model linear generator, it's more or less okay, so it's not very complicated. But in our case, our rotor is a disk, and magnets and generator itself, it's like making arc. And this becomes a nightmare for modeling software because it's not symmetric, and actually all fields you need to reconstruct like a point by point. At some designs what we trying to think and trying to test, and again each design asking to make all model and recalculate everything, and one more in our cases. And again, like a 2D plot, it looks very simple. So like a magnetic fields, so like going around coils and magnets. But if you're going to try to model full design, we try several softwares and actually fail with good results which are compatible with prototypes. And after that, we found EMWorks program, which is a part of SolidWorks. So it's integrated in SolidWorks, and this becomes very easy. You don't need to use several software for modeling. You use SolidWorks for model as a structure, and same software for modeling electromagnetic forces and fields. But in this time, it was 2019, I think, this program just arose, and it's so team who produced this software was from Canada. We tried to sell this product as well, and they produce like a free trials for at least month. You can just take it and use, and if you satisfy it, or you need to buy it. We take it with software for a couple, just per month, test our model, and find out what the EMWorks are crashing in our model. So our model become too complicated, and so we try to contact this the company. We say, okay, sorry, we understand, so something goes wrong. Give us additional time for testing, improve their software, and send us additional versions. And in total, it takes like a 3 iterations for us to adjust our model, and like a 3 versions of these software developers to make it software stably working. So I probably need to go to lunch, so I will very fast and show some results. So how it looks, so we have a standard SolidWorks design, and EMWorks defined magnetic fields, so density, and successfully make models and then trying to do results. And these results are also later compliant with physical samples that we have created, and studied in laboratory, and got similar. So okay, I'm not stopping on a plot because it's quite timing to explain, but it works. And this is probably a nice story how we from researchers could also interact with software developers and improve our knowledge and improve products as well. And yeah, so I will just not stopping here. Finally, we got nice testing. It just won't stop. It's not our generator installed, but it was tested in errant race bicycles from our Latvian company. So, and again, we are trying now to find some users and probably to establish something what Alexey says, like a startup, and then continue with the development of business models and products itself, because currently it's around TRL 6-7, so we normally tested in laboratory, have pilot products or pilot versions, and at this moment it's stopped. Okay, so I thought I just stop my presentation here because it's too time to close this session. If you have any questions, or we can discuss it in lunchtime. Okay, so now we have lunch until 1 o'clock, and so I will put my Wow. So, we'll join our session next at 1 o'clock. Please share screen and collect screen sharing as well. With continued presentations with our colleagues from Latvian University and Riga Technical University, but they are mostly online. So 2 presentations about like success stories about projects, and 2 presentations by Modris Doberis about practices about in SolidWorks and some features what we can do in SolidWorks. Yeah, so thank you, and time for lunch. Hello again. So we continue our workshop, and next session, first speaker will be Tia Sija from University of Latvia. So Tia, you are here, we see you, and yeah, please start your presentation.
Yes, hello. My name is Tia Sija. I'm from University of Latvia, from Faculty of Science and Technology. I apologize, I'm a bit sick today, but I hope that will not make my presentation much worse. So the topic of my presentation is how to determine wind speed without measuring it. Of course, the topic is about wind energy, but when I was creating this presentation, I actually answered this question in presentation, but it's pretty far towards the end. So we will get to that question, but before that, we need to start with some introduction. So, why do we need wind energy at all? Because I will start by assumption that renewable energy is good. There can be many different opinions, but I don't think that this is the time and the place to discuss them. So let's assume that renewable energy is good. The thing is that solar energy is much cheaper and easier to install from a regulatory perspective. What has happened with solar energy is that the cost of solar energy, it has decreased rapidly, exponentially. It's, if you know the Moore's law for computers, then it follows the Moore's law, the price of solar energy. Why do we need it? Why do we need wind energy at all? The thing is that we still do not know how to accumulate energy easily on industrial scales, on scales that is relevant for the wind grid. And the solar has quite significant limitations in this regard, as we regrettably know here in Latvia. During the winter, the sun is a rare occurrence, and it's typically about 1 hour of sunlight per day, if that. And of course, there is no sun during the night. So we need something else. We need wind energy. That is the opposite of solar in terms of when it is generated. We of course know that the solar has a diurnal and seasonal cycle. Maybe the lesser known fact is that the wind also has both diurnal and seasonal cycle. And what we can see here is that in the graph, it's the energy generated in 2023, and here are only 2 of the sources. The orange is solar and the green is wind, and you can see that, of course, obviously there is much more solar being produced during the summer, but for the wind the relationship is opposite. We have a lot of wind during the winter, and it is during the winter the wind has almost no diurnal cycle. The wind blows almost the same for the whole day and night. But we have this seasonal cycle, and we see that we can complement the solar energy with wind energy. There is one more thing that you need to know about the electricity market, because it's quite easy to, relatively easy, to put on a solar panel, you just buy on this increasingly cheap solar panel, you have a green field with some grass and maybe some sheep on it, and you just install the solar panel in roughly the direction of south. And and you can generate energy. And this seemed like a good idea, therefore a lot of people did it. And now is the situation that when there's a lot of sun in Latvia, then the electricity price is negative because everybody is producing it. So there is a strong economic incentive to generate energy when there is no solar energy. Now, okay, let's assume that we are in agreement that we need some wind energy. The next problem is that the wind turbines are quite high. There are a lot of problems that come together with it, but I will focus on one of them. And the typical height of wind turbine is around 100 meters. I think it's not very surprising that we need to know quite precisely what is the wind speed at 100-meter height. And because the process is so complicated, the wind developers, they need to know the precise wind speed with precision of 5% would be ideal. It's not like in other engineering disciplines where we can just make some safety allowances. The wind needs to be known very, very precisely. And this is very important at the wind turbine height, which is 100 meters. You might think that, well, where is the problem? We have a lot of information about wind speed. The forecast is, I can open my phone and see the wind speed forecast. However, that is the thing that is assumed by default and therefore usually not said out loud. I would say every normal wind speed forecast or wind direction forecast that you see, it corresponds to 10-meter height. It's just by default. You might know that there are lots of wind measurement stations, meteorological stations, around 20 for whole Latvia, operated by our Environmental Geological Meteorological Center. However, they all measure wind speed at roughly 10-meter height. The problem is that wind speed at 100-meter height differs significantly from the wind speed at 10-meter height. Usually, in most situations, the wind speed will be higher at 100 meters than it is at 10 meters. However, I would like to the thing that I would like to stress is that what you see in this graph is that on the x-axis it's wind speed and on the z-axis it's height from the ground. So these are some typical wind speed profiles that we can see. And the important part is that the relationship between the wind speed at higher heights, at the turbine heights, with the relationship of wind speed at 10 meters, there is no one single relationship. If you have measured 10-meter wind speed, you cannot reasonably calculate the wind speed at higher heights, at 100 meters, because the relationship from physical because of physical considerations, it depends on, first, most of all, the land use. It will be different between sea or some kind of urban area, and it also depends on the meteorological conditions. So this difference is governed not only by the surface, but also by the by weather, the amount of sun, the amount of wind speed. So the one conclusion that I would like to for you to take is that if we want to build a wind turbine, we must measure wind at every location where wind turbine is planned, and we must measure it at 100-meter height. That's non-negotiable. You can't calculate your way out of the 10-meter wind measurements. So how can we measure wind? There are two main approaches. One is this cup anemometer, technologically quite simple. The wind blows, these cups go around, and you can determine wind speed. However, again, remember, we must measure it at 100-meter height. So it needs a tower to be put on. And I assume that it's not hard to guess that building such a tower offshore is quite expensive, because you literally need to build a tower in the middle of the sea. There is other approach. You can measure wind speed at quite high at turbine heights from a wind lidar that's put on the ground. It's a remote sensing approach. It gives quite reasonable results, and you don't have to build this tower. You can do it from the ground. However, as we can see, it's not cheap. So, and there are some additional problems. You can't measure wind speed for a day or a week or a month and say, okay, I have established my wind speed. Climatically, it would be good to measure at least 10, 20 years. The definition of climate is the 30-year average, but of course no one has time to do that. But you should try to measure at least 1 year because of the seasonal cycle. And of course, we know that we have hot years and cold years. For instance, we have a very, very cold summer, a very cold winter right now. We also have windy years and still years. There is some variation between the years. And what we cannot do, we cannot travel in time and say, oh, this is our location. I would like to measure wind starting from 10 years ago. You just can't do that. So the wind measurement is necessary. However, we need to at least supplement it with something else. And then our wonderful solution is numerical or mathematical modeling, and I will be talking about it for the next slides. So first of all, the numerical modeling or mathematical modeling, it's not scary. It shouldn't be scary. I promise you that you have used products of numerical modeling every day. That's your average. That's your average weather forecast. I would say that all weather forecasts that are not based on the question, you can look at your cat and say that if your cat is becoming fluffy, then it will be cold winter. Those forecasts are not based on numerical weather prediction models, but the rest, I can guarantee you, there has been a model that runs to create this forecast. So what is a numerical model? The simplest way how I can ask you to think about it is that it's a computer program. That's what it is in essence. However, it's a very specific computer program that implements physics equations. Namely, we have found a way, it's quite an old approach, how we can implement physics equations, the laws of physics, in a computer program. And typically, the result of a numerical model is, you can think about as a spreadsheet full of numbers. But these numbers correspond to the values of physical parameters. And typically what we do is we visualize it as a plot or as a map, in most often the case of wind energy. Vladislav informed me that this will be quite a general audience. So I was thinking, what is the best way how I can explain to you what a numerical model is? And if you are unfamiliar with numerical modeling, I would recommend to think about it as a very precise video game. There are some commonalities that can make you understand numerical models better. And of course, there is also a very interesting thing that you might know that video cards or graphical processors, they're nowadays very much used in AI and the video cards and GPUs. They started as something for video games, and the underlying mathematics is quite similar, so it makes sense. And we know that computer programs, they need to know laws of physics to look natural. They are quite tricky to program, and there are two more aspects that I would like to stress. Is that you need that if you want to run a really nice computer game, you need a powerful, really powerful computer, and that is very true about numerical weather forecasts. And another thing is that you need the program to work quickly. You need to generate the results quickly. There is no point of video game if you get 1 frame per minute. The same is true for numerical weather prediction models. And I will not attempt to explain the full meaning of computer models. There are university courses for that. But there are 2 things that you need to know about models that I will try to explain to you in a simple way to understand how this wind resource estimation works with models. So the first of all is that this is different from a computer game, that models calculate the evolution of the state of atmosphere over time. And we are simulating a specific time and specific location. Our calculations are, they correspond to a specific time and place. And the other thing is that all models have a property called resolution that determines how precise the model results are. I will go into detail in those aspects over the next slides. So what you have to understand is that models calculate how the state of atmosphere evolves over time. Again, if you would like a more simplified example, we can, let's say we throw a ball in the air. We know the position and the velocity of the ball, and using the laws of physics, we can calculate how the ball will move afterwards. It's the same with weather models. We can we determine the state of atmosphere at a specific time and area, and we use these models to evolve how the atmosphere will change, how a cyclone will come towards us, and how it will start to rain. And what is interesting now, we have to separate 2 different things. One is these forecasts that are on your phone. They correspond to time in the future. The calculation is made so quickly that the forecast is ready before the time has happened. However, what we can do, and what is mostly important for this wind resource estimation, is that we can run the model for a period in the past. We can make the model represent atmosphere in the past. That's one thing. And the other thing is this resolution. Again, very simply put, we divide the atmosphere in very small pieces, both horizontally and vertically. It's called a grid. And almost the general rule is that the smaller the piece, the more precise are the calculations. Again, there's a good explanation why it is the case, but I will not go into the details. And we call this the typical size of the piece, we call resolution. And the typical resolution of numerical weather prediction models are between 3 and 30 kilometers. So now I will be answering the question that I posed at the beginning, how to determine the wind without measuring it. So the thing that is being done by a lot of people is that you run this numerical weather prediction model, you run this computer program, but you put the data in such a way that the state of the atmosphere corresponds to 20 to 30 years in the past for a region of interest. And that's another limitation. Let's say you are interested in a single point. However, the models, you cannot run the model for a single point. It doesn't work that way. Let's say we assume that Latvia is a 500 times 500 kilometers. You need much larger area, at least in the thousands. It's easy to understand if you listen to the weather forecasts and you know that there is an anti-cyclone over Russia determining the weather today, or there is a cyclone coming from the west. Regrettably, the whole atmosphere is joined together in processes. And again, getting back to the analogy with computer games, it is computationally very, very, very expensive, and therefore there are only a few institutions that can do that. There are two main types of datasets. That's why I invoke this property of the model called resolution. We have, for example, ERA5, and that covers the whole globe, and it provides wind speed data with 30-kilometer horizontal resolution. However, because of the huge interest from industry in this topic, there are wind atlases with much lower resolutions. For instance, the New European Wind Atlas that I participated in creating it, so I know a bit about it, and it covers only the area of Europe, but it provides much better horizontal resolution. I can go on and on about why small resolution is better, but I want to just point out a few things. A lot of this data is available completely free of charge. And I would like to stress that modeling data is available free of charge. You can just go to one website or another and just download it. And there are also some private companies that are offering proprietary modeling data for a fee, but you almost cannot get high mass these 100-meter wind observations. They are mostly done by private companies, and they are secret. It's a secret information. You cannot get it. However, these free of charge datasets, they can be very large, up to terabytes, and they need to be geo-referenced. They need to have a lot of metadata. So you probably most likely won't be able to just download an Excel file. You will need some kind of Python. The data will probably come in specific formats. They're not very hard to work with. They're actually quite reasonable. If you know Python programming, it's reasonably easy to do, but you won't get this data in the normal formats like Excel. And the last point I would like to make: why offshore wind? Offshore wind has obviously its drawbacks, mostly associated with installation costs. However, in Latvia, a simple thing is true, and it holds true quite, almost all situations, is that for Latvian climate, not for Southern Europe, for Latvian climate, there is significantly more wind speed over the sea. This is actually a result of one of these wind atlases that I mentioned earlier. This is the wind power potential over Latvia. Here you can see the Scholar scale. Here, not a lot of wind power. Here, lots of wind power. So it's quite easy. There is, of course, a simple explanation for that. You can think about the wind speed as coming mostly from the west. You have large wind speeds over the ocean, over the North Sea. The wind rubs and the wind loses its velocity over the land. So we have Scandinavia, a bit where the wind loses its wind speed actually quite a lot. And over the Baltic Sea, the wind is already smaller, and then the wind speed slows even more over the Kurzem. So over the Gulf of Riga, the wind is even slower. That's roughly the case. So I would like to leave some time for questions. So these are just the conclusions, that for wind energy, we need to know wind climate at 100 meter height with quite a lot of precision. We can, of course, measure things, but measurements are expensive and they take a long time. So the alternative is that we can use complicated computer programs to establish historical data speeds. They are, of course, not perfect. You need to compare them with observations, but it has been done for Europe and Latvia. Therefore, I would, if you are interested in this, I would recommend that you start your investigations in this area with those ready-made data sets. So that's all from me. I hope that there will be some questions.
Thank you. I don't know if any questions here. No hands, no responses, and yeah, so no questions from online speakers and listeners as well. It looks very nice, and I recognize Nevermap from your last slides. Yes, it's maybe not outdated, but it's not new anymore. So it's like 3 years, 4 years ago, but it's still maybe recent Baltic Sea resource for wind source. It's like wind models. Maybe you know about some kind of newest versions or something like this.
The thing is about wind climate, that actually, if for temperature and for the number of days with snow, there is quite a significant impact of climate change. Actually, for wind, the impact of climate change is much less pronounced. So the fact that we have older data for older periods of time, it's not as bad as yeah. And the previous European Wind Atlas, I think, is from the 90s. So there's quite a big gap between these wind atlases. They won't be
for more than 20 years, I think.
Yeah. There is one reanalysis called NORA that it's newer and it's quite good, but it covers I think Latvia a bit. It's mostly focused on the Scandinavia. So there are smaller, more focused products that you can look into, but it strongly depends on the area that you're interested in.
But do you have experience with Copernicus Wind Atlas? As I understand, it's based on satellite data that looks quite new as well, but I have not deeply go inside. So just find it's nice data, but not able to compare it with NEVA, for example.
I will have to look into that. What I can say that from satellite, first of all, from satellite you can measure the wind speed only over the waters. And also there is this problem that I already talked about, that when you are using satellite, you are measuring wind speed over the water by measuring the properties of the small waves on top of the on top of the water. So by definition, you are measuring wind quite close to the surface of the water. And again, if you want to calculate the wind at 100 meters, then you have to be very, very smart about it. That's the thing.
Yeah, thank you. Yeah, I think so. All questions from my side. Thank you for joining us and thank you for your talk.
Thank you.
So, Andrei, tell me, are you here?
Yes, I'm here, so I can share my presentation.
Excellent. So, yes, please share your screen. Andrei Zvaigzne, Riga Technical University, with his talk, Coastal Fishing Vessels Powered by Zero Emission Hydrogen Fuel Cell. Yeah, so we see your screen, but not full screen.
Okay, just a moment. It's better now?
Perfect. Okay, so yeah, floor is yours. Let's start.
Okay, thank you very much. I think also my presentation is a very good fit for the TIA presentation. Yes, first of all, I'm Andrei Zvaigzne, I represent Riga Technical University, and I will talk about our new project, what we are doing, this Horizon project H2Seas. And as I tell, it's perfectly fit for the previous presentation. As we learned that there is some periodical in energy, so we can, some periods we can have more sun, when sometimes we can have more wind, but the question how to store this energy and what to do it. And one of the solution, of course, is hydrogen. That hydrogen can be used for store the energy and use it when it needed, but not when you have a sun or when you have a wind. So our project is a coastal fishing vessel powered by zero emission hydrogen fuel cell. It's under the Horizon program. And the idea is to build a vessel, fishing vessel, using this zero emission and mostly using this hydrogen energy to power this vessel. Oops, sorry. In simple word, what we want to do, we want to design, build and test real fishing vessel, 12 meters size, what can be operated in Northern Sea and the Baltic Sea basin. Project partner, it's Riga Technical University lead partner. We have also Stockholm Environment Institute, French company Genevos, responsible for the hydrogen part. Atos Group is a shipbuilder, and Vidzemes University of Applied Science for our legal and testing thread. Standard working package what we have in the project. VP1 is the overall management. VP2 is we evaluated regulatory aspect and marine environment impact using of the hydrogen and how its impact was a law regulation, etc., etc. VP3 is a zero emission solution. It's a hydrogen system itself, how it's installed and how it's modulated and for the vessel. Shipbuilding, of course, it's everything that's related to the ship construction. VP5 demonstration at sea, and VP6 is a dissemination exploration. Taking account the direction of our seminar, so I will focusing on this two working packages, what is more like say hard part of the project. It's a zero emission solution and shipbuilding. A few words about the hydrogen technology. So this is a alternative to the thermic power engine, and it's of course have several advantages. First of all, there is no emission of the use of this technology. There is no noise. There is no smell. It's very reliable. There is no too many moving parts. It's of course very efficient. If we compare with a fuel cell, where is this maximum 35, 40 maybe % in the best case. In case of hydrogen, we can use up to 80% of efficiency. It's a scalable, so it's easy scalable. So we can put the small models and have a bigger effect, and can use several fuels: hydrogen, natural gas, LNG, LPG, several. So for Geneos, our main partner is a French company. They produce the hydrogen-powered fuel cells systems, what's specially thinking and specially built for marine application. And in our project, they create this hydrogen system, storage supply specification, manufacturing of hydrogen power model, and pre-assemble this model for the installations of the vessel, on the vessel. General idea of fuel cell that hydrogen coming together with oxygen and produces electricity, what we can use later on for different purposes. We will have this a hydrogen-powered model 40. These two models will be installed on our vessels. There's a general idea that it takes this hydrogen, it uses air outside, and what we have is water, hot water, electricity, but also what we need to cooling using the seawater for the cooling of the system. Powered model, it's a little bit scheme from the inside, that it's we filtering the air. Let's go in the model. Also, it's a gas management system. And what we have on the vents, it's electricity and seawater, fresh water, and other stuff. In the principle, what we have is two balloons where we will store the gas supply, power models, and let's go for the producer electricity. To calculate how much power we need, we also for the ship design, we make a typical fisherman, the coastal fisherman activities. How much power we need to leave harbor, transition to the fishing area, stay in fish area, and coming back. So we calculate approximately how much power we need for this. Build a graph. You see here, it's we use energy from the power fuel cells, hydrogen, and also the electric battery. So the idea is that to the end of our storage of hydrogen is almost empty, but on the end of the trip, our electricity is almost full. So it's how it's look on the vessel. There's two bottles go to the fuel cell, go to the electric battery, electric motor, and to the propeller. The main components, as I mentioned, this is a storage, this is electrical cabinet to control, the valve panel to control the gas flow, and the safety different sensors to control the situation of the vessels. So this is a principal electrical. And the valve, scheme. Problem also, the disadvantage of the hydrogen, of course, is a big storage compartment, what you need to keep hydrogen on the vessel. So we will use a special marinized system, the Luxor gas cylinders. And this is an electrical system, the control system where we control the bunkering station, we control on the bridge, we control the general sanitation and energy management system for the vessel. This is also some advantage and disadvantage of the fuel system and putting on the deck. So We have a better stability, but of course less space on the deck. Easy to control ATEX zone. Well, I explained later. Yes, so putting the batteries over there, we easy to control. ATEX is a dangerous zone for the exhaustion gases. So in case of any emergencies, this gas just go up and not affect any deck space area where the personnel waiting. This is manufacturing of these models. This you can see is a testing. Before they deliver it to the vessel, they make a rolling pitching, so the system can work in the hard environment. This is the cylinders. As you see, it's quite big. It's almost 3 meters long and quite heavy, but it's still only 9 kilo of hydrogen each. So this is a valve panels, what we will install. And for the shipbuilding, also you see one of disadvantage was the big storage compartments, these bottles. So we need to take care of it. But before we start, we define the prototype, what we need to build, how we need to build, what the operational cycles for the normal fisherman, coastal fisher boat. We make a feasible concept to make a preliminary design to see how to install this big bottles. You can make an imagine for the 12-meter boat to have 3-meter balloons. It's quite complicated using all the stabilities and calculations the vessel. After the preliminary design, what we deliver it to the shipyard. Shipyard go to this for the construction design, and the problem also that what is very challenging for this project, that we want to deliver sailing ready boat what they fully certify. So the readiness level of this project need to be almost the maximum. So this is normal vessels what we can sail at sea. So it's put us on the very hard requirement from the Latvian Maritime Administration. And as they have no experience of certify the hydrogen vessels, so they say that you need to go through the class certification, and we go to the Lloyd register, we go to this GNV, but finally we find this Polish Maritime Register who certify, so control the shipbuilding and certify the project. Here, also back to the topic of the seminar, there's some drawings. So what technical drawings we did for the vessels. Yes, this is was quite challenging to select the classification society. So it took some times and affect a project. But finally, we succeed, and we are in the process of a shipbuilding now. So this is some fundamentals for the construction. So we several steps for fabrication. This ship construction, general arrangement, selection, and the different system what need to be build, and first of all, of course, design and build inside on the vessel. So you can see some drawing, the technical drawing, what necessary for ship certification and also for the construction. The whole, the build and ventilation. As we use hydrogen, so it's a very complicated, I would say, ventilation system for the 12-meter boat. And we need to develop all this for the safety reason. Also, as we're going to deliver, show the ships in different places in Europe, so we make the removable wheelhouse, so a superstructure. need to be connected. This on May we make the first welding. So you can see some pictures. The boat. As you see, the construction go upside down. So we make the main structure. And of course, all the construction is supervised by Polish Register of Shipping. So they make a several inspection. Sorry. And finally, we turn the vessel, let's say, in normal position. And our ambition is to make a demonstration at sea in June in Latvia, in August in Pärnu, and in September we want to bring this vessel to France, to Boulogne, to show there. So this is a main presentation, so thank you.
No, thanks a lot. So very interesting. So you're almost done with production, and in next months actually you're starting testing it, right?
Not actually, not that we just finished with a hull, but still a lot of work needs to be done. All the inside installation, and hopefully in a few months we will bring all the hydrogen system from France to install on the vessel. So it's still a lot of need to be done for the project.
And what about like a filling with hydrogen? So are you planning to use some kind of existing infrastructure, which is, I understand, quite rare, or just bring hydrogen?
Thank you for the question. It's really headache. I am not covering here because it's another working package. But yes, when we start this project few years ago, actually, yeah, you know how it is. You write it, you submit it, you wait for the result, and it was quite ambitious plan that we will have this hydrogen supply station in Riga and several stations around Latvia and in Estonia and France. And unfortunately, for the last years, all this project was put on hold or cancelled. So it's quite a challenge now. In Riga, for the moment, we have only one for the bus station supply, but it's not really convenience to bring vessel to the bus station. So there is in Jelgava now also for the bus, and they have some sort of mobile station. So we are looking now. There is also a big international company who can supply this, and generally it's possible. We discuss with them; they can do it, but we are still looking for the better and cheaper options. Because also one thing that we need to bring the supplier to the vessel. That means that it need to go to be movable, and they need to go to the vessel. And another, it's also need to be certified, because the gas need to be clear enough that there is not cost a problem for the vessel at sea.
Well, thanks a lot. I think it's a question to market project as well, because we are trying to identify problems and gaps in innovations and infrastructure in the Baltic Seas. And this is clearly one of the problems that we need to highlight about refueling stations in port and services regarding hydrogen. So you are having ships that could work and could be replicated, but not infrastructure not ready for these ships at this moment. So it's a problem. Thanks a lot, and thank you for coming to our workshop and with a very nice presentation. Good luck with your project, and we try to be in contact and follow your results as well. Thank you. Any questions?
Thank you.
No questions. Right, second.
Thank you, and good luck with the seminar.
Yeah, thank you. So no questions, so we can continue to another talk. Yeah, so now we have a bit another format. So now before it was talks, just the discussions and showing well, cases of real results. But next we will try to switch back in demonstration modes. And Modris Dobris, are you here? We see your screen, but we don't hear you.
Okay, good afternoon.
Good afternoon. Nice to see you again. Yeah, so I will give floor to you, and as I think you will show kinds of demonstrations how we can go back to SolidWorks and use this tool for modeling as well. So yes, floor is yours, and maybe we can start. And I switch myself.
Okay. Too many screens to manage. Sorry. My name is Modris Doblis, and I am from Riga Technical University. In this lecture, we will move from educational framework I talked yesterday to applied examples. However, no water, no wind, no so global simulations that I had before in your workshop. Sorry, down to earth. In modern engineering practice, digital simulation has become an essential part of the design workflow. For many students, CAD feels intuitive because it is visual and immediate. Let me start with a few case studies of typical simulation tasks inspired by local industry. As I mentioned yesterday, some of them joined my courses, regardless that they are specialists in their field better than me. At the end, I will conclude with a structured parametric CFD workflow. The focus will be on workflow rather than on the physics, what is beyond the scope of my courses, as I mentioned yesterday. The scope is how a simulation task is defined, how parameters are selected, and how parameter what-if scenarios are set up to support engineering decisions. My introductory course is SolidWorks, and it focuses primarily on creating parametric design intent-based geometric models suitable for simulation and later reuse in what-if scenario studies. A secondary goal of the course was to train students to independently identify simulation tasks in selected reverse engineering projects, especially those that would benefit from high-performance computing resources, and to gain initial hands-on experience with these workflows. The course does not cover simulation physics, as that is the responsibility of later, more specialized courses. This focus was also a practical requirement to secure additional funding for the development of teaching materials in this project, the results of which are partially shown in my presentations. Oh, sorry. For this reason, I recommend oh, sorry, I lost the slides. For this reason, I recommend exploring the flow and thermal simulation examples, as they clearly demonstrate the values of parametric models and fit naturally into more complex CFD and multiphysics studies. Using SolidWorks, a virtual 3D model of the device is created, which is then analyzed with flow simulation to study gas or liquid flow and thermal effects. The correctly performed simulation, users must understand the physics represented by the model. This requires clear control over fundamental geometric entities, points, lines, planes, surfaces, and volumes. Based on the simulation results, the model is iteratively modified according to the defined design intent, and simulations are repeated until the satisfactory performance is achieved. Only after this virtual validation step is the physical prototype manufactured. Without the correct geometric and physical understanding, even advanced simulation tools produce misleading results. Beginners often confuse 2D geometry with 3D bodies. Example, hexagon in plane, 2D plane, versus cylinder in space. That is true for this today's students, which leads to invalid simulation setups. And as a consequence, it leads to the famous quote, garbage in, garbage out. So you get nice pictures, but they are useless. Before focusing on the Tesla valve, I would like to briefly show several applied digital simulation examples. These were prepared by participants of my course from industry and by students, based on their own real engineering tasks, demonstrating how simulation is used in everyday professional work. Here you can see airflow simulation in a hot swap fan. Here, CFD is used to analyze cooling efficiency and flow distribution under constrained installation conditions. Familiar company in Latvia. Some of you might know, but I will not just name it. In a chemical reactor, parametric simulation allows studying how diffusion is influenced by factors such as reactant concentration, temperature, reactor geometry, pressure, diffusion coefficient, flow regime, and fluid type, which is critically important for understanding and quantifying mass transfer in industrial scale chemical process design, because improved diffusion leads to better reactant mixing, more complete chemical reactions, and ultimately a more economically efficient process. Next, natural convection in a unipolar stepper motor drive. A thermal fluid interaction example illustrating how buoyancy-driven airflow affects heat dissipation without forced cooling. Further studies for the stepper motor are expected to increase model fidelity toward the real prototype by introducing more realistic part-to-part contact definitions, modeling forced airflow with improved aerodynamics accuracy, and using thermal simulation results to optimize heat sink, size, and placement for a given airflow, as well as fan parameters under fixed constraints of the drive prototype geometry. Further studies in this case, the student demonstrated how a complex engineering system, a turbojet engine, can be analyzed using parametric modeling and CFD within SolidWorks. A detailed 3D model consisting of 761 components was created using a top-down design approach and then used for an internal flow simulation representing high-altitude takeoff conditions. The simulation visualizes airflow path, pressure and temperature distribution, and velocity changes inside the engine, showing how air moves and interacts with internal surfaces. The results illustrate stable pressure levels and predictable temperature increase due to thermal loading and realistic three-dimensional flow behavior. Overall, this example highlights how parametric CAD models combined with CFD can be used not only for analysis, but also as an effective tool for understanding system behavior and supporting design decisions. It is important to note that SolidWorks flow simulation is intended for low speed and moderate compressible flows and is not suitable for high Mach number regimes. Applications involving strong shock waves or hypersonic conditions, such as Mach 5, require specialized CFD solvers. Tesla valve, in my example, is used as a convenient geometric example to demonstrate a what-if CFD workflow, including scenarios that may benefit from HPC resources. At this stage, the emphasis is on parameter control and the result interpretation. Detailed fluid physics is intentionally left off for online self-study or later courses. For context, the Tesla valve principle is widely applied in microfluidic devices such as micropumps and microvalves, where it enables directional flow control without moving parts, which is especially valuable at small scales. Further, I will briefly introduce the geometric parameters used in this study. My practical sample focuses on how to properly set up a parametric flow simulation in geometric model rather than underlying flow physics. But before this, I would like to reflect on what I saw and heard yesterday about the Service Pack 1 of SolidWorks 2026 coming up next Monday. In fact, SolidWorks, the announced artificial intelligence also has for a long time built in, which is coming up only. The result of preview we all saw yesterday, and but however, the industry will not yet be very happy with this. Here is the example of what my students do with this standard view one button setup, which is similar like this artificial intelligence. We must be careful with not overestimating the current power of artificial intelligence. So this is one button drawing the students prepare, but I expect something like this. So a small off topic, but still connected with SolidWorks. So PLM-oriented CAD training of Gen Alpha at the universities is an enormous challenge today. So especially when the baby boomers generation like me has to teach them. So back to Tesla valve. In this CFD study, the Tesla valve model is evaluated within a defined parameter range by varying the numerical value of a single geometric parameter in discrete steps. Even changing two parameters across a range rapidly increases the number of simulation variants, whilst 3 parameters, if you want to change, already require systematic planning of experimental points in a multi-dimensional space. When the number of parameters grows beyond 2, classical manual experiment planning becomes impractical and must be replaced by dedicated experimental design methods. By the way, as early as 1977, Vilnis Eglais, a researcher from RTU, then Riga Polytechnic Institute, developed an original optimal design approach based on the theory of experimental planning, closely related to what is now widely known as Latin hypercube sampling. In this demonstration, HPC-assisted simulations were therefore limited to varying just a single one parameter. The angle beta in this drawing within the shown range from 45 degrees with increment 5 degrees until 100 degrees. The design in SolidWorks was created as design intent, which follows the design intent, and these all red parameters control the setup of this design. Here are shown some screenshots from this setup. Later we will try to practice by ourselves, but in much simpler case. So setups of and some steps of solution. I saw yesterday you were also practicing on one example which was very similar to this I'm going to show you today. The task in this project was to prepare simulations which require HPC resources. But to prepare this before they know this physics, therefore this was great challenge for beginners. The simulation task must be executed remotely on RTU supercomputer using standard Windows remote desktop connection. So actually the connection is very easy. Each project participant was provided with an individual remote access account, allowing them to work in a familiar desktop environment while using HPC resources. A dedicated SolidWorks virtual machine is configured on HPC system to match the specific requirements of the simulation tasks. The CFD model is first prepared on a regular personal computer, not so powerful, and then it is easy transferred to HPC virtual machine, where the SolidWorks flow simulation solver is launched. And if the computational load increases, the task becomes too complex. An additional HPC resources can be added in the same setup, and the task can be simply run, enabling larger or more detailed simulations without reconfiguring the primary virtual machine, which was assigned at the beginning for the participant. The following screenshots are shown primarily to illustrate the simulation setup workflow rather than to analyze the results itself. They highlight how the geometry, boundary conditions, parameter definitions, and solar settings are prepared in practice. At this stage, the goal is to demonstrate the structure and logic of the setup process, not to evaluate the physical correctness or optimize the design yet. In this presentation, I focused on explaining how to set up a parametric CFD study in a structured and repeatable way using SolidWorks workflow. The emphasis was placed on creating a clean parameter-driven geometric model, defining meaningful boundary conditions, and selecting a limited number of parameters to explore realistic what-if scenarios. By deliberately varying only one geometric parameter, the study illustrates how parametric simulations scale in complexity and why experimental planning methods and HPC resources become essential as the number of variables increases. The key message is that simulation value does not come from colorful plots, but from well-prepared model, controlled assumptions, and a clear understanding of what questions this simulation is meant to answer. Actually, this is, thank you for your patience. And actually, this is all for the first theoretical part I was going to deliver to you.
Thanks a lot. Quite interesting. Any questions or comments or questions on YouTube side? Okay, it's our no activity. Yeah, probably we can continue with second topic. And you made SolidWorks example. It's exactly about this practical with the Venturi cube. Is it right? Or so SolidWorks file what you sent it before. This is about this one. Yeah. Yes.
This is about what I prepared when you asked me some practical. I don't know it will fit your needs, and unfortunately the problem was I work with SolidWorks 2025 and files are not back compatible, and you are working in SolidWorks 2018. And yesterday I was able to find one old machine where I had SolidWorks 2017, where I, through step file, converted the current contemporary model to the old one, so you can open it without wasting time to build it from the scratch. And just but a short time before I tried to check if the model works. Looks like it works, but might be some problems because of these versions. So each year, new version, new challenges for CAD designers, as you know. All you are familiar with this.
Yes, it's a problem. So it's new features, new looks, and you need to again learn how to use it. Not from the beginning, but it changes a lot, sometimes a lot. But I just in parallel tried to run this part, and no, at least in our computer it's opened with no errors. So this is probably good. So I think we can listen to your presentation, and after make a coffee break and relocate ourselves to computer class, because now we in auditorium, and continue like I think in more like interactive way in this case. Wow. So, but yes, but please continue.
Okay, are you ready?
Yeah, so I'll switch it myself off.
Yeah, okay, I will try to slowly go on. So I'm sorry, I did.
Maybe
Yeah.
not. Sorry, maybe now we can go like fastly through how it works, and after we in slow regime repeat it like following your guidelines. Like maybe we can do it like this one.
Oh, sorry. I expect that you, those who want to participate, are at least familiar with very basics of the SolidWorks, how it works. And here is represented a 3D model, part model of Venturi tube. Actually, after converting it, introduced some visual assistant planes, which I forgot to turn off, so we can start to improve a little bit this model before we proceed with simulation. So first of all, we can get rid of these plane 2, planes 3. Here in the design tree, they, after converting, are left as visible. If you show here with cursor and right-click on plane 2, several icons appear. We need to hide this one, not to represent, not to bother us here. The same applies to the plane 3. We can get rid, hide it, it's there, but it's just does not bother us. The second model has not assigned material. To be transparent, to see the work, this flow inside, let's assign glass material. Glass material to assign in the design tree, we must use right-click, edit material, since we do not have glass here in the basic material list. So right-click, edit material, find under the non-metals, other non-metals. Other non-metals, glass, which assigns a lot of physical parameters of the glass. If we have special glasses, we can create our own glass material to use it in simulations if they have special physical properties which do not match with library given ones. So this way we changed the model and now it is transparent. I expect you are familiar with zoom in, zoom out. And first thing is to activate simulation tasks is, oh, I'm sorry, I already practiced here and forgot to turn it off. So actually I was going to show you from the beginning how to activate, just in case it is not activated. Just in case it is not activated, you first explore under Tools, Add-ins. All the add-ins are additional software, part of software, which I recommend students from the very beginning. In my course, we do not deal at the beginning with these, and I ask them all to uncheck these, not to load and use the computer resources when we do not need them. Therefore, now, when model is created, And when we start simulation, first thing is we can explore what current version of SolidWorks, what we have, what we purchased, is available for us. Starting from 2024, academic environment has the same version of SolidWorks, the same SolidWorks premium version, the same year as industry. Before it, we, academic environment, we got 1 year delay. But right now, we got the same year, which is great benefit for students. So, and here is what we got for this premium version. These versions are very many. Even me, it's difficult to find out what it is. Here, there are these simulation options. And as you saw before, magnetic simulation, you have to purchase. This is not listed, included in premium. I don't know how much it costs, but you can add this. So we need, in short, bottom line, we need to activate SolidWorks flow simulation to be used in our current session. After a while, it does not load immediately. After a while, it appears here. Oh, sorry. Yeah, you saw. It happens. It happens. I don't know. You had the same situation. I will relaunch. This is because I have the version which was prepared in some way which is not expected. So we don't send these reports to the not to bother. This is educational. Okay, in my case, I just need to relaunch. Sorry, it happens, but not so much with SolidWorks. SolidWorks is quite an excellent software and works quite stable when we deal with it properly. I hope you will take time and catch up with me if you didn't.
Modis, maybe
yes.
Now we're not in a classroom, we're in auditorium.
Yeah.
I propose to make, let's say, 20-minute break and we relocate to classroom and trying to follow
okay.
your demonstration in computers.
Okay, so I will just show what I did before this. I turned off these two planes and assigned glass material. Assigned right click is under other non-materials, glass. Apply. I will make sure that it does not break again. Okay, and I will save. Please save. It shows that you have modified the 2017 version and save it to the current version you have. And then we can continue after your suggested break. So when we will start?
Let's say 2:40.
Okay, that's good.
Online, if you're willing to do some practical works as well, please write in the chat and try to adjust
okay.
control of computer for you. Yeah, so we'll meet in 20 minutes time.
Thank you.